first of all like to welcome each and every one of you to this program on astronomy research data analysis, where you are going to learn to create some amazing, beautiful looking visualizations that you can create from a boring looking CSV data or a tabular data, and even from the raw data from the astronomical surveys, how you can take that images and extract some amazing features present in those images. So all of this kind of work you are going to do in this particular program, and then whatever kind of visualizations that you will be generating, you can extract from Python into your particular system and then later on use it for your research work, thesis work or internship report, right? So that's the kind of thing that we are going to deal with in this program. So this whole program is divided into 4 different modules to make these things very easier for you guys, okay? But before I go ahead and explain any of this, let me quickly introduce to you all myself. So I am Rohan and I am currently working at Spartificial as a machine learning engineer, and I'll be the one who is going to guide you throughout this whole program. And I'll promise you guys that you are just going to simply enjoy this program, and you just need to code along with me. That's one thing that is really important. If you don't code along with me, it's just going to be boring for you, okay? Especially if you are new to Python, you need to code along with me, because each and every code that I'll be writing in the upcoming modules, I'll be writing from scratch. So I'm 100% willing that you all are going to code along with me, okay? So now let's talk about each and every module that we are having over here. So the first module, we are going to start from extreme scratch. Even if you are very new to Python, it's completely fine. In the first module, I have covered each and every basics of Python that you will require to create some amazing visualizations with the help of Python, okay? So module 1 is compulsory for you guys, just in case if you are new to Python. If you are already aware about the Python, then you are good to go ahead and move to module 2. In module 2, you are going to deal with a CSV tabular data. That data will be based on some kind of real stars out there in universe. Now from that tabular data, you are going to create some beautiful visualizations, including an HR diagram. If you are not sure about what is HR diagram, it's completely fine. Okay, we are going to learn about that in module 2. Then in module 3, we are going to go to the astronomical surveys, where we are having these raw images taken from multiple different telescopes, and from that survey we are just going to fetch an image of Andromeda galaxy and then do some of the pixel scaling and all this kind of basic visualizations with respect to an image data. And finally, in the 4th module, the last module, you are going to take that Andromeda galaxy and do a bit advanced level of image processing. And I am going to teach you that if you want to implement any kind of filter, if you want to extract any kind of features, that how you can do it with the help of Python. So that's exactly what we are going to cover in all of this upcoming 4 modules for this particular program. And I hope that you are just going to enjoy this, okay? So let's get started with the first particular module, that is basics of Python, from the next video. Hey guys, welcome to the second video of module 1. And here I am going to introduce you to Google Collaboratory Notebooks, or in short, you can also call them as Google Colab Notebooks. Okay, so for those who are not aware about it already, we use them in order to code in Python without actually installing anything in our system. Isn't it just great? So that's exactly what we'll be doing throughout this whole particular program. So what exactly are these Google Colab Notebooks, how it works, all of this kind of information you will be getting in this particular video. So let's get into it right away. So let's understand that how we can use this kind of Python notebooks that are available online in order to code in Python. The one that we are going to use is specifically called as Google Colab Notebooks. Okay, so you go to Google and search for Google Colab. And now if you come onto the second link, you just click on that. It will redirect you to this page where you are getting this option of creating a new notebook. So let's go ahead and click on that new notebook. And now I don't need that first tab, so I'll just close that up. Now the whole idea about this kind of notebooks, which we also call as interactive Python notebooks, in short IPYNB, as you can see over here also, right? These files are basically used in order to have the mixtures of text cells along with the code cells. So what you are seeing right now on my screen, this particular cell which is getting blinked like that, this is called the code cell. I can create multiple code cells by clicking over here. And I can do my specific task I want to do over here, 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 and get my outputs done. You will be using this a lot as we go ahead in this program. But yeah, this is a very basic introduction with respect to this code. Let's say you're writing some kind of a code in Python over here. If you want to run it, you simply come over here and click on this. Or else you can also see there is a shortcut that is Control Enter. You click on Control Enter and this code is going to run. Okay, and let's say if you want to go to the next cell by running this cell, you click on Shift Enter. It automatically shifts your cursor to the next code cell or any kind of cell. Let's say if I want to create a text cell between both of this code cell, I hover my mouse in between two cells and over here I'm getting the option of text. I click on that and I get this option of this text cell. Now the purpose of the text cell over here in this kind of IPYNB notebooks is to give you some kind of description of what will be done in this following code cells that we are writing. So in this kind of interactive Python notebooks, you are getting this kind of facilities to decorate your notebook the way you want, so that if anyone who is going to look into this notebook, or for that matter, let's say even yourself who are going to look into this notebook after let's say some months, you need to know that if your documentation is good and visually appealing, then it's very easy to find out a lot of stuff and it's going to be interesting to scroll through this whole notebook and get to the exact point where you want to find out some kind of information. So it all depends on how much decorative notebooks you want to create, how much kind of information in text you want to add, and then how much kind of code things you want to code over here and get your job done. Now, yeah, that was a very quick introduction about the Google Colab notebook, and pretty much things that you need to know about Google Colab is, I guess, enough over here. Some of the things that we can do to start over here before moving on to the second video would be, let's say, by naming this notebook. I'll change this notebook name to, let's say, basics of Python. Okay, any kind of name that is going to describe what kind of content is present within this notebook. And then I can also create a text cell and give a heading with the help of this hash. And let's say, because this kind of whole program is dedicated for astronomy visualizations and analysis from that visualizations, what we can do is we can give a good name like Python basics for astronomy, something like this, whatever suits you the best, right? And then after this we can start coding ourselves for the first thing in Python. Let's say, just like everyone does in Python, right, or any kind of programming language here, let's say we are going to print hello world, right? So if I'm writing hello world like this, right, and then I'm just going to pass this kind of hello world within print. This is going to be our first code that we have written in Python, print hello world, and that's exactly being printed over here. So now in this video I have shown you how you can create this kind of text cells, give headings, or not just headings, you can give images over here, you can add links to a specific word you want to add, you want your people to redirect to some stuff, you can have bold, italic, and all this kind of stuff. After that, I've also shown you how you can start using this kind of code cells in Python. And obviously, if you did not understand what have I written over here, why did I specifically have this kind of quotation mark, everything will be covered in the upcoming videos. So stay tuned. Hello everyone, welcome to the third video of module 1, and here we are going to talk about Python comments. So what exactly are these Python comments, why do we need them, and what are some kind of different ways to actually create them? All of these kind of things we are going to discuss in this video, so let's get into it. Alright, so now that we have written a specific code in Python, now let's say I want some kind of a way through which I can describe what I have written over here, or what is the purpose of writing this kind of code. I can do this with the help of Python comments. Okay, for that again I'll have to use this kind of hashtag, and then I just give any kind of description that describes what is the purpose of writing this code, what does it explain. So now, because this was my first code that I have shown you in Python, I can give this kind of a comment like my first code in Python. You can also write this thing for yourself, right? So what is the main purpose of writing this kind of comments? So whenever you are writing some kind of a logic of your code, if you are having this kind of comments that you are writing to describe your logic, that how did you come up to this particular logic to solve a particular problem, then what happens that even after, let's say, 1 year, 2 years, if you are coming onto this notebook, and now because you are having this kind of descriptions in Python that is describing what you have done, It's giving you a hint, some kind of this kind of a click to your brain that okay, now I remember why I had coded this specific thing in this way. Maybe because after 2 years of time, so you're coming onto this concept which you haven't touched in a while. Let's say you're trying to apply for an interview. You want to take a project that you have created over here and explain it to them. So if you are trying to revise something which you haven't used in quite a while now, so if you will be having this kind of comments in Python, that will help you to revise this kind of things very quickly, because this kind of comments is going to click your brain that okay, now I remember what was the reason that I had done this kind of code in this specific way, right? So that's the whole idea with respect to Python comments. But now that's not the only one way through which you can have the comments in Python. Okay, because over here we are having only one line of comment. What if I want multiple lines of comment, right? For that, what I'm going to do is I'm going to create one more text cell over here first of all, and just introduce to that the first thing that I'm teaching you guys is about comments. Okay, and I can also give this into this way of heading. Okay, 3 hashes, and now you can clearly see that this kind of text is much more smaller in size as compared to this. So this looks good, right? But yeah, now what I'm going to do is I've already explained the first thing about the comments over here. Now let's say if you want to have multiple line comments. Okay, so what I can do is I can use 3 quotation marks. Either I can use 3 single quotation marks or 3 double quotation marks. Both of them is going to work just the same. Okay, so I am having my first 3 double quotations like this and 3 double quotations at the bottom. Now anything that I am going to write within this quotation marks is going to be like a comment. Your Python is not going to execute as in the format of like some kind of a code. It's going to do something. It's just some kind of a description that you are going to mention over here. Let's say some kind of huge description you want to have, okay, is as compared to just a single line. Then obviously you can go ahead and use this kind of things. Let's say this is my first line of comment. This is my second line of comment. I'll be showing you this, that I'll be using this when I'm going to teach you the concepts of functions. At that times I'll be using this kind of multi-line comments. Now again, let's say that you are having bunch of lines that you want to write. Let's again, this is my first comment. This is my second comment. Now let's say if you want to comment all of this thing with the help of this hashtag only, you don't want to use this kind of quotation marks, then what you can do is, let's say how many lines I am having, it doesn't matter. The important thing is that I am going to select the whole text and then press Ctrl plus / and automatically it's going to give me this kind of hashes by itself. I didn't do anything. I just pressed Ctrl and the /. What did I do? I selected the text below and pressed what? Ctrl plus this. By doing this together, you can either comment all of this kind of code or maybe decomment it by again pressing the same thing. That's simple that it gets for the comments. So for a quick revision, what we have done over here is, now you know how to create print statements in Python. Obviously not like you are not aware about this, that why did we use this kind of quotation marks, what happens if we don't use it. I'll be explaining all of that thing in the following videos. But yeah, for now you know how this kind of print statement works in order to print something, and then what are the kind of need of writing comments for your code. Now in the next video, I'm going to talk about what are variables and constants that we need in Python. Hey guys, welcome to the 4th video of module 1. And here we are going to understand the concept of variables and constants in Python. What is the difference between them, and when and how should we use them? All of these things you will be getting in this particular video. Now, one thing that I really want to make sure over here is that I hope that you all are coding along with me. That's the whole fun about this particular program, that you are going to code along with me, and it's going to give you live experience instead of just watching the video. Alright, so if you haven't begun it till now, this is the right time to get started with it. Okay, so let's get into the video. So now what I'll be doing is I'll be just commenting this whole thing because it's looking very ugly. What is the reason behind that? You will be understanding right now in this video. So what you are studying right now is called as variables and constants. Okay, so before I write any kind of code, I'll be giving a text that describes that I'm going to explain about variables and constants. Okay. Now what I am doing over here is just remember your classes of mathematics. You know that we give this kind of things like x is equal to 3, y is equal to 5, or any kind of number 6, whatever it is, right? You know that you do this kind of things. So what we are doing over here is essentially we are saying that x is a variable that is going to take the value of 3. It's just like that. Y is a variable that is going to take the value of 6. Now, what is the whole purpose of having this kind of variables in your code? For example, let's say that I'm writing a lot of huge code and somewhere I want to use the idea of that data that I'm assigned to that letter X. I want to use that again and again. For example, I'm giving you a very short example. Let's say I'm having a value of 3 that I want to add to a value of 3 itself. Let's say 3 plus 3. Now, if I want to write, let's say 4 plus 4, what I'll have to do is I'll have to change this to 4 plus 4 manually. Now, like this, let's say I'm having a huge chain 4, 5, then again 4, then again 5, like this. Okay. And now I'm saying that I want to change these values of all 4s to 3s. I'll have to change this manually. Then 5s to 2s. I'm doing all of this change manually. And let's say that this kind of code is pretty much long and you are having multiple times you have to change these things. So it does not make sense to write these things again and again in every kind of lines. So what we do is we try to store this kind of data in a variable. For example, x is equal to 3, y is equal to 2. And now I just need to type x plus y plus x plus y. That's it. Now, if I want to see, so you can see that this is 3 plus 3y because x is having the value of 3. Now, in place of 2, we know that we are giving y because we know that y is equal to 2. And similarly, again, x plus y. Now, let's say if I again want to change this to 4, 4, 5, 4, 5. I just need to change x value to 4, y value to 5. As simple as that. So that's the power of having variables in Python. Now, just like that, there is also a concept of constants. Okay. What I'm going to do is I'm going to simply go ahead and first of all print this to show you the outputs, how it looks like. So you are having this kind of 22 over here directly. Okay? It's the summation of this 4 plus 4 plus 5 plus 4 plus 5. So that's how this kind of thing is working. Now, one difference between these variables and constants in Python is what you are having. If you are trying to define a variable, you are always going to define it with the help of lowercase letter. You are always going to define it in the lowercase letter. And the moment if you want to convert this into a constant, you define it into an uppercase letter. Now this uppercase letter is going to indicate anyone who is reading your code in Python that, okay, yeah, now I know that this x is never going to change throughout your code, whereas your variables can go ahead and change any kind of data that you want to store in the variable, because the name variable itself means that it is varying, right? It's not constant, right? So that's the idea. What I'm trying to say is that in my next code over here, I can change the value of y to some other value, for example 1. But because I have mentioned x in the uppercase, we are simply saying that, okay, yeah, this x will always be 4. It will never be changed. No matter how deep codes I am writing, x will always be 4. So that's a very common difference between variables and constants. In variables, you try to assign any kind of data in form of small or lowercase letters. And if you want to store the value of constants, what you do is you assign any kind of value and give a uppercase letter to that. So now both of them are now stored in the format of what? Constants. Right? As you can see, there are this kind of lines that are appearing, that are giving you this kind of yellow lines. What it indicates is simply indicating that x is not defined, y is not defined. Why it's not defined? Because I have removed that part of code. I have removed that part of code. But at the same time, it's also stored in the memory of this notebook. It is also stored in the memory of this notebook. What I'm trying to say is, if I comment out this code, And now I run this, even though I haven't defined x, y anymore, it's still giving me the output. Why? Because initially while explaining you the code over here, I had started with small x and small y. So now that small x and small y is by default stored into the memory of this notebook. So make sure this kind of things are not repeated in your notebook, or else you are going to run into some kind of errors. Okay. But here was a very quick description with respect to what are variables and what are constants and when you should use what. Variables can change its data that it's trying to store, and constant will try to have a very constant value. It will never change throughout the whole code. That's the whole idea. Now I'll see you next with respect to what is strings in Python. Hey guys, so welcome to the fifth video of module 1, and here you are going to understand what are some basic data types available in Python. We are not going to talk about all of the data types, just some of them, including string, integer and float. Okay, and also when I'm going to start the video, I'm also going to talk about a concept of runtime in Google Colab. It's really important guys that you understand this particular concept. So I'm just going to start with this concept in this video. So let's get into it. So now let's look into the strings. So what I'm going to do is I'm going to create one text cell, give a heading as strings. Okay. And now if I press shift enter, it automatically creates a code cell for me. Now one thing, okay, before I'm starting the explanation of the concepts of strings, I really want to show you what really happens if you try to click on this runtime and let's say for example you want to restart your notebook. Okay, so what you do is you click on restart runtime. It's saying that whatever kind of memory that was stored in this notebook, everything will be reset. And if I let's say click on yes, and now if I try to run this code, see what's going to happen. It's going to throw an error this time because xy, this small x and small y variables are gone because I deleted all the memory by restarting my runtime. So that's one thing that you need to keep in mind. Okay, if you want to define this x and y, and if you're then removing it and changing it to some other thing, then you should be cautious about that thing. So now moving on to the strings and the concepts with respect to that. So what is the whole idea behind the strings, right? So let's say if you're having some kind of a numeric data, you know how you can assign it to some kind of variable or constants. That's fine. But now what do you, if you're having some kind of a text data that you want to assign to a variable? For example, let's say I'm trying to create some sort of variables, create variables to store the information about a planet in our solar system. Let's say the first thing that I'm trying to store is the name of the planet. So I need to assign some kind of a variable to that particular name of the planet that I'm going to use. So for that, again, I'll have to create a variable, right? So let's say I'm going to call it as a planet name, something like this. You can also call it as a name underscore planet, anything that you like. Now over here, if I want to give a name as Venus like this, it's not going to work. Why? Because there is nothing like Venus that we have defined anywhere, just like for this x and y that we had seen in our previous video, and even for that matter in the starting of this video. If we did not define this small x small y, it's going to give you this kind of yellow kind of line below that thing that hey, you haven't given me any kind of value that we need to give to Venus. So it's going to run into an error that Venus is not defined. If I go ahead and run this, it's going to say that name Venus is not defined because we haven't given any value to this. So if you want to assign a text data to some kind of a variable, you always do it with the help of this kind of quotation marks. Now this quotation marks is going to ensure that okay, now this is a string. This is called as a string in Python. And now if you run this, it is storing this kind of text data in the variable called planet name. Now if I want to go ahead and print this thing, let's say I'm trying to print the name of this planet by calling the variable in which I have stored it, and now you will be seeing that it's printing the Venus value. What happens if I'm going to print like Venus without even defining what is Venus, right? Like this, it's again going to throw an error. that Venus is not defined because in itself you have not defined Venus as a variable. Over here, planet name was a variable which we have defined earlier before printing it, and that's why this is running without any kind of errors, unlike this thing that you are seeing over here. And the same kind of concept has been used over here. In order to print hello world, I need to pass it in the format of this kind of quotation marks so that it is converting this kind of data into string. And now Python understands automatically that go ahead and print this string data. It's not a variable anymore. If you don't give this kind of quotation marks, it expects this hello to be a some kind of a variable. You can again see there is some kind of automatic yellow line appearing, right? Because we haven't defined this hello. If I run this, it's going to run into an error, right? So that was the reason why I was having even the quotation mark in the first code that I had shown you guys to print hello world. So that's how you can define a string in Python with the help of this quotation marks. Now it's not that you always use this kind of double quotation marks. You can use single quotation mark. I can do the same thing by giving this kind of single quotation mark. This is also a string. I can go ahead and print the same thing. It's going to be Venus this time, right? I'm going to delete this code. And now I can also use, let's say, 3 quotation marks, either of single type or double type. Even that is fine. Again, this is pretty much useful when you want to create a string which is of multiple lines. So let's say I want to give a description line by line. Let's say this is Venus, right? And now I want to give this information that planet name is Venus. Okay, now I want to give this kind of information. This is the second planet in our solar system. First is Mercury, second is Venus, right? So this kind of information, if I'm giving over here, if I want to store it in multiple lines, for that I'll require to have this kind of 3 quotation marks, either of single type or double type. Okay, I can change this to double also. 3 double quotations, even that will be fine. Okay, but before I run this code cell, before I go ahead and run this code cell, I'm going to print it. See, this is how you are getting multiple lines of text, right? Now if I run this code and again I run this, you will say there is no change because essentially it's happening the same thing. But now what happens if you're trying to have this kind of multiple lines of code with either single quotation or double quotation like this? It's not going to work. It's only capable of taking this kind of multiple text by using 3 quotation marks of either single or double type. So yeah, that's the idea with respect to strings. Now you can store as many kind of information with respect to this kind of planet. For example, name of the planet is Venus. I want to give Venus to it. Then let's say if I want to store the age of the planet, approximately Venus is about 4.6 billion years old. So planet age is 4.6 billion years, right? I can write this kind of information over here. I can also write, let's say, what is the index of this planet? Planet index. What do you mean by this planet index? That on the first index, we are having Mercury. On the second index, we are having Venus. On the third index, we are having Earth, right? So Venus comes on the second index. So you can store this value is equal to 2, right? Now let's say in Python, if I talk about indexes, if I be very specific with respect to indexes, in Python, we start from index 0. We don't start with index 1. That's one thing you need to keep in mind. I'll also give a comment over here indicating that in Python, index starts from 0. Hence, Venus is on index 1 after Mercury on index 0. If I wanted to store the information with respect to Mercury, I would have written the planet index equal to 0 because it's the first planet we are having in our solar system, right? So that's the reason why we'll be indexing that as 0. Now Venus, because it's the second planet, we'll be calling it as at index 1. Now one more interesting thing that you can do over here is, if I'm just going to run this code, and now if I print this information that is name of the planet and planet age, and also the planet index. Okay, now if I'm going ahead and running this code, it's printing me all of this respective information. Now, if I want to check the type of the data, if it's a string type, if it's a integer type, or if it's a float type. Now, what is the meaning of float? If you're having a number in decimals, okay, if you're having any kind of numbers in either fractions or decimals, then you simply call it as a float number. So if I'm trying to check the type in Python, what I need to do is, along with printing them variable, I also want to check the type of the variable. So what I do is, along with printing this variable name, I am giving one more command in Python called type. And now what is this type going to do? It's simply going to reveal what is the data type that has been stored in the respective variables. That's the thing that I'm trying to look after. And now if I simply run this code, you can see that the first two things are of class string. It means that this planet age and the planet name, both of them are storing a data that is in the format of strings. When I talk about planet index, now that is not a string, that is an integer. Okay. Now, just because I also discussed about the float, let's say I'm creating one more variable, let's say any random variable for that matter, z, and I'm giving some number to it, 3.2. Now I've explained that any kind of decimal number or a number that you are able to express in fraction, you can call them as a float type. So if I go ahead and print the type of variable z, see what happens. You will be seeing that it's coming out as a float. So yeah, this was a very quick introduction with respect to what are strings. And not only strings, we have also discussed about integers and floats. So these are some basic data types that you must know in order to go ahead in this particular program. Now, in the next particular video, I'll be explaining you with respect to what are some kind of ways through which you can play around with the strings and do some more beautiful stuff when it comes to strings. Hey guys, welcome to the sixth video of module 1. And here I am going to discuss about one of my personal favorite concept in Python, known as f-string. So we're going to talk about what are these f-strings, how to use them, and when should we use them. And by the end of this video, I'll also be talking about what is the concept of string concatenation and how you can achieve it with the help of f-string as well. So let's get into it. Let's try to do something really unique with the strings. Okay, it's going to be some kind of a magic. Let's try to go ahead and explore what I'm talking about. But before that, I can also call this as basic data types. This is looking a very big name. I'll just change this to basic data types. Okay, I'm going to change this to basic data types. Okay, and these data types are what? Strings, float, and integers. These are the data types that we have discussed about. Now I'm going to talk about f strings. Okay, I'm going to talk about f strings. Okay, now what does this mean? For example, let's say I want to print some kind of a statement which is saying that how many moons does a Jupyter have. Okay, so let's say I'm trying to print a statement. Now because I want to print a statement, I'm going to give it within a quotation that planet Jupyter has, or not Jupyter, I should say Saturn, because I'm looking forward for Saturn, not Jupyter. So planet Saturn has 146 moons. The reason I would choose Saturn is because I've just looked onto Google that yeah, currently as of June 2023, there are 146 moons that have been confirmed for our planet Saturn. Right? So I'm writing this detail as of now. Now, as you might be knowing that as the astronomers are having much and much more information about this kind of gaseous giants that we are having in our solar system, they are keeping on updating the values of the moons once they are discovering new moons, right? So now what happens in future if we want to update this kind of values? Let's say we found out that Saturn is now not having 146 moons, instead it's having 150 moons, right? So I'll have to manually change this value to 150 to print this kind of thing, right? So now what I'm going to do is I'm going to create a variable called as Saturn moons. Okay, and I'm also going to change the name of the planet. I'm also going to store that. What if I want to print the information for a different planet, right? So I'm also going to store this thing as a name of planet, and I'll change this, not Saturn moons, let's say moons of planet, something like this. Whatever makes sense to you, give a very good name so that if anyone is reading it, everyone is able to make a sense of what's going on. So name planet moons planet. So I can give the name of this planet as Saturn as of now, and I can give that currently it's having 146 moons. Now what I want to do is I want to print the variable as it is. If I'm changing this variable, the print statement should automatically change. Okay. For example, if I want to replace this Saturn with this variable, what I need to write is I need to write name planet. Similarly over here, I will change this thing to moons planet. But now if you notice, if I run this, it's going to print the same thing as it is. It's going to print the same thing as it is. Right? It's going to print the name underscore planet and moons underscore planet instead of this Saturn 146. What is the reason behind that? It is because we are not giving any sort of an information to the string that, hey, you need to take the information from this variable and not print literally the string that we are giving over here. So that's the purpose of f strings. You are giving f over here and then writing this thing within this kind of curly braces. Okay, I'm giving all the variables that might change into this curly braces. And now if I run this, you can see that planet Saturn has 146 moons. Now let's say in future if this changes to 150, you can see that planet Saturn has 150 moons. You don't have to go to, let's say I'm having multiple print statements with this planets Saturn with moons of planet Saturn basically, with multiple print statements. I don't need to manually go ahead and change this 150, 150, 150. Okay, I just need to make a change to this variable, and everywhere else in the code it will automatically be updated to 150 because we are having the change in the variable. That's something you need to keep in mind. That's the power of f strings. That's completely a magic. Okay, it is also used like, if you want to, let's say, concatenate two strings, if you want to join two different strings, even then you can use this kind of f strings. There are multiple methods, but let's stick to a very specific method because this is a universal method that always works. So let's stick to this particular method. I can also give a name over here describing the code. I should say comment, not name, and I should describe it like understanding the power of f strings, right? Over here also I could have given this kind of comment, checking the type of variables. Obviously for me, I already know what kind of this kind of things is, but for someone who is a beginner, who is going to look into this kind of notebooks, for them to understand what are the things that we are doing over here, right? Anytime, let's say in future, they're going to get referring to this particular notebook, they want to know what they have done over here. So for that, we are giving comments. That this is displaying the data values for each variables. So this kind of comments are always recommended. You can go ahead and give this kind of variables, some kind of comments. Okay. All right. So now let's talk about string concatenation. What is the spelling of concatenation? Let me check. It's string concatenation, right? I am very bad with spellings, but yeah, coming back to this thing. Now let's see if I'm having two strings. Okay, that Earth is the only planet with life. Let's say I'm going to store it in a string one variable, and I'm going to have this kind of either double quotation or a single quotation, and I'm going to store Earth is the only planet with life. Okay, and after this I'm giving another statement, string 2, or maybe not, right, something like this. So if I want to print and attach these strings together, I want to create a statement out of this. Now there are again multiple ways that you can do. A very straightforward way, would be to join them with the help of plus operator. I can have print of my string 1 plus string 2. And now if I run this, it's going to create a error, because if you can see, I have written string 2 without the underscore. Now if I give underscore and run this, now it's saying that Earth is the only planet with life with full stop, but now there is no space in between. So for that you can create one more string in between string 1 and string 2, that is the space string. This was a string, this is also a string, and this is also a string, right? And now you can see that thanks to that space, we are having the space between this first sentence and the second sentence. You could have also achieved this by having a manual space over here and then write string 1 plus string 2, and that is fine. But now let's say if I want to do it with the help of f strings, how can I do it? Very simple. I'm calling my string 1 variable and then string 2 variable with a space in between. Again, it's going to run into an error because of the underscore. So yes, that's how it's going to work. How we can do it with the help of f string, right? We will look into its power as we advance our program in order to go ahead and do astronomical visualization and analysis. But for now, this is how you can play around with the f strings. And now in the next particular video, we'll be discussing about a new concept altogether, that is how you can get an input from the user in Python. Hey everyone, welcome to the 7th video of module 1. Here you are going to understand this concept of how you can take user inputs in your code. So let's say you are writing a code and there is some kind of a problem where you need to take some kind of inputs from anyone who is running your code and save that data in some kind of variable. So for that, what is the command in Python through which you can achieve this kind of things? And by default, what is the data type of the output by using this kind of input command? We are going to learn about these things in this video. So let's get started. Now I'll just create one more text cell, give a heading as user inputs. Okay. So what we are trying to do over here, we are going to run a command in Python that is going to allow users to give some kind of input. Okay. So what's going to happen? I'm going to use a command called input, and now that input, if I'm going to run, see, it's creating this kind of a text box where you can give any kind of input that you want and store it in a particular variable if you want. Okay, for now I'm not storing it anywhere. I'm just trying to get an input. It's not going to do anything. So I'm going to stop this run. Okay, I just clicked on this. It's saying keyboard interrupt because I manually stopped it by myself. Okay, now what I'm going to do is I'm going to store it with some kind of a variable over here. Okay, for example, let's say I'm trying to ask name of the user. So I can give this kind of a variable name, username. Okay. Now, if I'm going to write this kind of input, it's going to give an empty text box. Now, if I want to give some kind of description so that users are able to understand what kind of data to give, then you can have this kind of a string information that enter your name like this. And now if I go ahead and run this code, see how beautiful it's asking for the name. Now user can simply go ahead and give, for example, my name is Rohan, so I'm going to give Rohan and press enter. And now if I look into, I'll just give a comment over here, use input to take user inputs. And just like this, I could have also come over here and check the type of variables by using type command, right? This kind of descriptive comments are always recommended. Now user name has been given as Rohan. If I want to check how it looks like if I'm trying to print this, it's simply going to take this username equal to Rohan. That's what we have done. That's all about it, right? And now what if I check about the data type? Can you go ahead and guess what kind of type is this kind of username going to have? Because it's a text data, we expect this to be a string. It's as expected that we got a string. Now what happens if I'm going to code and ask user to input their favorite number? Okay, I'm again going to give a comment to this code first of all, that is displaying the variable and its type given by the user. Now asking user to input their favorite number. So again, let's say I'm creating some kind of a variable to store this information. User fav number, something like this. And asking as an input, I am asking let give or enter your favorite number. Okay, I run this. So again, it's asking user to give their favorite number. Let's say they are giving 7 because my favorite number is 7, and I assume most of your lucky number might be 7 as well, right? I don't know why 7 is very lucky. I'll just hit enter, and now again go ahead and display the variable and its type given by the user. And now if I'm printing first of all my user fav number, it should display 7. And after this, if I'm going to print the type of this user fav number, look into the output, it's still a string. So what is happening over here? The way that we are calling this input command that is inbuilt in Python, it automatically converts any kind of data that is given by the user into a string format. It automatically converts any kind of input given by the user in that text box into the string format, even if it's a number. We just looked into that. So let's say if you want this number to be converted into some kind of a numeric format, either let's say integer or a float, what you do is you try to convert this kind of data type into integer format or a float format. How we can do this? I'll explain that in the next video. Hey guys, welcome to the 8th video of module 1, and here we are going to talk about that how you can take a particular data type and convert it to some other data type. For example, if I'm having a float, how can I convert that into string? So all these kind of data type conversions you are going to understand in this particular video. So let's get into it. So now let's go ahead and understand that how we can take this particular data type that is in the format of string, the 7, how you can convert that into a numeric data type that is either integer or a float, or maybe let's say both of them. So for that, what I'm going to do is I'm going to create a heading which says that data type conversion. You are going to learn about how you can convert any data type into some other data type if it's possible to convert, or else you will be getting an error. So the commands that you need to know, commands to convert. If you want to convert any kind of thing into a string, any kind of data, it could be a integer, it could be a float, it could be any kind of data type. Okay, we have covered only 3 of them, but let's say it could be any kind of data type. If you want to convert that into a string, the command in Python is the string. Any kind of input that you give to the string, that input, if it's possible to convert that into a string, it's going to convert it into the string. Just like that, in order to convert any kind of input into integers, you are having this command of int, integers. So any kind of input that you pass to this int within this kind of parenthesis, it's going to convert that input in the format of integers if it's possible to convert that input in that integer. For example, let's say if I'm having 3.5, if I try to convert that into an integer, it's not going to convert that 3.5 into an integer because 3.5 is in the format of float. However, there is some interesting thing that's going to happen if I'm going to run this kind of code. You will be understanding it in a while. Now, just like that, if you want to convert any kind of input into the float format, you call the float that is available in Python itself, and then you give some kind of input. That's how it works. Okay. And now I'm going to give one more comment after giving one empty line, that convert a string data into integer and float. So we know that this 7 is currently existing in the type of string. I can again cross check it by simply typing this type and user fav number. And this time I'm not writing any kind of print in top of that because in Google Colab, what happens is if I'm going to run this, the last line doesn't require print statement to print the output. Okay, but if I'm giving, let's say I'm just copying this thing and printing it again over here, it should have been printing twice for me, right? If I run this code, but it's going to print only once. Why? Because it's going to give me the print of the last statement automatically. I don't need to give print command. If I want to print both of them, I need to give print for both these lines. Okay, that's something that we need to do. Okay, but anyways, coming back to our discussion, that is, we already know that now this user field number is in the format of string, right? So now I'm doing is converting a string to integer. How? I'm passing this int and then passing in this user field number and simply running this code by pressing Ctrl Enter. And I'm also trying to print the type of the string to int and see if that thing has converted. And at the same time, I'm also going to print the string to int variable that we have created. As you can see, now the output is again 7. See how the 7 are looking just the same. It's the change in this data type. Now from the string, we have converted it officially into an integer. Now this string to integer variable is having the value of integer 7. Right? How did we do it? By just using this kind of inbuilt command in Python of integer. I gave an input to it because we know that the 7 can be written in the format of integers. We are having this kind of an data. Now what if I, let's say for example, give a string like this, and ask to convert this string into an integer? It's not a number. How will this be converted into an integer? It's not possible. You are getting this kind of a value error that, hey, I'm not able to convert the string into an integer. Invalid literal for this integer. It's not possible to convert this into an integer. So make sure that you are giving these inputs that are able to be converted into an integer. Now at the same time, now what happens if I'm giving 3.5? Now this time you might expect that it can give you an error because now it's in the format of decimals, and even 3.5 in itself is not an integer, right? So what's going to happen over here? It's not going to give you an error. Instead, it's going to round it down to the nearest integer. So if I'm having 3.5, it's converting to 3. If I'm having 3.9, it's still going to convert it to 3. So yeah, that's how this kind of integer works. So make sure if you want to have 3.9, let's say if this was in the format of string, and now if I run this time it's giving me an error because string cannot directly be converted into an integer that is having a float data within itself. So I need to convert that 3.9 first of all into float. So that this 3.9 that is existing in a string is first of all converted into a float, and now that float will be converted into an integer, and now it should work perfectly. See how that 3.9 string got converted into a float, that is 3.9, and now that 3.9, if I'm giving as an integer of this 3.9, it's converting into 3, right? So that's how it's basically working. In 3.9 the integer part is 3. That's what essentially we are getting, right? So yeah, coming back to breaking this whole thing into a step-by-step format. This was user field number. Okay, and let's say I'm also having the string to integer, or let's say, yeah, string to integer. Now integer is already done, right? We are about to change it to float. So now we are having float of user field number. Remember, this user field number is already defined over here. We haven't done any kind of changes to it. So it's still in the format of and string. Okay, it's just that this variable is now given this value that is integer of that string data. Okay, so again, if I'm first of all printing what is the type of user field number, it won't change. It will just be the same because I haven't done any kind of changes to that variable, right? That variable is still the same. Okay, it's giving me some kind of an error. It's giving me a name error that S type is not defined. Oh yeah, because I've done a type over here. See, now it's still, you can see it's this is the last print statement. It's saying that it's still a string, right? Now let's say I'm trying to convert that string into a float. How we can do it, right? I'm going to print this thing string to float and also print the type of it. See, that's how it's working. It's converting that 7 into 7.0. And now that decimal indication is saying that it's basically float type. Again, I've done some kind of a type over here. I should have not written float. I should have written string to float, right? String to float, like this. Because float is a function, right? It's not some kind of a variable. So yeah, as you can see now, it's giving you the output of float. The type of the string to float variable that we have created is a float. Now let's say if I want to get user input of two different integers and add them together. How can I do it? So what I'll do is I'll take number 1 as an input. I'll ask them to input their number. Give any integer number. Okay. And then after that, I'm going to give another variable, that is input. Give one more integer. All right. And then if I'm going to add these numbers together and print it, n1 plus n2, or else let's say we are having a very fancy way to give this kind of a statement by using f string. I'm going to say that the sum of n1 variable and n2 variable is the summation of them, that is n1 plus n2. Now remember, I am not converting this into integers, right? Because we know that by default, this input is going to expect the numbers in the format of what? Strings. So let's see if I'm running this as of now and giving, let's say 7, and another integer is, let's say my another favorite number is 9. So 7 plus 9 should be what? 13? 9, 10, 11, 12, 13, 14, 15, 16. Okay, my bad. Again, my very basic mathematics is also very wrong. But anyway, 9 plus 7, whatever is the value, okay, 9 plus 7, you can do it in Calci. It won't be 79, right? So now what's going to happen? The reason we are getting this 79 is because that this n1 and n2 is a string, and we are concatenating them, this kind of string, with the help of this plus variable. I mean plus operator. And that's the reason why the 7 and 9 are getting concatenated. We are joining the strings together with the help of that plus. Like how we did over here while before this f statement, f string, I had given you a way through which you can do it by simply converting this into this plus, and there is also no quotation marks. And if I print this, it was giving this, right? How they were joining this two kind of strings, and then we had given this kind of space and everything. So yeah, that's exactly the same thing that I'm showing you over here. Okay, this is string 2, just converting it back to what it was. And yeah, that's typically what we are going to do over here, that because it's in the format of string, it's concatenating them. Now if I want to convert this into an integer, I need to pass this int on top of this. Why? Because I'm converting the string into an integer, and I know user is going to give me an input of an integer. It's going to convert it automatically into the format of integers. And let's say my mathematics is really very weak. I'm giving the value of 7 and 9, and this value of 16 is now accurate, right? So yeah, that's how it's going to work. How you can take input from the user if it's a numeric data, and if you are sure it's going to be an integer, no other data, you directly give this input of int on top of this input that you are getting from the user. It will automatically convert it into the integers, and then you can do any kind of sorts of things you want. So yeah, that was about how you can do the data type conversions, convert one kind of data into some different type. Hey guys, welcome back once again to the first module, and here is the 9th video of it, where I am going to teach you the concept of control flow in Python. Now this is the heart of programming. If you don't know this concept, you are not a good programmer at all. Not that other concepts are not important, they are equally important, but as I mentioned, this is the heart of this programming language. So we are going to start with the looping part. Specifically, we are going to look into the for loop and while loop. Once you understand what are this kind of looping, why do we use them, how to use them, we are going to move on towards the condition statements, where we are going to understand about if statements, if else statements, and also if else statements. And again, there are a lot more things that we need to cover in this video. So let's get started. Now let's go ahead and talk about what is control flow in Python. Okay, let me define this as control flow. And the whole idea that you're going to learn over here is, I'm just going to cross check if that's the 7. Yeah, that's the 7. Okay, the whole idea you're going to learn over here is with respect to for loop and while loop, and then you're going to learn about some condition statements. Okay, and the main idea over here is that if you are having some kind of a code which is repeating, okay, and you don't want to manually type all these kind of things. For example, if I'm writing print 0, and then after that print 0, I'm also writing print 1, and then print 2, then print 3, right? I'm knowing that this kind of integers are giving, like, being printed starting from 0, then 1, 2, 3, like this. Let's say if I want to do this for 100 times for some reason, okay, this is just for an example. As we'll be going in the upcoming modules in this program, you will see the power of all of these things. Okay, right now I'm just trying to teach you that this kind of things exist. Okay, so if I want to do this kind of things, if I want to automate this kind of things, how can I do it? Because I know that there is some kind of certain kind of things which are keep on repeating itself in a specific way, I can transform this whole idea into for loops or maybe while loops. I'll be first talking about for loop. Okay, so what happens is, if I'm trying to initiate my for loop, I need to give the keyword called for. Then for what? So for some kind of index that is present in some iterator. Now what is the meaning of iterator? Iterator is nothing but some kind of a storage where you are having multiple values that one can take. Okay, that index can take. Okay, so let's say if I'm having list of numbers. So in Python, you can create a list with the help of the square brackets. Okay, again, this is not important thing to discuss as of now, but let's say that you know about this kind of list, and I'm storing, let's say, 0, 1, 2, 3, 4, this kind of values in the list. Now what's going to happen? Automatically this index is going to be like acting like a temporary variable. You can call that as a temporary variable that's going to take one by one values that is present inside this iterator. List is an iterator where you are storing multiple different values, and this index is going to take these values one by one starting from 0 in the first loop. After the first loop is over, it's starting the second loop, it's going to take the value of 1. This index will keep on changing its value starting from 0, then the next value, that is 1, then next 2, 3, 4, like that, until this kind of last value has been taken by this index. This kind of for loop will keep on running. Okay, so what I'm going to do is, I'm simply going to print index. As you can see, the first time this code ran, the index was taking the value of 0. That's why it print the value of 0. Similarly, now the first loop is over, it's entering the second loop, it took the value of index as 1. That's why it is printing me the output of 1. So that's how you can iterate through this kind of iterators, and list is just one of the example. Let's say if you want to create a list of 100 numbers, and then you want to iterate, you cannot manually go ahead and create this kind of a list of 0 to 100 or 0 to 99 for that matter, right? So the way through which you can do this is something by using range. Okay, now what is range? The way it works is, it takes the start value, it takes the ending value, and then it takes the skip value. If I show you, let's say if I'm giving first of all range of just any number 10. So it's going to give me integers that are present in between 0 to 10. That's the purpose of range. In order to prove you that, what I'm going to do is, I'm going to convert this into range of 10 and then run this. So it's going to give me the values, 10 values in between 0 to 10. So starting from 0, it goes all the way up to 9, as you can see. After 9, there is no output, because these are first 10 numbers starting from 0, and yeah, we are ending at 9. One value that is less than this. Okay, now let's, if I don't want to start from the index 0, I want my first integer that is present in the range to be, let's say, -5. So I can start with -5 because I know that I can give that kind of a syntax, start and then end. If I'm just giving one number, it's just taking the value of end at where you want to end, a value before that actually. And now if I run this, you can see that now it's starting from -5, not 0. It's going till 10. By default, the value is set to 0 for the start if you are not giving any specific input to it. Now it's going to take the value of -5. Okay, so if I change this 10 to -5 and then if I run this, okay, I did a mistake. I should have written -5 comma 10. And now if I run this, say starting from -5, -4, -3, it's going to go all the way up to 9 until that 10 is achieved. You are keep on going to iterate. Okay, so it's not like you are going to get only 10 values. No, anything in between -5 to 10, you are going to get that as an output. -5 is inclusive, 10 is exclusive. Okay, just keep that in mind. But typically, let's say we want some kind of numbers to start with 1 and then go all the way up to 10. In that case, I need to go from 1 to 11. So I hope this kind of things are making now a good sense of how to play around with this range to get your things done, right? It's now going to start from 1 to 10. Now 11 is exclusive, remember that. That's why it's getting printed to 10, right? That's the whole idea. One more thing that I can write over here is start is inclusive and end is exclusive. It simply means that the value of end is the actual value 1 before that end that we are defining. That's what range is going to take. All right. And now what is the meaning of the skip? Let's say if I want to skip, right now it's currently by default skipping 1 numbers, right? After 1 it skipped 1 value, it went to 2. 1 plus 1 is 2, right? Then 2 plus 1 is 3. If I want to have this plus 2 instead of plus 1, I can, let's say, have this comma 2. So now after printing 1, it's going to add 2 numbers to it. It's going to go to 3 directly without getting this 2 as an output. So it will be like 1, 3, 5, 7 and 9. Okay, why it stopped at 9? Because 9 plus 2 is 11. The moment I reach 11, it's not going to give that as an output, right? That's not how it works. So yeah, that's how it's going to be. After 9, because the next index value is 11, it's not going to run for that index. So yeah, that's about how you can use for loop to do some kind of specific thing. Right now, I have given a very simple logic that if you want to print some numbers between, let's say, 1 to 10, and if you want to skip 2 values starting from 1, then skip 2 values, you get to 3, skip 2 values from 3, you get to 5. That's how you do it. So that's the concept of for loop. Now, if I want to do the same thing with the help of while loop, how can I do it? I can do this by giving while keyword and then a condition. I need to provide some kind of a condition, and this kind of colon is again very important. I did not explain you over here, but this colon is very important. This colon is going to indicate that whatever you are going to write within this kind of space, okay, this space is also important, which we call as an indentation. So if I'm going to delete that space and run this, it's going to give me this indentation error. Why? It's giving me this indentation error because the space is missing. The for loop expects this kind of space so that any kind of code that is written within that space, that's going to be the part of the loop. If I'm going to print some value over here, let's say 5, and run this, see, it's at the end also printing the value of 5, but now that 5 is not printed for this many times. If I have this kind of space in between, so after every number 5 will be printed. After every number 5 will be printed. See, after 1 5 is printed, after 3 5 is printed. So that's the power of this kind of indentation. If you're going to give this indentation over here, it's going to assume that print 5 is supposed to be there within the for loop. If you don't want to have that indentation, then now it's fine. It's not going to give an error because it's having at least one line to run within the for loop. And if I skip that thing, now it's going to give an error because it needs at least something to run, right? But now let's say if you don't want to get an error like that, you can simply use pass keyword. Okay. Now this pass keyword, what it does, you can try to think and you can think about the whole logic of the loop. For that time, you can use this pass keyword, and if you try to run this, if you are thinking about some kind of logic, this pass keyword is a very good way to just don't write anything within the for loop. Right now, just initiate the for loop, go into the second part of the code, and then come back later on over here. So for that, you can use pass. Okay, but anyways, coming back to where we were, okay, I'm going to remove this thing and also remove the whole line and come on to the while loop. Okay, so in while loop, it expects some kind of a condition that you need to run this loop until this happens, until this condition occurs. Okay, and then over here also, automatically, if I keep enter, if I press enter after the colon, it gives me this kind of indentation automatically. And now over here I can give any kind of way through which I can loop into this loop, any kind of thing I want to do. Until a certain kind of condition is met, it's simply going to run. Okay, for example, let's say I am asking a user, I want to create this kind of a loop where it's asking user to enter their favorite celestial objects. Okay, and every time they are giving the inputs, I'm going to also keep a track of an, like, this index. I'll also be updating the index after every iteration, so that I am having, like, favorite celestial object 1 is this, then favorite celestial object 2 is that. So that's kind of stuff that I want to create. And after that, the condition to break this for loop is again something that I'll be giving. And that's how this while loop will be over. For the for loop, what's happening? In the for loop, we are automatically ending it once the iterators are over. Like once you're not having anything to iterate for, it will be over, right? So once you are hitting that value of 11, you are not going to have anything else to iterate. So that's about the for loop. But in the while loop, it's going to run forever if the condition is not met. So it's compulsory for us to write a condition in a way, if you want to stop your loop, that condition should be satisfying a certain kind of thing through which you can stop the loop, you can break the loop. Okay, so what I can do is I can come up with this kind of a logic that always run this thing. Okay, I'm not giving any kind of specific logic over here. I'm just saying that go ahead, run this loop forever. At the same time, I'm also having some kind of counter. Okay, I'm having some kind of index that I'm going to track that how many times this kind of iterations are happening. And now I'm also asking user to give some kind of input. Okay, let's say enter their favorite celestial body. So let's say I'm going to store this in the variable called object, that is obj, asking for the input, enter your favorite celestial object. And then I want to ask them that this is the first thing that they are inputting, right? CT plus 1, because CT by default is 0. So I'm just going to write CT plus 1 over here and then have this F string, and this is also typo, so I'll convert that into input. And now what's going to happen in the for loop? Okay, if I run this as of now, see what's happening. It's asking that enter your favorite celestial object 1. I'm going to say Earth. Now again it's saying enter your favorite celestial object 1. Why? Because we are not updating the value of the CT, and it will keep on asking me because I'm not giving any kind of condition to stop this while loop, right? So for now I'm manually stopping this over here. So let's talk about how we can update these counters. I can, once I'm done asking this kind of input from the user, I'm going to update the value of CT and say that CT is equal to the previous value plus 1. You could have also written this as like, CT plus equal to 1. It's essentially doing the same thing. It's taking the previous value of CT and adding 1 to that. Okay, so 0 plus 1 is 1. Okay, and now 1 plus 1 will be 2, right? So that's how this is going to become 1 plus 1 2, right? So it will ask enter your favorite celestial object. When the CT value will be 1, this 1 plus 1 will be 2, or by default you could have started this with 1 and like you could have removed this 1 over here, because it will start with 1 and then automatically it will be 2 in the next iteration. Whatever, it's up to you, right? How you code your specific logic. So yeah, that's what I have done. And I'm also going to give the condition that if user is going to input something that is asking to stop, that yeah, that's it, I don't have any kind of favorite celestial bodies apart from what I have given as an input. So if the object input that has been given by the user is equal to, let's say, something called quit, okay, then what I'm going to do is I am going to break the for loop. So there are multiple new things that you are learning over here, that is this if statement along with the break statement. So what's happening? So until the user is going to write quit, it's going to run this while loop, and the moment they are going to type quit, it's going to break the for loop. So this is called as condition statement, that is if condition. If this condition happens, then you're going to terminate the for loop by using this kind of break keyword. And then let's say if this is not the quit, you can continue the code, so you don't need to do anything. If this is the condition that is met, then break the loop. Okay, and I can also give this kind of a print statement over here that type quit to exit. Right, this kind of hint is something that I'm trying to write over here so that user knows how you can escape this kind of loop, when to stop. Okay, right. So now let's see what kind of things happen if I'm running this code. So see how it's coming, type quit to exit. So now let's say that favorite celestial body is, for example, Earth, then let's say black hole, this kind of inputs. Now I'm tired, I want to give quit, but now I give it like this. It's not quitting. Why? Because I give this q as capital, right? I give this q as capital. I need to write small quit, the lowercase quit, only then it will stop. So now to tackle this kind of conditions, what you can do is you can take the user input and convert it into this kind of lowercase. The way you can do it by passing this lower function that exists in Python for string. So if I want to demonstrate that, I'm going to write a comment, convert any string into lowercase. How you can do it? Let's say if I'm having a string demo is equal to uppercase or any kind of combination of letters, uppercase, just like this. Okay, now if I print this string demo, it's going to be as it is, uppercase. Now if I want to convert that into a lowercase, what I'm going to do is my string demo dot lower is what I'm going to print now. This lower is converting this any kind of uppercase is anything to a smaller case. If it's existing, it will convert into a lowercase. If it's already a lowercase, it's not going to do any kind of changes to that. So now by applying this, even if it's writing capital QUIT, even still that is fine. Okay, so if I run this, and now if I am writing Earth, black hole, right, and then QUI, let's say capital T also for that matter. See, it's still quitting. Why? Because the power of this lower functionality that is implemented to the string. There are again bunch of different methods that you can apply to a string, but because we don't have to learn everything in Python, only some specific things that you will require in order to do some kind of astronomical visualizations and analysis, then this much amount of information is quite okay for now. Okay, as we'll be going ahead, you will be learning a lot of different stuff in Python. Over here, I'm just giving you a warm-up so that you are understanding a lot of things in Python and you're not just getting confused of some basic stuffs, right? So yeah, that's about, like, we have talked about how you can have this kind of for loop, you can have while loop, then also talk about some kind of conditions like this. Let's say if this is the condition, then do this. Else if object lower equal to some different thing, let's say capital quit, then do what? Then let's say print type smaller quit, smaller or lowercase quit, or else it's not going to make any sense as of now. So what I'm going to do is I'm simply going to delete this. Okay, I'm just going to keep it as of now over here. I'm not going to complicate the things. If there will be something where you will be requiring to understand the else if condition also, or that specific time I'll be understanding you, like I'll be explaining you. Okay, for now all of these things are again quite a lot of things to understand in just video. So yeah, I'm going to end this video over here, and in the next video what we are going to learn about is functions, and I'll try to incorporate this kind of if else block over there with else if condition also, right? So stay tuned for that. Hey guys, welcome to the final video of module 1, and here I'm going to teach you the concept of function in programming. So to start with, we'll be talking about what is the need of the functions in programming, and I'm sure by the end of this program you will be appreciating that you have learned this particular concept. So we'll also learn about how you can create your own function in Python, then in order to use it, how you can call these functions. And then at the end of this video, you will also be creating a function that's going to work like a very simple basic calculator to perform some kind of addition, multiplication, subtraction, and all that kind of stuff. So let's get started with this video. Now let's understand the concept of function in Python. I'm going to create a text cell, give a heading. Now the whole concept of the functions in Python is very similar to again what we do in mathematics. If you are giving some sort of inputs to a function, now that function can take any kind of formula, right? Now if you're giving some kind of inputs to that formula, let's say you are having f of x is equal to 3x square plus 2x plus 2 something plus 3 something like this. So now if you're going to give the value of x as 2, automatically this x will be taking the value of 2, and whatever is the output of 3 into 2 square plus 2 into 2 plus 3, that will be the output of this function. Now the very similar idea is what we are following in Python also. We create this kind of functions to repeat some kind of block in Python, okay, just like what we did for the for loop or while loop. But over there you are continuously iterating one by one. But now what if you want to use same block of code in this code cell, but then after let's say 2-3 code cell again you want to use that, again after 1-2 code cells you want to use that. So for that you create functions, right? So now how do we create these functions in Python? You use this kind of keyword called def for defining the function. Then you give name to the function. Now let's say that I'm trying to create a function to greet every one of you over here who are watching this video. So def greet, I'm giving this random name that came to my mind, and then you need to give some kind of input arguments to this function. Right now I'm not giving any kind of arguments, and now again this kind of colon is given so that Python understands that yeah, now anything that is given below this kind of colon with this indentation, it's all going to be the part of the function. Let's say that I'm trying to print the value, or not the value but the string called hey astrophiles. I'm assuming most of you over here who are watching this video are astrophiles. So what I'm doing is I'm going to create this kind of function that's going to do this particular thing, okay? Hey astrophiles, I'm just trying to greet every one of you. Now how to call this function? Once you have created a function, how you are going to call them? You are creating a function to greet viewers of this video, right? And without any input arguments or parameters. You can call them as input arguments, input parameters. There are wonderful names given to the same thing over here, okay? Now I'm going to call that function. How to call that function? You call the name of the function like greet, okay? Have this parenthesis and just run this code. You're going to get an output of hey astrophiles. I don't need to write this kind of same thing again and again. Now anytime I want to call this function, it's going to print hey astrophiles for me. Isn't it just interesting? Now I'm just going to go ahead and add one more magic to this function, that I'm going to specifically greet some of you over here, okay? Let's say that one of your name just for example is, let's just not give any kind of random name, let's just take my name, okay? And let's say some of your name is also Rohan. So yeah, if Rohan, if you're watching this particular video, then I'm going to greet you specifically, okay? But yeah, coming back to the concept, what I'm trying to do over here is define a function to greet a person whose name will be given as an input. So now what I'm going to do over here is I'm going to first of all create a very similar kind of function, but this time I'm going to have this kind of a name, okay? So let's say defining a function, give a name, let's say greet person, something like this, and now it takes one input argument that is name, okay? Now this time what I'm going to print out is this hey whatever is the name. Again, because I'm using the f strings, I need to use f over here. Hey whatever is the name, I hope you are enjoying this session and learning a lot of things in Python, something like this, right? And now if I'm going to run this code to create this function, now again call that function, okay? Now how it's going to work, see that I'm going to call this greet person and give a name of, let's say, Rohan, okay? So yeah, hey Rohan, I hope you are enjoying this session and learning a lot of things in Python. Yes, I am. Okay, thank you. But yeah, anyway, moving on to the next part. So yeah, this is what I'm trying to show you, that now I can just call this function with different names. Okay, call this function with different name. Okay. Now I'm going to again call this function person, and let's say that I don't know, this name came up into my mind out of nowhere. Let's use Karan. Okay, I'm lying. He's my best friend. So yeah. Anyway, so hey Karan, I hope you're it's going to print the same thing, just that wherever now there is a name variable, it's going to replace it. Like this, you are trying to create some bunch of different formulas for function, not actually the formulas, but specific code that will be repeated with some kind of different inputs that you give to a function. So yeah, this is how this kind of functions work in Python. But now that's not all to this kind of things. Okay, now I'm feeling a bit sad that I'm not wishing all of you over here. So what I'm going to do is I'm going to call this function for one more time. Call this function to greet everyone. To greet everyone here watching the video. I can simply call this great person, but instead of just greeting one of you guys, I'm going to greet every one of you. So what I'm going to do is let's just call this as everyone. Okay. And now I'm going to run this. It says, hey everyone, I hope you are enjoying this session and learning a lot of things in Python. Now this is good, right? So yeah, that's about this thing. But yeah, now moving on to some more advanced concepts of Python that you must know, because these are very essential. You will be using a lot of inbuilt functionalities in Python and different libraries in Python in the upcoming modules. You need to know these things that I'm going to teach you right now. So please pay attention very properly over here. Okay. Now what I'm going to do is I'm going to talk about two things that are keyword arguments and the default arguments, and also the positions of the arguments. Okay. Now this concept is really very important. Default, but I should say first of all I'm going to talk about position arguments, and I'm going to talk about keyword arguments, and also about, let's just talk about these things right now so that I'm not confusing you guys with a lot of stuff. So what happens over here is that if you are giving two inputs, okay, you're not giving only one input, you're giving two inputs to the function. For example, one that is the name, and then you can give some kind of a greeting message. Okay, now you cannot just have, I hope you are enjoying this session. You can have some kind of different message also if you want. Okay, so I'm going to give this kind of functionality to my users who is going to use the function that I'm creating in Python, so that they can give any kind of message they want. Okay, this is just some examples that comes into my mind right now. So what I'm going to do is I'm going to again create a function. I'm first of all going to talk about positional arguments. Okay, I'm also deleting the keyword arguments. So if I'm greeting and I'm passing, let's say I'm creating a function called greeting, passing name and message, and then I'm saying that print a name. Okay, I'm giving this f string, print name and then message. Something like this is what I want. Okay, I want to print my name first, and then I want to print some message, or else I could literally play around with these things properly. I can say, hey, name, and then some kind of a message, something like this, right? It's up to you how you create your function. So let's say I'm creating it like this, and this time if I'm trying to call this function by placing the input arguments in the same order while building it. So I'm going to call my function that is greeting. I'm going to give a name. Again, let's say I'm going to just play around with the names. I'm going to play with, let's say, Lavanya. And then I'm writing a message, are you an astrophile? Something like this, right? And now if I run this, it's giving, hey Lavanya, are you an astrophile? This kind of question has been asked, right? And if you can see, this exclamation is also getting printed. So if I don't want that, if I'm just again calling this, okay, so yeah, this time see what's happening. I'm not getting that kind of exclamation mark. Now this time what I've done, I've placed this Lavanya in place of name. In place of message, I've put this. Now what happens if I'm going to shift? Call the function by shifting the positions of the arguments of the function, right? So I'm going to call the same function again, but now change this kind of message with name, right? And then like this. And now if I enter this, hey, are you an astrophile, comma Lavanya? See, it does not make any kind of sense, right? So that's the thing that I'm talking about, the position of the arguments. Whenever you are defining a function, you always look into what kind of way, what is the position of each and every arguments. If name argument is kept first, you always go ahead and give your this kind of name is equal to something. Okay, there is Lavanya. You don't give this kind of message over here. Whatever is the first input argument, that respective input should what go over here. Okay, because now it's thinking, Python is thinking that, hey, this is the first argument, so this should go in the place of name. So that's something that you are learning over here with respect to the position arguments. But now what happens if I'm again having the same kind of thing, but I'm specifically saying that this is my name argument and this is my message argument. Okay, now call this function with keyword arguments. So what I am doing over here is I'm giving some kind of argument keyword. Before passing just the arguments, I'm also having its respective keyword that I have used to define that argument. So this is called keyword arguments. Okay, that now even though the position I have changed, but now because I'm giving a specific keyword, now Python understands that this should go for the message argument and this should go for the name argument, and therefore you are getting this as an output. I hope these things are making sense to you. Okay, now one more thing that you can study in functions that is very common is default arguments. That is, while creating this kind of a function, okay, while creating this kind of a function, let's say greeting with default argument, something like this is what I'm defining the name of the function. And now what I'm saying is, if someone is not giving any kind of name, or if they are not giving any kind of message, by default what kind of message they should be seeing? Welcome to this program on astronomy visualization, something like this, right? Visualization, something like this is what I want to give them a message, and I want to print hey name and then the message. Okay, now what's going to happen? Always remember, your keyword arguments that you will be giving will always come later on. First the position arguments will come. If you are having mixture of keyword arguments with the position arguments, always remember, whenever you will be calling a function, you first need to pass in the position arguments because the order matters over there, and at the end you can change this kind of keyword arguments order. That's fine at the end of the function. What I'm trying to say over here is that first of all I'm going to call this function without passing message argument and see what happens. So greeting with default arguments, and now I'm giving the name of, let's say, Rohan. I'm coming back to, because I'm not in the mood to think about new name, you can say that. And now if I'm running this, see, it's giving me an error. The reason it's giving me an error is because I haven't run this code, right? It's giving me that this thing is not defined only. So how are you running this? And now if I'm running this, you can say that, hey Rohan, welcome to this program on astronomy visualization, right? It by default took this argument, whatever was written over here, and it gave me over here. Now what would happen if I'm giving my message variable first and then giving my name? Okay, I'm saying message equal to WhatsApp, something like that. Okay, and then now see what's going to happen. In the first position there should be name. Okay, but in place of that name you are already giving this message variable, message keyword. Now this keyword is already taking this kind of value. Now in the second position there should be a message. Now that is already existing over here. That's why you're getting this kind of red line, and obviously you're going to run into an error. Position for arguments follows keyword argument. So always write your position arguments first and then the keyword arguments. Okay. So over here I could have written this as like, a name, that is Rohan, and then the message. This is fine. Just write explain, right? Even while defining the functions, if you are having this message first and then the name like this, see what happens. It's going to throw an error. Non-default argument follows the default argument, just like in the keyword and the position. If you are not having any kind of default values, you always keep them first. Okay, that's something that you must know while creating your own functions. Okay, now all of these things that you have learned over here is going to be pretty much very useful whenever you will be implementing these ideas in the upcoming modules that you will be learning. Okay, but now one last thing that I want to describe over here is I'm going to create a function that will either add, subtract, multiply, or divide two input numbers. Okay, so I'm going to come up with a very basic calculator with the help of functions. Okay, and I'm going to show you that how you can do all these kind of things. Create a function that will either add, it's not whether, it's either add, subtract, multiply, or divide on any two numbers that has been given as an input. Okay, so let's say I'm creating a function called basic calculator. Okay, and now I'm giving some kind of inputs of two numbers, that is number 1, number 2, and then what kind of operation I want to have. For example, let's just call that as an operation: add, multiply, subtract, or divide, something like that. Okay, I'm trying to demonstrate that if, else if, and else kind of statements. Okay, so now let's say if operation dot, again I'm using this kind of lower functionality, so that if anyone is also giving capital ADD, even that's going to find in order to compare. So if the user input is add, I want to return something. Now this is again a new thing we are learning in functions. It's not always about printing, right? If you want to give something as an output, just like in the mathematical function, if you're giving some input, it's going to give you some kind of specific output. It's going to return some outputs. So you can get something out of this calculator or the function that you are creating by calling a keyword called return. Anything that you write after return will be the output of the function when you call this whole function with some input arguments. Okay, you will understand this in a while. So let's say I want to return. What do I want to return? I want to return n1 plus n2. Whatever is the output of this n1 plus n2 is what I want to return. Now if I run this code and test this, basic calc, giving my first number as 2, second number as 3, and then operation is add, and then run this. See, the output is 5. How did I get this output 5? Because I'm returning this value. I can store this value in a variable now. I can store this in, say, addition, something like this, and then also print this, and I can use this kind of addition somewhere else in the code, right? Addition. So yeah, that's the first thing that we have done. Now the second thing that we are going to do is we are going to say that if, else if operation dot lower is to subtract, okay, then return what? Return n1 minus n2. Just like that, else if operation dot lower is to multiply, then what you do? Return n1. Asterisk symbol is used for multiplication. And then else if operation dot lower is to divide, then you are going to return what? n1 divided by n2, right? Else, if anything else is given as an input apart from add, subtract, multiply, or divide, you are going to say that print, I'm going to create my f statement with f string. You can either in your operation input can either take add, multiply, subtract, or divide. You gave whatever was the the operation that has been given by the user. You give this, try again. This kind of message is what I'm trying to print. Okay. And now if I run this code, see how it's working. If this is the condition, then do this. Else if this is condition, then do this. Else if this is the condition, do that. Else if this is the condition, do this. And if it's nothing like that, then do this. That's the proper if and else block that we have created over here. Okay. So now if I run this, it's giving me 5 as an output, right? Now let's say if I want to do some kind of multiplication, and I'm storing it in the multiply, something like that, right? Now I'm going to create this kind of basic calc function and give this kind of thing that first number is 3, the second number is 3, and then multiply. Okay. And print the value of multiply also. Print multiply. 3 times 3 is 9. We expect the output of 9, right? You can go ahead and test for all of these things. Okay, what happens if I'm trying some random input? And I'm not going to store it. I'm just going to try to see what's the output that we are able to fetch. 3, 3 and some random thing. Okay. And then if I run this, it's going to give operation. Input can either take add, multiply, subtract, or divide. You give this, try again, right? So this is the thing that is giving output. I can shift this to capital O, and I can also give some kind of information over here with the help of multiple strings over here. I can say that parameters. I can first of all give the kind of an idea of what this kind of function is doing. This is a really very good way of documenting your functions. Okay, I'm describing what this kind of code is doing. Okay, this function is doing. Creates a basic calculator that takes n1 and n2 in the same order and performs either of addition, subtraction, multiplication, multiply, and divide. They can perform either of this, right? And then you can give parameters, and then you can have this kind of parameters that n1 first number, then n2 is your second number. Like this, you can just give all the kind of proper information. And then operation is any of the operations mentioned above for our basic calculator, that is add, subtract, multiply, or divide. And then it's going to also return what? It's going to return what is it going to return? It's going to return, let's check what is it returning. Yeah, either the output of the calc, the output of the operation done n1 and n2. So you can also give an example over here if you want, but yeah, that's pretty much about how you can describe a function, so that if someone else is going to use your function, they already know how to give some kind of inputs while calling your own function that you have created, right? So yeah, that's about the functions that you should know. And over here, these are some kind of pretty much things that you should know. If you know about all of these things, you are now having enough ideas to advance yourself into Python and learn a lot of beautiful things in terms of how you can create different visualizations in astronomy by using some new things itself. But at the same time, now you're aware about a lot of things in Python. That's for sure not going to make you think like of a lot of overwhelming stuff going on. Okay. So yeah, make sure that you are going through all the kind of quiz questions that we have given, just to ensure that you are now having a proper idea about all of these concepts that we have taught before you advance to module 2. Hi everyone, welcome to the second module. I hope that by now from the module 1, your concepts of basics of Python are clear, because all of those concepts will be now implemented in module 2. That will be helping us to convert a tabular data of real stars out there in universe and create some amazing visualizations out of it and do some observations, get some observations out of it, do some kind of analysis, and then whatever kind of visualizations we will be creating, we'll also be saving it into our system. So all of these kind of things we'll be doing in this particular module. And specifically what type of graphs we are going to generate from this tabular data of stars. We are going to generate the bar graphs. We are going to generate the box plot. We are going to create the line plot. Also the pair plot, and finally at the end of this particular module, you will also be creating an HR diagram. Now this HR diagram, if you're not aware about it, it's completely fine, because by the end of this video, you will be knowing this everything, and you will also be coding for the same thing. Okay, it's one of the most amazing things that you will be seeing whenever you are dealing with the star data. Okay, so let's get started with this particular module. Hey everyone, welcome to the second video of module 2. And here I'm going to give you a quick sneak peek on the dataset that you will be using throughout this particular module. So this is basically about some real stars out there in universe. And yep, without spoiling any of your excitement, let's get into the video. Let's go ahead and try to understand what kind of astronomical data that we are using in order to create some of our first visualizations in this program with respect to that astronomical data. And then not only that, how you can take this kind of visualizations that you are going to create in Google Colab and save it into your system, so that later on, whenever you are doing your research work, in order to give support to whatever kind of work that you are writing in your research, to support that work, you can always add this kind of visualizations, right? So how you can extract this kind of visualizations from Google Colab into your system, and then obviously you can attach this kind of visualizations into your research paper or maybe report or whatever kind of research work that you might be doing. So all of these things will be covered in this particular module, and specifically the data that we're going to deal with is stored in the format of the CSV file in this particular Google Drive link. So we're going to directly export this data from the Google Drive into this Google Colab, and then we are going to explore this kind of data set step by step and then create these visualizations. That's the whole idea. The main goal is to create some kind of different visualizations from the data set, and the data set is all about different stars that are existing out there in space. And then all of the stars are given with its respective properties of absolute magnitude, then surface temperature, spectral type, and also the luminosity. And at the end, we are also going to create this kind of a Hertzsprung-Russell diagram, or in short, you can also call it as a HR diagram, which helps astronomer classify any kind of a star based on its properties of this absolute magnitude, spectral type, surface temperature, and the luminosity. So that's the whole kind of idea that we're going to deal with throughout this particular module. And I'll see you next in the upcoming video, where we are going to deal with exploring of this data set. Hello everyone. Welcome to the third video of module 2. And here we are going to go ahead and import the libraries. So what kind of libraries are we going to import, or what kind of libraries are we going to use throughout this module 2? You're going to understand each one of them, as in why are we importing them. And then yes, as you can see on the screen, find out what are these kind of libraries and why are we going to use them. So let's get into it. Now, in order to explore this kind of data set that we are having in the format of CSV that is stored in the Google Drive, and also create visualizations on top of that, what we'll be doing is we won't be coding everything from scratch. We are going to use some of the existing libraries that's going to help us so that we can save over time, and at the same time use this kind of libraries to create some kind of beautiful visualizations after exploring them. So for that, I'll have to import these libraries, which will help us throughout in this particular module. So what I'm going to do is I'm going to go ahead and import the libraries that are going to first of all help us explore the data set in a proper way. So I can do this with two of the libraries, that is import OS. Okay, how exactly it will be helping, you will get to know in the upcoming videos. But yeah, OS is one of the library that is going to help us to, let's say for example, create a directory where we are going to save all of our visualizations, and also it's going to be useful for some other purposes that we'll be seeing. Apart from that, if you want to open the CSV file and explore it step by step, the main popular library that we're going to use is Pandas. So I'm going to import Pandas as PD. The reason I'm calling it as PD over here, so that because I don't want to write Pandas again and again, okay, I just want to use PD in short, so that I don't have to write Pandas again and again continuously, right? It's up to you. You can just simply import Pandas and use all the functionality of Pandas library by calling it as Pandas, not PD. It's your choice. Okay. I can also import Pandas as, let's say for example, my name is Rohan. So I can also import this thing as import Pandas as Rohan. But now it does not make sense, right? It's almost pretty much same letters that we are having. So a short form that we use in the Python community for pandas is PD. Just like that, you will also maybe needing some kind of a way through which you can create an array from this kind of a CSV file. Okay, so from the CSV file, you want to generate some sort of array. For that, you will require a library called as NumPy. So I'm going to import NumPy library as NP. So now I have imported all of these libraries that are going to help us explore the data set. Now, in order to visualize this kind of data, you will require visualization libraries. So for that, what kind of things I'll importing? I'll be importing the first thing, that is Seaborn. Again, because there are a lot of characters in this particular word, I'm going to import it as SNS. Again, a short form that we use in Python community for Seaborn. And then we are also having one of the most popular libraries for visualization, that is Matplotlib. So I'm going to import Matplotlib and specifically PyPlot, and I'm going to import it as PLT. Again, a short form to call all of these things together, right? So these are the libraries that we are going to use majorly to create some kind of different visualizations after exploring it with the help of OS, Pandas, and NumPy. So that's the whole idea. And now from the next video, we are going to go ahead, call the data from that link, and finally start exploring it. Hey everyone, welcome to the fourth video of module 2. And now that you are already having a quick idea of what is the dataset all about, let us try to explore this dataset with the help of Python. We are going to convert the CSV data into Pandas data frame with the help of Pandas library, and then summarize this whole information that we are able to fetch from this particular data frame about the stars. So let's get started. Now what we are going to do is we are going to take that CSV data. I'm going to simply copy this link and use this particular link or path to the CSV file, read that CSV file with the help of Pandas library, and create a Pandas data frame. So what does this mean? So I'm going to use Pandas functionality. So I'm using PD and then dot to refer to any kind of functionality that is present in Pandas. And now because I want to read the CSV file, I'm going to write this command read_CSV. And then it expects this path in the format of string to that CSV file. So I'm going to simply give this kind of a quotation mark and paste that link. Now you don't have to download this particular data from this link and then upload it somewhere to basically read the CSV file. This link is shareable for everyone. So you simply go ahead, copy that link, paste it over here and simply press Ctrl Enter to run this code. And you will be seeing that the whole data of that CSV file is now expressed into this kind of a table that is your Pandas data frame. Now, how do I know that this is a Pandas data frame? So whatever code that we have written and whatever it is generating for us, I can always check its type by simply writing the type and whatever command that I'm getting over here. If I'm running this, and you can see that we are getting this Pandas data frame, right? So what I'm going to do is I'm going to store this Pandas data frame into some of the variables so that we don't have to again and again read the CSV file. So I'm going to store it in a variable called, let's say, star_tf. What it means, it's a data frame which is having the information of stars, right? So you can name it the way you want. This is what I have chosen. Okay. Now let's say if you want to visualize top 3 rows of this data, how you can do it? You call that data frame that you have created, and then on top of that, what kind of functionality you can use? You can use the functionality of head. This head automatically gives you, if you don't put any kind of input over here, it gives you first 5 rows of data that is present in your CSV file. Now let's say if I want to visualize top 3, I can just give this 3, and yeah, you can get this kind of 3 first values that is present in our CSV file. As you can see, there are some different properties of the stars, and there are some different respective stars that we are having over here. So 0 is a star that is present on our first particular row. Then the second star is present on index 1, so on and so forth, right? So that's the kind of idea that we are having. Now, what if I want to visualize some 10 random samples of the stars that are present in this data? So for that, we use some different functionality of the data frame, that is sample. This sample allows you to get some random samples from this data frame by simply passing in the number. For example, let's say I want to visualize 10 different samples from this data frame. As you can see that now on the left side, the index values are completely different. It's not starting from 0, 1, 2, 3 like that. It's some random index. So it is indicating that we are trying to display some random 10 data points that are present in the CSV file, right? And each and every star is having the properties with respect to its temperature, luminosity, radius, absolute magnitude of that star. What is the star type? If you can see, the star type is given in the format of some numerical data. There is some kind of a reason behind that. I'll be explaining it to you in a while. And then there is also a star color and a spectral class. This is the kind of data that we are having, right? And all of this kind of stars are having this kind of properties. And by using these properties, we are going to create some of the visualizations that we'll be seeing throughout this module, right? Now, let's say this is the overall data that we have seen, right? Now, if you want to get, let's say, a generic information from this data frame, then how you can do it? You can do it with the help of, you again call the data frame whose generic information you are trying to look for. To get it some of its functionality, you press this dot, and the functionality that we are looking forward to is the information of that data frame, and that command is .info. You don't need to give any kind of inputs over here. You simply run this, and you are going to get an overall general information that is stored for this particular data frame. It is giving you that there are a total of 240 different stars that are present in your data frame, whose index are starting from 0 and goes all the way up to 239. Okay. And then there are some different 7 columns for each and every row that is present in our data. And what is the name of these columns? We can also find that over here, that my first column that is present on my index 0 is temperature, as you can see over here. That's my first column on index 0. This is a index 1, index 2, index 3, 4, 5, and 6. In total, there are a total of 7 different columns like that. And respective name of the column has been given over here. And then there are also information with respect to non-null count, what it means. If there are any kind of data point in this whole data frame which is missing, for example, if this was missing, then what would happen? In a radius, there is one missing value. So over here in radius, you would have got 239 non-null. Out of 240, there are 239 data points which are not missing, which are not null, but there is one point which is missing. So this kind of non-null count column is giving you an idea with respect to how many data points are missing. As you can see that out of 240, all of these 240 are non-null. It means every data is complete. Now the reason the data is complete like this, in real life you don't get this kind of complete data. You have to perform some of the techniques called as feature engineering, handling the missing values and all this kind of things, so that you can use this model for a proper analysis. That's the whole idea, and that's again one of the reason why we have converted the star type into numerical type, because at the end this data was used to create some of the machine learning models. But now, because that's not part of this particular program, we are not going to talk about that. I'm simply going to tell you that, let's say 0 means, let's say, some kind of a dwarf star, 5 means some kind of a supergiant star. All this kind of information I'll be giving you at the end of this particular video. But yeah, just know that all of this file that you are seeing right now, it wasn't like this from the beginning. It was made perfect so that we can perform this kind of visualizations on top of this kind of given data, right? Because our aim is not to handle this kind of missing values, do some kind of feature engineering and create some kind of machine learning models. Our job is to take the data set which is complete and then create visualizations on top of that. That's the whole idea of this particular program, right? So let's focus on that particular part. So now we are having 240 non-null contents for every columns that is existing. Along with that, we are also having that for each and every column, what is the data type in which this information has been stored. So overall summary is present over here, that out of 7 columns, 3 are of float type, which means there are some kind of decimals involved over here. Then there are 2 columns with integer type, and then there are 2 object type. Object type, you can call it as, like, some kind of a text data that is present over there. Something like that is what you can assume as of now in a very, layman language. And the total memory consumption for this kind of data is 13.2 plus KB. So yeah, that's also giving you the kind of idea with respect to the memory that has been used to store this particular data frame. So as you can notice, for the temperature, all of these values are in the format of integers. But now if you talk about luminosity, it's having this kind of decimals which are involved, right? And now that's why it's also given this luminosity in the format of float. Don't worry about this kind of numbers, okay? These numbers are basically giving you the precision of the way of writing that particular number. So let's not go into this kind of technical details as of now, right? Let's focus on this kind of, this is a float type, this is also a float type. This is again a float type because again some kind of numbers with this decimals. But then star type is integers, and then star color and spectral class are both having some kind of text data. So now again that are appearing over here in the format of the object data type of this pandas data. So here that's an overall observation that we are able to make by importing this data from this particular Google Drive to Google Colab, looking into some of its random samples, and then also getting some kind of generic information on top of that. If you want to look into its overall observation, here is I have written in a complete detail. Okay, there are 240 rows with 6 independent features and 1 dependent feature, that is the target column. Again, this is mentioned with respect to, let's say, a machine learning data set, that you are trying to classify the star type based on other 6 properties. Okay, so that's the kind of idea about this data set. But again, we are not going to do any kind of machine learning thing over here. We are simply going to create visualizations. Okay, and here are all the kind of information about the columns, right? This is the target class, the star type, right? But anyways, you don't need to get into that particular information. And what is the meaning of LO and RO? That is L0 and R0. These are the average values of luminosity of the sun and radius of the sun. So all this information that you are seeing with respect to the luminosity and radius, now that is with comparison to the sun, that compared to sun, what is the luminosity of this star? Compared to the radius of sun, what is the radius of this particular star? So it gives you some kind of a comparison directly that, okay, yeah, this star is less luminous as compared to our own sun, and also its radius is small as compared to our own sun. So yeah, that's the kind of idea that we are having. Apart from that, yes, there are star color and spectral class, which are categorical features, which means it's in the format of some kind of categories. There are some kind of different categories of colors. There are some different categories of spectral class, right? So this is the kind of data that we are having over here. And then this is what I was trying to look after, right? This is something that I was trying to look after. That this information about the star type, the integers that were mentioned, right? Originally, it was having some kind of a name to it. 0 stands for brown dwarf. 1 stands for red dwarf. 2 stands for white dwarf. 3 is standing for the main sequence. 4 is for supergiants, and 5 is for hypergiants. Now we are going to create some kind of visualization at the end of this module that is going to display this whole information of the stars into an HR diagram. And finally, we'll be able to classify it like this: hypergiants, supergiants, white dwarfs, right? Red dwarfs. This kind of thing is what we are going to expect at the end of this module. This is one final visualization that we are going to create. So yeah, that was the idea with respect to exploring this kind of a data set so far. After this, what we are going to do is, in order to create a visualization and then save it somewhere, we are going to create a directory in the next video. So stay tuned. Hey everyone, welcome back once again to the module 2. And in this video, we are going to understand that where exactly are we going to save the visualizations that we'll be creating in the upcoming videos of module 2. So for that, you're going to understand that how you can create a directory in Python, and then how you can get the path of the directory so that we can use it in order to save all the kind of beautiful visualizations that we'll be creating in some of the upcoming videos. So let's understand how we can create a directory and get a path of it in this particular video. Let's get into it. Now, before we go ahead and create any kind of visualizations, we need to save it somewhere. So for that, I'm going to create one directory, or you can call it as a directory or a folder, whatever you want. So for that, I'm going to first of all give the name to that folder. So let me create a variable called as folder name that I might change maybe later on in future. So yeah, I'm just giving it as a folder name over here as star plots. You can give whatever name you want over here. And then I'm also going to create a folder now of this particular name. Right now, I've just created a variable. I haven't created any kind of folder. Now, how can I create that folder over here? Now, if I show you over here, this is what is called as the session storage space of the Google Colab, where by default, this kind of sample data exists for every notebook. Okay, so we haven't created anything from our side. It is already existing. If you will check, it will be existing for you as well. Now, my job is to create one more folder whose name is star plots. And the way that I can do this is I'll just come to the next line, and write OS, because that's the library that we have imported in our previous one of the previous videos. And I'm going to use a specific functionality of this OS that's going to help me create a directory, and that is called as make directories. Make dirs is the command, and now it expects two of these inputs. The first input is the name of the folder, so I'm going to give this as a folder name. At the same time, it expects us to give exist OK, and we are going to set this to true. What it means? It means that if this kind of folder already exists in your space, then it's not going to recreate the folder or something like that. If it's existing, it's not going to do any kind of changes. If it's not existing, as of now we don't have this kind of file, then it's automatically going to create a directory for us. Now if I run this code, now the code has run successfully, and if I refresh this part, you can see this directory has been created for us. Now the main idea is, to whatever kind of visualizations that you will be creating, you need to create a path that will store it within this particular location. So for that, what I need to do is I need to simply get the path of this folder. I can do this by clicking on this three dots over here and click on copy path, and I can create a base directory path over here, which simply means that any kind of visualizations that you are creating, you will be storing in this base directory. And now I'm going to equate this to the string of this path, and now I'll just make this path dynamic, just in case we are having some different folder name in future. If I want to change, I don't have to change this base directory path. I'm going to use f-string for that. That's what we had learned in our first module, right? So I'm going to write folder name over here instead of star plots, right? So I just can change the name of the folder if I want, and automatically this will be changing, right? So that's the whole idea. And after this, there is one more slash I need to give. It means that if I am concatenating this particular path with any kind of files that we are generating of visualizations, I'll be simply concatenating it on top of this base directory. So in order to connect them, we need a slash. Just like how you can see there is a slash over here, right? Whatever session storage you are seeing of Colab over here is referred to this kind of content that you are seeing. Then inside this space, you are having this specific folder that you are trying to extract over here. And that's why, because this folder is existing in this space, you are giving this slash over here. And now then you are giving this kind of star plots. And then to store any kind of data within this directory, right? Then you are giving this kind of a slash again. And now once you will concatenate with, let's say, example.png, some file that you have created. So you just need to concatenate this name of the file that you have created and attach it with the base directory. That's it. And your path of that new visualizations that you will be creating will be stored over here, and the image will be generated over here, right? So that's the whole idea that we are having, as in why we are having this base directory over here. Okay, if it's not making any kind of sense as of now, don't worry. As you will be going ahead in this particular module, you will be getting a lot of ideas with respect to what is the need of this particular base directory. All right. Now in the next video, we are going to go ahead and visualize the count of stars for each type of star. Like, we are having varieties of star. So we are going to visualize what are the different counts, in what quantity are this kind of stars present, right? So stay tuned for that. I'll see you in the next video. Hey guys, welcome to the 6th video of module 2, and here you are going to create your first visualization for this data on stars. So you're going to create your bar graph, and it will be very basic visualization that we'll be having with the help of Matplotlib library. And in the upcoming videos, you are also going to customize it and look at just amazing. Okay, so for now, let's create at least the basic version of the bar graph that's going to give us some of the information about the data set. So let's get into it. Now let's go ahead and create our first visualization, that is in order to see that out of 240 stars that are available in our dataset, how many of them belong to brown dwarf, how many of them belongs to red dwarf, so on and so forth, for all the kind of different categories that are present in our star type column. Okay, so what you will have to do is, first of all, you will have to fetch this kind of a count with the help of Pandas data frame. And then you can, on top of that, use this functionality of Matplotlib in order to visualize it. So what we are doing, first of all, I'm just going to copy the name of this column so that we can extract all of this data that is present within this column of the data frame. And how I can do it? I can come back to that particular code cell over here and I can simply type star df to access the data frame. And now to access any specific column of the data frame, you need to pass in this square brackets. And then I paste the name of that particular column, but now in the format of strings. Okay. And now if I just run this, over here you can see that there are different star types of category 0 all the way up to 5, right? As you can see over here, 0 stands for brown dwarf, 5 stands for hypergiants, and everything within that is going to be stored into this particular column. Now, if I want to get this kind of a count, that how many zeros are present, how many ones are present, so on and so forth, I have a particular command for that that exists in the pandas data frame. I need to go and type value underscore counts with this parenthesis. So what's happening? It's giving us all this kind of counts that there are 40 zeros that are present, or I should say 40 brown dwarfs present, then 40 red dwarfs present. Similarly, like that, all of this count are, as you can see, is 40, 40, 40. So out of 240 stars in total, 40 of them are for each and every category that you are seeing over here. 40 main sequence stars, supergiant stars, all of this are having 40, 40 type of count of stars out of 240. So now if you want to visualize this kind of a data in, let's say, format of bar plot or bar chart, whatever you want to call, what you can do is you can simply come over here and use this functionality of plot over here on top of whatever you have got, and then give this kind of input as what kind of plot you want. Do you want a bar plot? So you give this kind of input as kind and set it to bar, that hey, go ahead, take this kind of data, that's what you can see, and create a bar plot out of it. And now in order to visualize this, I can simply have plt.show. I'm using the Matplotlib functionality to display the graph that I will be creating over here. Okay. And now if I can run this code, you can see that this is the output that we have got. Okay, it's a very plain output. We haven't customized it. That means the goal of the next video. That is like, we're going to customize the above plot and then finally save it. Right now, this is the very basic graph that I have created, that is indicating that, okay, now for different categories, here are the respective counts that you can see. It's a perfectly balanced data for us. And yeah, now in the next video, you will be seeing how we can customize this plot and make it look very, very beautiful as compared to what you are seeing right now. Hi students, welcome to the 7th video of module 2. Here, we are going to take the graph that we have created in our previous video. We are going to customize it. We are going to make it look much more beautiful as compared to what it was in our previous video. And then once we are satisfied with the output, we are also going to save it in that directory that we had created earlier in the 5th video of this module. So let's get started. Alright guys, so get ready to see the whole different magic. We are going to take this kind of basic default looking graph and beautify it by using this kind of customizations that I have written down. I'm going to take this basic graph and convert it into something really very beautiful. Okay, so let's go ahead and try to do it together. So first of all, I'll need this kind of basic graph on top of which we are going to build everything. So I'm just going to copy paste this code and run this. So yeah, here we are having the same kind of graph. The first thing that I'm going to do is I'm going to adjust the size of the figure according to my convenience. Okay, so let's say some of you might like a bigger size of this figure. I would personally go for a smaller size. So how can I adjust the size of this figure? I can do this with the help of a plt command. And what kind of command I need to use? I need to use the command called figure. Now this is going to give me the axis of this whole figure on which we are having this axis on which we are having this graph. Okay, so we are having one whole figure. In that figure, there is one axis, that this kind of square that we are seeing. And now on that axis, we are drawing this bar graph. So what I am doing is I'm trying to get the access to this figure. And now inside this figure, there is an option called as figure size, that is fig size, F-I-G-S-I-Z-E. Now over here, you can give how much amount of width and height you want to give to this particular graph or plot, whatever you want to call. Let's say I'm changing this to 5,5 and see how it looks like. So yeah, that's the kind of output that I'm having. I guess I would still like to decrease some of the size. Let's say I'm doing something like 4.3, 4.3. Hopefully this is fine this time. Yeah, this is looking a much more better. Okay, for some of you, you might like a very huge graph, you might try to increase the figure size in that case. But I guess for me, it's convenient for me to use this particular figure size. So we are done with the first customization. We are trying to adjust the figure size that's suitable to me, right? We are done with this part. Now the second part is to add the value of the counts on top of the bars. It simply means that for each and every category, okay, at times what can happen, that some of the bar, the count is less, let's say somewhere in between 20 to 25. Now if I want my readers to exactly know the count for this particular bar, so we can add the count on top of this kind of bar, and that's exactly what I'm going to do. In this particular case, it could be like, our users or our readers might be confused that, like, if this bar is exactly at 40 or 39 or 41, whatever it is, right? So this kind of skills is necessary for you to have, that whenever you are drawing a bar chart, if you want to show this label on top of this bar, you can, what you can do is, first of all, see, we were having this kind of figure. Inside figure, we are having this axis on which we are drawing this bar graph, right? So I'm going to label this axis because I want to use some of the properties of this axis, and that is, I want to set bar labels. I can do it with this command ax.bar label. What I'm doing on this axis where I'm drawing this kind of bar graph, I'm getting its property called bar label, and now there is something which we give an input called containers. Containers. What is the spelling? Containers, right? And now I'm going to access the values of each and every bar by using the 0 index. And now if I run this code, see, now we are having this kind of 40 count, right? It will be really very useful the moment, let's say, any kind of bar count is like, somewhere it's at 40, somewhere it is 35ish, 30ish, somewhere in between. It's going to be very much useful. Also, you will be seeing this in the second visualization that we'll be creating, where the level of bars are not equal. Okay, but yeah, that's how you basically do this particular thing. After this, let's say I also want to change the color of this. I'm not satisfied with this kind of black color. I can simply change the color by giving the input argument of bar label as color and set it to, let's say, for example, red. See, now it's much more better, right? We decreased the size of the figure, then we took the axis on which we were having the bar graph, we took the labels of each and every bar with the help of ax.container0 and simply displayed it with the help of this functionality of this axis, that is bar underscore label. So that's what we have done so far. The next thing is to set the background to dark. Now it's again your choice. Okay, if you think you like darker backgrounds, then you go for the darker backgrounds, or else you can stay with this kind of lighter versions also, whatever is suiting you the best, right? I personally like the darker background. So what I'm going to do is, I'm going to use this plt.style.use. Okay, this is the command through which you can set a particular background. There are again multiple backgrounds that you can choose. The one that I'm going to choose is called dark underscore background. Okay, and now if I run this, okay, there is some kind of an error. The error is saying that dark backgrounds is not available. I guess I've done some kind of a typo. It should be dark background, and see, now this is the output. Now it's looking something weird, right? I cannot see the axis mark. What I can do is I can simply run it again, because that's the, this kind of issue is there with Google Colab, that if you are changing the style, okay, then you will have to run it twice. So yeah, that's how it's looking like right now. Automatically this color of this axis has changed from black to white. That's the property of dark underscore background, right? Now if I want to change this to default, I can also use this kind of default style, and maybe I'll have to run it twice to make it look better. See, I'll have to run it twice. So hopefully we're getting back from where we started. See, yeah, that's how it's looking like, right? So what I'm going to do is, I'm personally a fan of dark background, so I'll be changing this to dark background. Now at the same time, what I'll be doing is, I'll also be changing the color of each and every bar. So right now it's a plain cyan kind of looking bar, right? I'm going to change each and every color for this bar. Okay, for this what I can do is, I can simply come onto this particular graph and give one more input. Instead of just having just kind is equal to bar, I give color property, and now I just don't have only one bar to change the color. For example, if I change this to, let's say, brown. See what happens. It's changing all of them to brown, right? I don't want this. I want to create a list for each and every color that I'll be giving to these bars. So let's say I'm choosing, let's say brown, red, white, right? All these kind of colors are coming into my mind. What I'm going to do is I'm going to create a list. Okay, I'm going to store all of these colors in the format of list. Let's say first is brown, right? Then the second one is red. Then I'm giving white. You can choose these colors the way you want. Then let's say yellow. Then some kind of different colors that's existing in the matplotlib.py plot. Let's say there is light blue, and maybe the last one I would choose as orange. Okay, so I guess we are done. 1 2 3 4 5 6. 1 2 3 4 5 6. So yeah, I guess this should work. Let's see. Yeah, see, now we are having multiple colors in the bars, right? Brown, red, white, yellow, light blue, and orange. So yeah, that's how you can change the colors of each and every bar, right? I hope this is making sense to you. Now after this, let's say I want to describe that what is this plot giving us, like, what kind of title we want to add to this plot. So for this, what I can do is I can give this command plt.title and set any kind of title that I want. For example, I can give, let's say, visualize star count per star type, right? Visualize star count per star type. And also I can give a color to it. For, let's say, by default, what is the color that we get? So this is the kind of output that we're getting. We can also set this whole font to, let's say, bold. Okay, I can also change the color of it. Let's try to do this kind of things. You can also change the font size. You can try to decrease the size, increase the size, whatever suits you the best. Let's say the first input that I'm giving is the color, and I'm choosing the color as royal blue. Okay, how do I know this kind of things exist? How do I know this dark background exists? How do I know this kind of colors exist, right? Because I've gone through the documentation of each and every command. You can simply go to its official documentation by searching on Google. I can simply copy this command, go to Google and search for it official documentation, and you can get all this kind of things. Or nowadays you're also having access to chat GPTs, right? So you go to chat GPT and ask for what kind of different styles I can use in this plt.style.use. It's going to give you multiple different suggestions. Right? So I'm going to set this color to royal blue. I'm also going to change the weight of this font to bold. And I guess font size is looking good to me. I'm going to run this. I guess this is looking pretty much good, right? So yeah, we are done by setting a title. Now I'm also going to add a Y label and also change the color of this Y ticks. This kind of things are called Y ticks. This is called as X ticks. So first of all, what I'm going to do is I'm going to add my Y label. I'm going to do this with the help of plt.ylabel and give some kind of name, like, whatever this is describing. For example, let's say number of stars, count of stars, right? I can give a hashtag for that is representing number of something. So number of stars, right? And I'm also going to set a color to this. Let's say I am choosing a color called pink. Okay, let's see how the output looks like. See, this is the kind of pink color that I've got, but now the font size is pretty much small. I want to increase the font size. How I can do this? I can give the input parameter called font size itself. That's the name of the parameter, and change this parameter size to, let's say, 13. Let's see how it looks like. I guess this is better, but now it's like, even much more as compared to this. So maybe I would like to decrease to 11 and see how it looks like. I guess, yeah, this is better. This is much more better. Now, how I can take this white text and change its color to, let's say, some different kind of pink. Let's say tab pink. This is the color that I want. Okay, so let's go ahead and try to do this. I can get access to this white text by again using PLT and use white text. Okay. Now I'm going to set color parameter to this as, let's say, tabular pink. Again, tab pink is one of the color that is available in Matplotlib. So I guess, yeah, this is looking much more good, right? Obviously, you can play with this kind of colors the way you want. I guess I am comfortable with what I'm having right now. Maybe I can try to change this color to, let's say, white, not pink. Obviously, you take this thing, change it the way you want. Yeah, I guess, yeah, this is much more good. Great. Now, one more thing that I would like to do is, I would like to replace all the X ticks from 0, 1, 2, 3, 4, 5 to its respective names that are shown over here. So what I'm going to do is, I'm going to simply copy these things and come over here and paste it. Put it over here. And then this is in the same order that I want to write. So I'm just going to delete this part. I don't want this kind of part. Okay, and I also want to arrange this into a proper kind of way through which I can change the X ticks. All the 0, 1, 2, 3, 4, 5 that we are having over here, right? 0, 1, 2, 3, 4, 5. I want this to be changed to the labels that I want in place of the 0 to 1 to 5. Okay, so what I can do is, because I want to change this X ticks, I can give this plt.xticks. And now what kind of things I want to change? So these are called the ticks that are present inside xticks. So I can give it as a part of list. It is 0 to 5, right? So 0, 1, 2, 3, 4 and 5. Now I want to replace this ticks with the labels. Okay, the first input is ticks, the second input is labels, right? And now I'm going to give again a list of all of these things that we have written over here. Okay, let's say brown dwarf is the first thing. I'm going to give it in the format of string, and then I'm going to do it for red dwarf, after that we are having white dwarf, and then main sequence, after that we are having super giants and hyper giants, and hyper giants. Okay, so I guess this is good. Let me just try to run this and see. Okay, I guess we have to delete this. We don't need that thing anymore. And now if I run this, hopefully it's changing. Yeah, see, now this is what I am getting. Brown dwarf, red dwarf, but I don't want this kind of things. Okay, I want to rotate these things, let's say some degrees, and I also want brown to be in the first line, dwarf to be in the second line, red to be in the first line, white dwarf, dwarf in the second line, like that, right? So what I can do is I can give a new line character between this brown and dwarf, similarly for red and dwarf, right? Similarly for this main sequence, and then there is only one word, so I don't need to convert them. But now what I can do is I can just bring this down so that it's visible to everyone. And then I'm going to give one more parameter called rotation. I can give, let's say, 10 degrees of rotation. Let's see how it looks like. It's a bit cluttered, right? So what I can do is I can maybe try to rotate it to, let's say, 45 degrees or something. Let's see how it looks like, right? After changing this to 45. I guess 45 is going to look good. Yeah, this is looking much better, right? I guess, yeah, this is much more better. Now let's say I want to change the color of this as well. I can again give the property of color to this xticks and change this color to, let's say, maybe lime. Let's see how it looks like. This is looking good, right? So yeah, that's what we are having. That's what we are going to get by replacing the ticks of x from 0 to 5 and giving it its respective label, that is brown dwarf, red dwarf, white dwarf, so on and so forth. So yeah, that's what we have done over here. And after this, we are going to save this particular plot in the base directory that we had created. I want to store it within this thing. So now how can I do this? Right? I guess the plot that we have created is far more beautiful as compared to what we had seen over here. Right? I can maybe try to again change this to super in the first line, then giants in the second line. I could have done that, but I guess this is fine. Now, in order to save this thing, what I can do is I can simply come over here and give this command plt.savefig. Now, what is this thing going to do? It's going to allow us to give the path where I want to save this figure. So the first thing is I want to give the base directory, right? The base directory is the directory that we have created for the star underscore plots. Now, if you remember this base directory, wherever we have created, we have given this slash. So I just need to concatenate the name that I want to give to this plot. Let's say we are giving this name. In order to concatenate, we can use the plus operator. And then let's say give this as bar plot star count, something like that. Bar plot star count dot png. You can also save it as JPEG if you want. But yeah, let me just go ahead and try to do this. And hopefully we are getting this output over here. If I, yeah, see, that's there. If I double click on this, over here we can see that this is the kind of output that we have got, right? Now I'm simply going to close it and close this also. And yeah, we are done with this first plot. Okay, this is the first plot that we have saved. After creating it, after beautifying it, that's what we have done. Now in the second upcoming video, what I'll be doing is, I'll be creating one more visualization. It would be a bar graph only, but with the help of Seaborn. And now see that with the help of Seaborn, how we can do the same kind of stuff. And that is much more convenient as compared to using Matplotlib. All of this reasoning will be getting clear once you look into the second video or the upcoming video. Hey everyone, welcome to the 8th video of module 2. And here we are going to visualize some different part of the data set, again in the format of a bar graph, but we'll be creating it with the help of Seaborn library. And you are going to see that how easier it is in order to create some amazing bar graph with the help of Seaborn as compared to Matplotlib. So let's get started. Now what we are going to do is we are going to go to the top part to that data frame that we had created and take a look onto the star color. We are again going to create a bar graph, but now with the help of Seaborn. You will see the power of Seaborn that with just one line of code, you are able to achieve something like this colorful different bars and all of this kind of things. You will see that. So now what I'm doing is, first of all, I'm trying to visualize the star color count that is present for each and every color. So for this, what I'll have to do, I'll have to go to star df. Inside that star df, there is a column called a star color. I should give it with the help of strings. And then I can check the value counts with this. So as you can see that there are red stars, the count is 116. For blue, it's 56. For blue white, it's 41. By default, it's coming into the descending format, starting from the highest and going till the lowest. And now if I want to get access to these values, this red, blue and all these kind of things. Now this is present in the position of index. So I can take this command. On top of this command, I want to grab its index. So I'm going to give this command dot index. So here is the whole index, red, blue, blue, white and all of these things. So now what I want to do is on the x-axis, I want to plot these colors that are this index. And on the y-axis, I want to get this particular values. Okay, if I grab the first value that is present over here, it will be 116. So it's 116. Now if I want to grab the value present on the first index, it will be the second value, 56, right? So I want to plot this data on my y-axis and I want to plot this colors on the x-axis. So what I can do is, I can use sns.barplot. I'm trying to create a bar plot with the help of Seaborn library. On the x value, I am giving this whole thing with index.index. That's the color name. And on y, what I want to see the value counts. So I'm going to copy this part. Okay, I'm going to copy this much part and save it in y. Okay, let's just try to run this and see how the output looks like. See, this is the kind of output. If I don't want to have this kind of extra labeling that is there on top of the graph, I'll have to use the command plt.show. I'm trying to use both Matplotlib and Seaborn to come up with one final output. So by using this plt.show, this axis will be going away. So yeah, this is the kind of graph that we are having. See, now again we can have any more customization. See, by default, it's not coming out as a white background right now because we have already changed it. Once you change it, it will be like this. Okay, it will not going back to white color. You will have to go and switch this style.use to default in order to have this kind of white background. But I guess black background is quite comfortable. But now you can see that I don't even have to set this kind of colors manually. It's coming automatically without myself doing anything over here. Now what I can do is I can just come over here and give one more thing that is called palette. I hope I have given the correct spelling. Again, there are multiple palettes that are available. This Viridis is my favorite one. So this is looking much more beautiful, right? So yeah, that's about it. Now I can again go ahead and customize it the way I want, right? I can change this uh, color for this y-axis. I can change these colors of the text and everything. I can do this, right? So what I'll be doing is I'll simply be going ahead and doing this kind of visualizations. Okay, I guess the figure size is looking pretty much good. I'll be changing the text of the x-axis, plt.x text. Give a rotation, I guess, of 15 degrees or 10 degrees. 15, I guess. Let's try 15. And I'll give the color as orange and see how it's looking like. This is good. Now what about star color? I'm going to take the y labels. It's coming by default. I didn't even give this thing. It's coming by default. It's all because Seaborn is built on top of Matplotlib. By default, within this bar plot, they are giving this kind of y label that is the title of the column. That's what they're giving by default. I didn't even set it. But if I want to change its color, I can use plt dot, let's say, y label and give some kind of color. Let's say white. Can also change the font size to, let's say, 13. Let's see how it looks like. It's giving me some kind of an error. Y label. Okay, y label is missing some kind of an argument. Okay, maybe we are trying to, oh yeah, we are missing the y label. We'll need to give this kind of command, that is star color. Okay, we'll have to give this. If you want to change this y label, you will have to give this kind of name, only then it will be working fine. So yeah, now it's working fine, right? So yeah, I've given this kind of things. I can also change the colors of the y text if I want. plt.y text. This color is equal to tab pink. This is my favorite one for the y-axis. That's what I use frequently. So yeah, I can also have the title of this plot that we are visualizing. plt.title. We try to basically give title on the top because we know, like, this is the kind of order. First we draw the plot. After drawing the plot, we give the title. This kind of order is not something that you need to follow. TITL. Right? Now visualizing the count of star colors. Something like this. Maybe color is equal to royal blue. For title, again, I prefer this if I'm having the dark background. And font size, let's say I'm setting it to 15. 2 more than what I am having for this. I can also set this to weight equal to bold. I can also, for the X text, I can try to change the font size if I'm able to do this. I can take this, right, font size, change this to, let's say, 11. Hopefully it changes. Yeah, it's changing, right? So I guess this is pretty much great. Now I can also add, like, this kind of containers to this bar. And the same way I'll be changing this to AX because I'm trying to get axis of the axis, right? And then I'll be doing AX dot bar label and then AX dot containers 0, and then maybe I can give a color of red. And I can also maybe change the weight of this thing to bold and see how it's looking like. First of all, the main thing I really wanted to show you is that by doing this just one line of code, it's giving us the Y label, it's giving us everything, even different colors of the bar with the help of palette, right? So all of this kind of things, we are doing it in just one line. So that's the power of, like, using Seaborn. It's built on top of Matplotlib, so it's just easy to customize it the way you want. As you can see that star color was already existing even before giving this Y label. But now if I want to change some of its property, I can do it because Seaborn is built on top of Matplotlib. So yeah, that's about, like, how you can visualize a different kind of bar plots. And now in the next video, let's try to visualize something else. Hey everyone, Welcome to the ninth video of Module 2, where you will be visualizing the outliers present in our dataset. And one of the ways through which we can do this is by creating the box plot on all of these kind of features that we are having in the dataset. And we are going to visualize them side by side with the help of a subplot. So what is subplot and everything will be covered in this particular video. So let's get into it. Now let's go ahead and try to create some different type of visualization apart from the bar plot. Now what we are going to do is called box plot. Now it's typically used to visualize the outliers that might be present in any of your numerical feature. So the main idea behind box plots is that you are going to have this kind of variation of numeric feature in front of you. It's going to give you the idea of the median. It's going to give you the idea of the upper quartile, lower quartile, and also the outliers, right? And for the outliers visualization, we typically use the box plots. And finally, just save it into this particular folder that we have created. And I guess we did not save this particular code. So let's go ahead and try to save this figure. Save fig. And the name that I'm going to give you, not give you, but yeah, give this particular graph is base directory plus, let's say, visualize or just star colors viz.png. Let's go ahead and also try to cross check if it is done. Yeah, it's done. I'm going to see it. So yeah, that's the beautiful plot that we have created and saved, right? Anyways, yeah, we are also going to save this kind of box plots that we'll be generating. All right, so that's the whole idea that we are going to look into. So now what I have done is I've already created one this kind of get a gist of data by checking the first 5 rows of the data. So over here we can see that temperature, luminosity, radius, and absolute magnitude are what? Are your numeric features. All of the last 3 features are your categorical feature. It's some kind of categories. Now we use box plots to visualize this kind of numeric features. So now what I am going to do is, with respect to all the star type, that is 0 to 5, for all the star types, what is the variation of temperature? What is the median? What is the interquartile range? What is the outlier, if at all they are present in any of the star type category with respect to the temperature? I am also going to do this for luminosity, radius, and absolute magnitude. So I am going to create multiple plots for all these numeric features with respect to star type. You can also do this for star colors and also the spectral class. It's your choice. Right now, I'm going to show you any one visualization and I'm going to do it with respect to the star type. That if let's say my star type is white dwarf. So with respect to white dwarf, what is the variation of data for radius? What is the variation of data for luminosity? This is the kind of thing that I'm going to generate. So what I'm going to do, I'm going to come over here and get this box plot with the help of sns.boxplot. It requires what you want to display on x-axis, what you want to display on y-axis. And lastly, I'll be also showing this pld.show. And on x, what I want to show is the star type, right? And on the y-axis, let's say I'm giving, for example, only one thing as of now, that is temperature. So sns.boxplot on x, what am I giving? Star df, star type. And on y, what I want is star df. It is temperature, right? I'm just going to copy the whole thing, but a better way would be to not copy this. Instead, use .ilog feature. It's giving you the location on the basis of index. Now it takes 2 things in the input, the rows and the column. I want to plot all the rows and the first column that is present in the star df. Okay, all the rows of the first column. Now first column is present on index 0, right? So I can get its use with the help of this 0. Okay, remember this kind of column that we have given over here. That column is giving you this idea that everything that is present in rows, you grab that part, but now only for index 0 column. So now if I go ahead and visualize this, let's see what kind of output do we get. See, this is the kind of output that has been generated. I have got 0, 1, 2, 3, 4, 5, all the different star types which are corresponding to this kind of names. And now if you see, there are no much of outliers except this 0, right? This kind of diamond, this diamond is basically highlighting the presence of outlier for the class 0, and if we are talking with respect to only one numeric feature, that is temperature. Now what I want to do is I want to generate the same thing. Now in place of 0, I can change this to 1 and see the output. The output this time is for luminosity. See, I don't have to change the column name by default by manually. Don't have to do this thing. Okay, it's happening automatically. But now instead of plotting this one by one, I want to plot it all together in one figure and then save it. And that's where this kind of concept of box plot comes into the picture, right? So what we are trying to do over here is, this is one whole figure. Now from that one figure, we are creating 6 different axes. How we are creating the 6 different axes? By giving the command of plt.subplot, providing the values of rows and columns. I am giving 2 different rows and 3 different columns. And then the first axis over here is starting from position 1. The second axis is on position 2. The third axis is on position 3, so on and so forth. So that's how you can create the subplot and try to visualize this thing over here. So what I can do over here is, I can do plt.subplot and give one, let's say I want to create 4 different graphs in one row. So 1, 4, and I want to first of all look into my position 1, and then I want to see how the output looks like. Let's see how it's looking like. See, this is on the first position. Now if I'm just trying to change this to 0 and copy this whole code, come down over here and just change this to 1. And but at the same time, I'll also have to change the position of this to 2. See, now I'm having this kind of plot, but it's very much cluttered, right? So I'll have to manage the figure size accordingly, and I'll also do some kind of one more command that you will see of Matplotlib to adjust the layout that we are seeing right now. If it's getting cluttered like this, then we know how to do this. I'll be showing you that. Okay, but the whole idea is, I want to create this kind of subplots. But now just imagine if there are multiple subplots that I want to create, it's not a very good thing to like manually change this kind of indexes. So what I'm going to do is, I'm going to create a for loop over here. So what I'm going to do, I'm going to create for loop. But how am I going to create the for loop, right? That's something important that we want to understand. So in this for loop, I am going to create 4 different axes on index 1, 2, 3 and 4, or I should say on position 1, 2, 3 and 4. So for I in range of 4, so it's going to go from 0, 1, 2 and 3, right? And now I want to also give indentation over here. Okay, I'll remove this plt.show command as of now. Okay, and now I want to change the position with respect to I, because I is starting from index 0. I'll add 1 to it so that we get 0 plus 1 is 1, because we know that subplot always starts from position 1, not from position 0. So that's the reason I've done this kind of thing. And now at the same time, I'll also change this to I. It's going to take the 0th column first, then the first column, then the second index column, and then the third index column. So that's how I'm going to create my subplots. Let's see how it's going to look like. See, that's how it's going to look like as of now, right? I also like to change the background. It's not, black is not looking good for this one. So what I'll do is, I'll first of all change this style to default, and you must do it twice to get a proper output. Okay, this is for the first time that we have got this. This is for the second time, and I guess this will be, this time it's good. It's still cluttered because we did not change the figure size. So plt.figure, what kind of command we give? We give fig size, right? Fig size. And let's say I'm choosing 20 by 8. 20 by 8. So I'm going to get 20 spread and 8 in terms of height. So I guess now this is better, right? This is much more better. So we are getting this for temperature. Over here we are getting for luminosity, but still there are some kind of cluttering. That's what I can see. So to adjust this cluttering, what I can do is, I can maybe see, first of all, get rid of this Y label completely, and instead of that I can have a title for each and every plot. Okay, I'll be removing this kind of things and have a title on top of that. That's the kind of thing I want to do. So what I will do is, I'll say plt.y label and convert it to nothing. And at the same time, I'm going to set title. And what is the title? Title is the column name. So how do I get access to the column name? So for this, there is one simple code, that is star df dot columns. That's it. If I run this, see, I am getting access to each and every columns, right? So now what I'm going to do is I'm going to go and call these columns one by one with the help of iteration, index I. So plt dot title star df dot columns, and then I'm going to give an index. I'm also going to set a color to red, and now see how it looks like. See, now it's better, right? I cannot see any kind of cluttering anymore. If you want, you can also expand this by, let's say, changing this 20 to 25, right? Even that's fine. But I guess this is much more better, right? But now what is this indicating? If I want to give a title on top of this whole subplot that I have done, I have created, I can use something called as subtitle. See, SUP, I can again get its access with the help of PLT. See, this is what is called subtitle. Now, what kind of title am I giving? I'm going to say that visualizing outliers in numeric features of star data. So visualizing the outliers, that's what I'm doing. In what? In numeric features of star type. Now after this, what I want to do? I want to give color to this, I want to give weight to this, and also font size to it. So I'll be giving color equals to, let's say, a black color. Let's say a black color is going to work well. If not, I'll be changing this. I'll also try to change the font size, not the font size, but weight to bold. And lastly, I'll be also playing with the font size as 15. Hopefully it works perfectly fine. Yeah, this is good, right? Maybe I can change this to some different color, but I guess this white and black combination looks good. It's pretty much simple and straightforward. I guess I'll be going with this, right? Again, if you want to add any kind of different kind of visualizations according to you, you can surely go ahead and try to change anything you want, okay? But I guess this is fine for me. So I'll be simply going ahead and save this figure, plt.savefig, and say that this is boxplot.png, and also give this box plot with respect to star type. And now run this, and hopefully we'll be getting this saved over here. I'll refresh this. Okay, yeah, I'll refresh this. Okay, see, it's coming out of this particular directory. Why? Because I did not give the base directory, right? It's going by default on the session storage. I don't want to do that. So I'll delete this file, come back over here and give base directory, and then concatenate it with this thing. And I guess now it will be working fine. So this kind of things will happen with you also if you are coding. It's just that you need to minimize any kind of error that you might be seeing and get the things done the way you want, right? And now let's go ahead and visualize the box plots that we have created, just in order to check everything is fine. See, yeah, that's the kind of output that we are getting, right? So yeah, that's what we have got for the box plots. And yeah, that's pretty much about this particular video. Now in the next video, what we are going to do is we are going to look into one more type of graph called as line graph or line chart. So I'll see you in that particular video. So far we have seen how we can create a bar graph and also the box plot. Now let's look into some different type of visualization, which is called as line plot. So it basically takes some of the data points in your data and simply connects them with a line. Okay, so it's going to be helpful for us in order to visualize some of the patterns that are present in all the kind of numeric features that we are having in our data set. So let's get into the video and understand how we can get these things done. Alright, so now let's assume that we want to create the line plots for each and every numeric feature. So what we are trying to do is, in the outlier, what we did with respect to star type, what's the distribution of the temperature, luminosity, radius, and absolute magnitude. We got this kind of median values for each and every classes, and also the interquartile range and all of this kind of outliers that we wanted to spot. Right, you can surely now go ahead and remove this kind of outliers if you want, but our purpose is just to create some visualizations and find some observations on top of that. So from this box plot, we can say that in the luminosity, we are having most of the outliers. So you need to try to remove these outliers, or try to do something through which you can minimize the effects of outliers. Right? But now what I am trying to do with the help of my line plot is to connect, let's say for temperature only. Okay, we are not talking about anything else. Let's just focus on temperature. I want to connect my this point with this point, then this point with this point with a line, and then see, try to observe if any kind of pattern is being formed or not. That's the kind of logic that I want to build. Now again, I want to do this for all the kind of data that we are having that is in numeric type. So for this numeric features, I want to create this line plots. Again, I will be using a for loop with the help of subplot. But now at the same time, I'll also be showing you that how you can use function in order for anyone who is reading your code, or even for that matter, if you are reading your code after some time, it's much more readable and more convenient to your eyes. Okay, it's better that we use a function. All of this you will be understanding over here. So let's get started with this. So what I'm trying to do over here is I'm trying to create a simple line plot. I can do this with respect to plt.plot. Okay, next thing is pair plot. We are going to do that in the next video, but right now let's focus on this. plt.plot. Now what do I want to plot? Let's say for example, I want to plot the temperature. So star df, and now I can give the dot ilog. I want all the rows that is present in the first column, that is my temperature column, and simply plot it. Let's see what kind of output do we get. Also I can do plt.show so that we are not getting this kind of outputs. I can hide those outputs by using plt.show. Alright, so yeah, let's just wait for a while. This is the kind of output. See, this is the kind of pattern that we're getting. Okay. Now it depends on some kind of task. Our job is to create visualizations and give some observations. Then how, let's say in data science, in machine learning, how can people use this kind of observations and create something out of it, create some kind of automation stuff with respect to machine learning, deep learning, any kind of data science project for that matter, right? So this is the kind of pattern that we want to get for each and every numeric column, temperature, radius, and all of those, right? So what I'm going to do is I'm again going to take the help of subplot, and now this time what I'll be doing, I'll be having 4 different rows and 1 column. So 4,1, and I'll also be changing the index with the help of I. I'll be again having this kind of for loop for I in range of 4. So it's going to go from 0 to 3. I'll also select this thing and press tab to give this kind of indentation over there. And yeah, we have given an indent. We are having the space. Everything looks good. I need to change this 0 to I. I guess everything is going to be fine. I need to remove this plt.show. I'll bring out of this for loop and see how it looks like. Okay, this is the kind of thing it's looking like as of now. I can also change this kind of colors for every graph. I can give a title to this and I can customize it the way I want. But a very basic graph I have in front of me, right? So I can give this kind of plt.title the same way that we had done in our previous code, that is star df dot columns, and then I, and I can also give a color to this kind of title, let's say red, and at the same time I can also adjust the figure size, plt.figure. What kind of figure size do I want? Let's try fig size is equal to 15,8. Let's say what happens. So I guess this is good, right? In terms of visualization, this is looking good. But now if I want to do one more magic over here with the help of subplot, what I can do is I want to adjust the layout that I'm having. I can use plt.tight layout. And then if I try to look it, hopefully it's going to give us a better layout as compared to what we are having currently. Okay. It's automatically going to adjust the spaces between this kind of axis that we have drawn. And that's how it's looking. Now at the same time, I also want to change the colors of each and every plot that we are seeing. So for that, what I can do is I can create a list of colors over here. Okay, let's say colors equals to, now let's say because I'm having 4 different plots to draw, I want to understand that what kind of colors I can use. Now again, you need to have this kind of idea with respect to what kind of colors that Matplotlib is giving you. I'll be using again some of my favorite colors like royal blue, gold, cyan, green, something like that. Okay, you can choose your own colors. Royal blue, let's say gold. Then again, green is not something that I like. I like lime. Okay, so lime and cyan is something that I'll be having. Lime and cyan. I could have also drawn magenta, not cyan. Anything that you like. I'm just trying to give you some different kind of colors that are available. Now, in place of this plot, I'm going to give this kind of parameter of color is equal to colors of I. So what it's going to do? In every time, in every iteration, the value of I is going to start from 0 and all the way up to 3. So when there is some kind of an error, automatic saving failed, don't worry, click on this show diff and click on save changes, and it's going to automatically save everything for you the way it should be. All right, yeah, great. So now what this is doing, it's trying to get access of the royal blue when the value of I is 0. It's going to get the access of gold when the value of I is 1. Similarly, lime when I is 2 and 3 when magenta when the I is value 3. Okay, so that's the kind of thing that I want. And now if I try to see how it works, let's see, hopefully everything is good. Okay, it's giving me an error. What's the error? Magenta. Okay, there is a wrong spelling. Hopefully this is the correct spelling. Yeah. See now how beautiful this plot is looking like. Right, I can also give a subtitle if I want. I can give it anywhere. Okay, it's not compulsory I give it on the top. I could give it anywhere. plt.subtitle, visualizing the distribution of numeric features. Something like this. Let's say I'm giving a color of black, the same thing that we did above. Okay, I like this kind of black and white combination. If I'm choosing that, then font size is, let's say, 15. And let's say if I want to give anything else after running this code. Yeah, I also change this to bold, right? The weight of this text to bold. Weight is equal to bold. Maybe I can also try to increase the font size if I want. Okay, I guess this is looking pretty much cool. Maybe I can try to decrease this 15 to 12. Maybe that can be giving us a better visualization. So yeah, this is much more better, right? So yeah, this is the kind of output that we have received. This is the kind of pattern that we are having line by line for the temperature, luminosity, radius, and absolute magnitude. Now it's job of machine learning engineers and data analysts that, like, they find something useful from this and get something done for any kind of application they're trying to build. Right now in this program, we are trying to focus how to develop this kind of visualizations. And yeah, that's all about this particular thing. But now let's say I want to convert this whole thing into what? I want to convert this thing into a function. Now, how can I do this? How can I convert this in the format of functions? I can simply cut this thing, come up over here. Let's say I'm defining a function called line subplot. It's going to take some kind of inputs and I'm going to paste everything over there. Okay. See, first of all, I am giving this I. So I'm going to give I. At the same time, I'm also giving my star df, right? So I'm going to give star df also as an input. I'm also giving colors as input. So let's say that I'm giving colors over here as input. I guess all of this is going to work fine. So I've defined a function that's going to give me a subplot. It's going to give me a plot for different values of I from the I log. Also give me a title, and I guess everything is going to look good. So over here, I'm going to simply call line subplot and give the input of star df. Then what was it? Colors and I, the value of I, right? And hopefully we are getting the same output. I guess there is some kind of a spelling mistake. Subplot. Yeah, now if I'm running this, I hope everything is working the way we had got in the previous step. Yes, it's just the same, right? Let's say if you want to have some kind of a gap between these two things, how you can do it? You can do that with the help of, let's say, a new line character over here. Okay. And yeah, see, now you're having a good amount of gap between that. So this is the kind of thing that you have done in this video. Now I'll see you in the next video and we'll be creating some kind of pair plots. Hi guys, welcome to this video of module 2 where I'm going to teach you the concept of pair plot and how you can easily create that with the help of Seaborn library. So let's get into it. Alright guys, now what we are going to do is we are going to learn about one more visualization and understand what kind of information we can fetch out of that kind of visualization, and again save it like what we have been doing for the above plots. I guess I have again forgotten to save this. Anyway, I'll be doing it very quickly. I'll be giving base directory and the name. Let's call it as line subplot.png. Okay. And it's always our duty, guys, that we go ahead and always cross check the output over here. Okay. If I just open this, at times it might be that it's looking very good over here, but it's not looking good over here. So you need to cross check before extracting all this kind of information. All right. So this looks good. And again, once again, if I'm just trying to open this, see it properly. Actually, this is looking just incredible. Okay. To be very honest, this is the kind of power of Python. By writing only this few lines of code. Okay. This few lines of code, you have created some beautiful things, right? With the help of just few lines of code. And now one more thing that I want you guys to pay attention to is that I am not giving any kind of comments as of now because I am explaining you these things while coding along, right? So what I want you to do is different person will be able to comment a particular code in a different way. So what I am going to do is I'm going to provide a code that is this whole notebook with the proper comments, but I want you to go ahead and comment it by yourself on the basis of your understanding. What do you understand by this particular line? What was the purpose of creating this kind of function? One person can simply go ahead and write that it's improving the readability of the code, so it's better that we convert this whole kind of step into a function. Like we did not do this for the previous step over here. We did not change it like this, right? Now you can also go ahead and try to convert this into a function, right? It's going to improve the readability of this code. But all of that things is up to you. And even for this function, you can give a very good description with the help of multi-line comments. Give the information about what this kind of function is doing. Then give the information with respect to the input arguments and what is it going to return at the end. So all these kind of things you can mention in this multiple line comments, right? So yeah, that's how we are using all the kind of things that we have learned in our first module and implementing it over here. Isn't it just amazing? Yeah, anyway, coming now back to pair plot, let's try to understand what is it all about. Okay, so what is the main purpose of creating a pair plot, or was it what it's going to do? Let's say that I'm going to take temperature, for example. What it's going to do? Pair plot. It's going to take a temperature column and it's going to compare with all the respective other axes. That with respect to temperature, how luminosity is varying. With respect to temperature, how radius is varying. And all the other columns that we are having. Okay, for that matter, how temperature is varying with temperature. Even that kind of data we'll be getting with the help of pair plot. And by default, you are going to get this kind of relation in the form of scatter plot. You are just going to get dot, 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 dot. If you want, you can also create a line plot. But by default, pair plot is going to be in the format of scatter plot. Okay, all of this information I have written over here. And now, because you are seeing that there are a lot of kind of combinations that we are creating, right? Temperature with all the kind of other columns including itself, the luminosity with all the other columns itself. So there are multiple subplot that we'll have to get, right? Multiple axes in a subplot. Now a good thing about pair plot of Seaborn is that it's going to get you rid of all this kind of pain of creating subplot and all this kind of functions and this kind of things. That's the power of using Seaborn. It's going to do it by default for us, and we are just going to enjoy the output that we are getting. But at the same time, it's also having some of the drawback. And the drawback is that if there are a lot of columns, just imagine the type of combinations that you will be getting, and then you will be creating it into a subplot, right? And then you will be getting the plots. It would be a really time consuming task. But thankfully for our data, we are just having 7 columns. It's still going to take some significant amount of time, but not as compared to how it will take for, let's say, 30 columns, 20 columns, right? So that's one thing you need to keep in mind. So now let's first of all go ahead and try to visualize the pair plot with the help of Seaborn. pair plot is something I want. Now I just need to give the whole data frame because it's going to take each and every column and do everything by itself. Okay, let's see the output that we're going to get, and I'm also going to show this thing. Let's see what kind of thing do we get. Okay, as you can see itself right now, it's taking a lot of time to create this plot, right? Because still there are 7 different columns and it's taking all these kind of possible combinations. Okay, so this is the kind of output that we are getting. The temperature column is getting compared with its same temperature thing. Then temperature thing is also getting compared with luminosity. Then just like that, temperature is also getting compared with the radius, absolute magnitude, and star type. Okay, all of this numeric column. Okay, it won't be taking this kind of categorical column, which is of the type object. It's just going to take the numeric type of data, that is either integer or float. Okay, it's not going to take into account of this last 2 columns that we were having in the object type. Okay, so yeah, this is the kind of correlations that we are able to fetch. That let's say with respect to temperature, let's say what is this particular column? This is absolute magnitude, right? So for this, you can see that we can clearly see that as absolute magnitude will increase, the temperature is going to fall. This is some kind of observation that we are able to make, right? So yeah, this is the kind of output that we get with the help of pair plot. Now, one more thing that I can do is I can visualize this data point with respect to, let's say, some kind of hue. What it means, this kind of parameter that I can give over here in subplot. Let's say I just need to give the name of column over here, spectral class. Okay. What it's going to do, there are again multiple categories within the spectral class. So where is each and every category going to belong to this kind of pair plot? All of this kind of things you will be able to see. You can go ahead and create this kind of pair plot with respect to different kind of hues present in the data. See, now that's what I was talking about. There is a class M, class B, class A, this kind of data. And see, all of these kind of points are being marked differently. Wherever there is purple, it's with respect to class O. Wherever there you can see the dark yellowish kind of thing, that's class B. So that's the power of hue. You can change this kind of hue with any kind of different categorical data that you are having. Okay, and maybe star color is something that you would like to go ahead and look forward to. So yeah, that's what we are seeing, right? In the same data, because we did not count, let's say, spectral class over here, we are giving that kind of data with the help of hue parameter. That's the power of Seaborn. Now again, what I'm trying to see over here is I'm trying to change this whole background plt.style.use to dark background, and then see how the output is looking like. And maybe I would like to also see the previous graph, if how this would look like in a dark output. Okay, and I'll also change this color to, let's say, some different kind of thing. But right now, let's say how the output is going to look like. That's the output that we are having. I can maybe run this one for one more time, because right, while changing the style, we need to run our code twice. And what I'll do is I'll also go ahead and run this code. I don't need to again set the background to dark because it's already set for me right now. Okay, I don't need to change it again to dark background. So yeah, I guess this is the thing that we have saved. I'll again cross check it by saving it. Okay, I haven't saved it, so plt.savefig. What am I going to do? I'm going to save it in base directory, and the same thing, right? The name of this plot will be what? It will be pairplot.png, right? Now there is a parameter over here in pairplot again called kind. Okay, this kind by default is set to scatter. As you can see over here, it's highlighted. You can change this to the different kind of plot that you would like to see. Okay, scatter is fine for me, so I guess I'll just keep it as it is. I won't be changing, but yeah, that's something I wanted to show you guys. But now let's just go ahead and save this figure and then also look into the output if it's done in a proper way or not. All right, guys. So yeah, these are this kind of beautiful visualizations that you are creating with the help of Python. That's literally something that you can go ahead, fetch it out from this Google Colab and attach into your research papers or reports that you are creating. You can mention about this kind of details, your observations, and give evidence to that with the help of this kind of visualizations that you have created, right? So yeah, we are done with this. let's look into this thing. Yeah, pair plot is created. Hopefully there are no errors. It's looking good, right? It's looking beautiful. Yeah, you can see this kind of plots, right? For the same columns, like for example, radius versus radius is giving this kind of thing, right? Luminosity versus luminosity is giving this kind of thing. Similarly, like over here, star type and star type. So yeah, for the middle part, that's the type of output that you're getting, and everywhere else you are getting the scatter plot. This is really very beautiful, to be honest. So yeah, that's about the pair plot, and I'll also go ahead and try to run this once, or I should say twice. I'm not sure. Let's go ahead and check. I guess this is looking even much more better, right, as compared to previous white one. And I also change the color of this to white, or let's say tab pink. Let's see how it's looking now. Hopefully better. Yes, it's just amazing, just amazing. Great. So I'll also go ahead and cross check this one, line plot, line subplot, and see if the changes have been saved. Yes, this is much more better, man. This is just amazing. So yeah, now I'll be seeing you in the next video where we are going to create this kind of a plot called HR diagram. Okay, something like this. So yeah, stay tuned for that. Hey everyone. So welcome to one of the most lengthiest video you will see in this entire program. So in this particular module, this is the final ultimate visualization that you are creating with respect to this star data that we are dealing with. So this is about creating an HR diagram. What is HR diagram? I'll be talking about that in this particular video. But then how you can create this with the data set that you are having and compare it with the actual HR diagrams so that you are able to appreciate that what kind of skills that you have learned over here. Indeed, the video is going to be super lengthy, but it's going to worth each and every minute that you're going to spend on it. So let's get into it, guys. Alright, so this is my particularly favorite part to create the HR diagram. The reason behind that is I personally love this kind of diagram. Okay, it's because, like, how amazingly we are able to categorize or, like, classify this kind of different stars depending on its properties, that is temperature, absolute magnitude, spectral class, and also the luminosity, right? Now you need to understand one thing, that all the kind of previous graphs that we have created or the visualizations that we have created, all of them can be always created if you are having this kind of tabular data. Now we are able to create an HR diagram because we are having the data of star and its respective properties, that is temperature and absolute magnitude. Right now we are going to use both of this to create this kind of a diagram. So now because we are having access to this data, only then we are able to create the HR diagram. You won't always be able to create this diagram. Unlike all the other graphs, you will always be able to create this kind of graphs, right? So that's something that you need to know before we get started. Okay, so yeah, keeping this kind of things in mind, that because over here we are dealing with the star type data set, and that's the reason, because its properties, that is temperature and absolute magnitude, is available to us of real stars. That's why we'll be able to create something like this. Okay, so let's get into it. Now because I want to plot temperature on the x-axis and the absolute magnitude on the y-axis, we'll be requiring its values from the data frame. So how we can fetch these values from the data frame? So what I can do is I can create a variable called as temperature, and from the star df I can store all the values of temperature, okay, in this temperature variable. How can I do it? By calling dot values on top of this column. Okay, so on the left side of this dot, what are we doing? From the star df we are fetching this column of temperature, and now all the values that are present in that column, I am using dot values. So what it's doing, let's go ahead and try to print. It's going to create an array of these values that are present in this column, as you can see over here. Array, what is array? Array is just one of the other data structure that we have in Python that's used to store this kind of data like this. Okay, just like list, as you can see, right? But now how do I know if this is a list or an array? I can just go ahead and type this type functionality on this temperature, and we can see that it's a NumPy array, n dimensional array, right? For now you just need to know that it's just a kind of a list you can think of, but with much more functionalities. Okay, but anyway, now we have extracted the values of temperature. Just like that, I'm also going to do it for absolute magnitude, and star df absolute magnitude dot values. Okay, now because I'm having access to both of these values, I can simply go ahead and create a scatter plot. Now what is the reason of this scatter plot? If I show you this, in this HR diagram, you are trying to plot a specific star by giving its x coordinate and y coordinate. For each and every star, you just need x coordinate and y coordinate, and you simply plot it. So for that, what I am doing is, the functionality is called scatter. Okay, if you use plt.plot, it's going to give you a line plot. Okay, just like what we did over here. If you try to use this plt.plot, okay, what is it going to do? It's going to create this kind of lines. We don't want to connect the stars. We just want to plot the stars as it is. And that's what we are using, that is scatter plot. On x-axis, I am giving temperature. And then on y-axis, I'm giving absolute magnitude. And then I'm just using plt.show to simply get the output without any kind of text written on top of the figure. So hopefully everything is working the way we want. And see the output. No, it's not working, right? Now there is a specific reason behind that. Okay, we wanted some kind of parts to be there on the top part, as because we can see over here the hypergiants and the supergiants are existing over here, right? But there is nothing over here, it's completely empty. The reason behind that is, look at the temperature and the absolute magnitude axis. These values of temperature are starting from a higher value and going all the way down to a lower value. Similarly, like that, we are also seeing in the absolute magnitude. We are starting from a higher value and then going up by decreasing the value. That's completely opposite to what we are seeing in our Matplotlib output. We are starting from a smaller value, going all the way up to a higher value. And just like that, in our y-axis, we are starting from a negative value, going all the way up to positive value. So in order to get this kind of nature of the graph, I need to invert my axis. Okay, I need to invert my x-axis as well as the y-axis. And the way that we can do it with the help of Matplotlib, I can use PLT and then GCA. What is GCA? It's giving me get current axis. Okay, so whatever we are doing right now is on an axis, right? So we are getting this current axis. And then there is a property called invert, and then x-axis. And then I can also copy this line, paste this for y-axis, and let's see now how it looks like. See, this is what we expect. This is where the main sequence stars are. Then on the bottom part, we are having red dwarf, brown dwarf. Over here, we are having white dwarfs. Then on the top, we are having supergiants and the hypergiants. This is what we expect, right? Now, there is one thing that is really very different. We are not adding any kind of colors. We are not adding any kind of sizes. But now, to add this kind of functionalities in your graph, what you will need? For each and every star, there are some unique properties, right? Some unique values of x, some unique value of y. And along with that, it's going to have some respective color depending on what type of star it is. It's also going to have a specific size and also a label given to that particular star, as for example, white dwarf. So what I'm going to do over here is I'm going to create a whole lot of a Python dictionary. What is Python dictionary? It's another data structure that exists in Python, just like list, just like array. There is one more thing that is called as Python dictionary. Now, what is the reason, what's the main reason we are using this Python dictionary? You will be understanding in a while. It's going to take a lot of time for me to show you the whole dictionary. So what I'm doing is I'm simply pasting that part that I have copied and simply having it over here. Okay, I'm also going to get rid of these values because I have also pasted it over here. Okay, so on the top, these two lines basically, temperature and absolute magnitude, you already know how did we get this. But now what is the star type, right? So there is a column called star type right in our data frame, and I'm simply converting this into the values. It means if I try to visualize star type, okay, if I go ahead and print this, it's going to be the list of the zeros, 1, 0, 1, 4, 4, all these kind of things, right? We know that 0 stands for brown dwarf, 1 stands for red dwarf, 5 stands for hypergiant, so on and so forth. So now I have also created this kind of an access to all of these specific data points that are present in our data frame. So now our main motive is we are going to take each and every individual star that are from the first star all the way up to the 240th star. We are going to iterate one by one. We are going to get access to x and y coordinates. At the same time, what is the star type of that particular star? Now, by getting an access of what kind of star it is it of type 0, type 1, type 2, type 3, type 4, or type 5? I have created a whole Python dictionary for that. So, let's say if the star type is 0, then these are its respective properties. If the star type is 1, then here are its respective properties. This is what we create in Python, in dictionaries actually. It is Python dictionaries are made of key value pairs. What it means? This is the key and this is the value of that key. So in order to get access of the value, you need key. So what I'm trying to say is that if I want to see star types, okay, and now in the star types, if I'm giving 0, so now 0 is the key, right? If I run this, it's going to give me its respective value, right? Now again, the value is in the format of dictionary. If you can see, there is a curly brackets, right? And then there is a key and a value associated to that. There is a key and a value, key and a value. So I have created a dictionary within a dictionary, right? So the reason behind that is, let's say that the first star is of class 0, okay, type 0. Now I'm going to call this as the property of star 0, star type 0. And now if I want to get an idea what is the label of the star, I simply need to pass this key. It's going to give me brown dwarf. If I want to check what is the color that we are going to give to this particular star class, that is brown. What is the size that we are going to use to plot this kind of dwarfs? It's going to be size of 30. And then what is the marker that we are going to use to display on the graph? What are these markers? Over here, you are getting this kind of circles by default. Okay, you could have changed this to cross, you could have changed this to a dot, right? You could have done a lot of different markers that are available in Matplotlib. Currently, we are choosing only 2 types of markers. If it's a dwarf star, we are going to use marker as a dot. If it's a main sequence star or any kind of giant star, then we are going to use a marker as O. That's the kind of idea that we are having. By default, marker is O, as you can see. Okay. But now the whole idea that I want you to understand is that, let's say in the iteration, out of all the 240 stars, we are on, let's say, index 2. So what is the star type on index 2? Let's check that. It's 0. But now let's say if I'm on index 100, let's see. Over there, the star type is 4. So now what I'm going to do is, I'm going to change this 0 to the star type of 100. That is 4 in short, right? And now if I take a look into its property of marker, it's going to be O, right? And if I take a look into its label, it's going to be supergiants. See? Just like that, if I want to get an access of the color, I can just do this by passing in the color, and that's more than enough. I guess you might have understood what I'm trying to say. I'm trying to come up with a logic that if I'm trying to create a scatter plot, and for each and every individual point that I'll be plotting, I want to give this color, label, size, and marker. how can I do it with the help of this Python dictionary that we have created for star types? That's exactly how we are going to do it. Okay. So again, if I want to show you what is the length of the star type, it must be 240, right? So in this star type, there are 240 different values, right? Starting from 0, star type, let's just visualize it for one more time. See, 0, 0, 0, 1, 1, 1. So all of these things are for 240 times. So I'm going to iterate from the first index all the way up to last index. And then whatever is the value of star type, I'm going to get its respective properties with the help of this syntax. So that's the idea that I'm going to implement with the help of a for loop. So what I'm going to do is I'm going to create a for loop in the range of this 240 values. Okay, so length of star type, because we know that length of star type is what, 40, right? 240 I mean, right? So now let's say in future, if someone is updating this CSV file, if we are having a lot more data as compared to 240 stars, it will be very dynamic for us to write this length of star type instead of 240, right? So that's the reason that I have written this length of star. So now what's going to happen? The value of I is going to start from 0 and go all the way up to 239, right? And now I'm going to plot this scatter diagram for each and every star. So the temperature on the index 0 and its respective value of absolute magnitude on index 0 is the first star that I'm going to plot. Then when the value of I will change to 1, it will be temperature 1, comma absolute magnitude 1. So each and every star that I am going to extract from the temperature and the absolute magnitude, I am creating this XY coordinate and then I'm simply going to plot it in the scatter plot. But now at the same time, I'm also giving the properties of the size, color, marker, and the label. Okay. Now I can extract these properties just like how I have explained over here. So I'm going to copy this part and store it into a variable called as properties. Okay. But now I need to change this to I, because I don't want star type that is present on index 100. I want to automatically change if the value of I is changing. So when the value of I is 0, it means on the first row, what is the star type? With respect to that, give me the properties, right? And then when the value of I is 100, at that particular point, what is the star type? Get me its respective properties, right? So that's the kind of idea that we have done. And after that, if you want to call its respective properties of size, color, marker, and label, how you can do it? I'm going to give properties and I'm going to write size over here, right? Size, color, marker, label, right? I'm just going to copy this code, paste it for color, change this size to color. And for marker, again, I'm going to paste this, change this to marker. And for the label, again, paste it and change this to label. So our idea is done. Hopefully everything is going to work fine. Let's go ahead and try to test this. Okay. I'm just going to get rid of this extra things because we don't require it anymore. And if I go ahead and look into this output, I don't need any kind of extra spaces. I'll get rid of this, right? So see, this is the kind of output that we're getting, right? All the hypergiants, supergiants are getting colored. Then these are the kind of main sequence stars. These are the red dwarfs. These are brown dwarfs. These are white dwarfs. All of them are what we expect in the HR diagram. It's in the same exact way, right? That's what we expect, right? But now there is one thing that we are not able to give any kind of label, right? We are not able to see any kind of label that this is a white dwarf, this is a main sequence star, right? We are not able to see these kind of things. The reason behind that is because we haven't given legend. In Matplotlib, you give this legend in order to display this label. So if I run this code, just stick around with me because there are quite some more things we are doing in this specific video, because there is a problem associated with this command. Okay, I'll be explaining that to you. See, that's the problem I was talking about. Now for each and every star, that is for 240 stars, whatever is the star type, it's going to give a label to it and assign in the graph itself. Now that's not something that I'm looking forward to. if my brown dwarf has appeared once, I don't want to label it again, because I know that this kind of stars are going to be brown dwarf. Then this type of stars are my red dwarfs, right? If it has appeared once, I don't want to appear it for more than one time. So now I am going to come up with a very good logic that's going to help me solve this issue. Okay. Now the reason that I'm able to explain all of these things very fluently, it's not that because I'm a very good programmer, everything comes to me in just a second. It's not like that. It's years of practice. At the same time, I have already done this I have already solved this problem. Okay, it took me some time. It's not that on the spot I got these things. Okay, so it's completely fine. It's not that everyone is going to get it on the spot. If you are especially a beginner, it will take some time, right? So try to digest the things that I'm going to explain right now. Okay, so see, what I'm going to do is I'm trying to create two things. This requires some kind of an idea of how legend works. Okay, so let me explain you that first. Legends basically take one input called as handles. What are these handles? These handles are nothing but each and every plot that you are trying to give. Okay, so let's just call this thing as axis. Okay, and I'm just also going to press tab to shift it to the right, and I guess one space back should do, right? This is looking good. Yeah, this is looking better. Yeah. Now what I'm going to do is, in place of these handles, I'm going to write labels. Now what is this labels? I've again not created any kind of labels. So I'm going to create a set called labels. Labels is equal to set. At the same time, I'm going to create axis empty list. So what I have done? I have created two empty data structures. One that is a list and one that is a set. The unique concept about the set is that if there are more than one thing that is repeated, okay, there is a one thing that is repeated for more than one time, it's going to consider it for only one time. So what I'm trying to say is, let's say I'm having set of 1 comma 1 comma 1. See what is the output going to be. Okay, it's going getting this kind of an error because we have done a syntax problem. I'm going to come out of this and then I'm going to give this. See, the output is only 1. Output is only 1. No matter how many times 1 is repeated, it will always give the output of 1. So that's the kind of logic that we are having over here. Okay, we will be keeping on adding the labels over here and make sure that labels are appearing only once. Okay, and then for which plot I want to give this axis label. Okay, for whichever plot I want to give this label, I'll be adding that data point to this particular axis and labels. It might be getting a bit overwhelming. So let me go ahead and show you what I'm trying to say. Okay, what I have done till now, I have created this kind of a scatter plot and that's what you are seeing. But now this kind of legends are looking very ugly, right? So we are trying to sort that problem, okay, by calling these two things. Now I'm going to give an if statement. Now what is this if statement all about? If the label that we are getting for the star type, okay, so from this properties, if the label value is not present in labels, okay, only then you are going to give this ax is equal to this kind of graph. And then after that, what you are going to do is, this is really important, you are going to add this axis to this axis and then also add the label, because it was not present in this particular set. Because it's not present, you are going to add it. Okay, so what I'm doing is, I'm going to first of all add this ax to this axis list. How can I do it? I can do it with this axis command, that get me that list which I'm trying to add some new values. So in the list, you can add some new data point with the help of this append command. Okay, the append command that you can see. Okay, for some reason I'm not able to click it. Yeah, anyway, I'm successful in clicking it. Anyway, so now axis the in empty list, I want to append what? This ax. This is the handle. Okay, this is the, not the handle actually, but the axis. In the handles are the labels that I want to display. So what am I appending over here? I am appending this AX. Okay, so what's going to happen? For every iteration, if the label that is present for the respective star type is not already present over here, then what you do, you create this axis, and that axis, what you're going to do, you're going to pass it onto this particular list that we have created. That's an empty list. And after that, what you're going to do is you're going to add a label to this set. How am I going to do this? I'm going to achieve this with the help of labels dot not append anymore. It's going to be add directly. That's how this kind of functions are built. Okay. For set it's add, for list it's append. And now I'm going to add the label, that is properties and label. I hope the idea is getting clear. It will be clear once the output is in front of you. Okay. Now let's say if this label already exists in label, then I don't want to add label to this kind of set. Then I don't want to add. Okay. Then I don't even want to create this kind of axis. In that case, what I want to do is I'm going to give this else block and simply create my scatter plot without adding any kind of axis or any kind of that stuff. Okay. So yeah, that's the kind of logic that we have created. I'm going to press shift tab. Yeah, this is looking good. So now we are expecting the output to be very decent. It's not going to be as ugly as what we had seen. Okay, we have got an error. Let's try to look into the error. It's saying that string object has no attribute get underscore label. Let's see, where did we got this error? This error is over here, right? It's because the labels, right? It should be labels. Let me check this to axis and see how it works. If the axis is going to work, then yeah, I would have done an error. Yeah, I had done an error. Actually, we had to store the axis. Okay, what is happening? So this axis is giving you this kind of an command that, okay, for this particular point that you have plotted, you want to display this label, right? And that legend is automatically having this kind of labels, right? That's the kind of mistake that I was making. Legend is already having access to all the labels. That's the reason why we were seeing brown dwarf multiple times, red dwarf multiple times, right? So that's not a problem. The problem is that if the axis is present over here, if I show you the axis list, let's go ahead and see it. See, now all of this is a path collection. For each and every point, there might be 6. 1, 2, 3, 4, 5, 6. What is the reason of this 6? Because we are having 6 different categories, right? So for each and every point, we are having this kind of axis. Now what I am trying to do is, I want to show the label of legend only for those respective axes, or else I don't want to show it. So that's the kind of thing that we have done over here. And hopefully now it's making sense. And now obviously you can beautify this plot by customizing, by adding x-axis, y-axis and all that kind of stuff. And I can simply go ahead and copy paste this thing because I have already done this for a lot of times. I've copied that data and I'm simply going to paste it over here. Okay. And let's see now how the output looks like. And now let's say if you're also interested to add the data of sun, okay, in this whole thing. I guess the diagram is pretty much small. I'll also increase the figure size over here. Figure size. How I can do this? With the help of PLT, right? Figure and then fig size. I'm giving my figure size as, let's say 10,6. I guess this is going to be fine. Okay. Now I just want you to realize that even after having a lot of experience in Python, this kind of problems happen. Okay. You need to go to the documentation and make things fine. As a Python developer, it's our duty to go ahead and make things right, depending, because we're having access to all the kind of documents. Okay. But right now I was able to solve this error because of the the output of the error that we had got. Anyway, the important part that I want to convey is that you should not ever be frightened if you're getting errors. Okay. If you're getting errors, it's okay. You should know how to solve those errors. That's it. If you are good at that, you are good to encounter any kind of problems in your life. specific to at least the Python programming questions. Okay, but anyway, if we are talking about this, I'll just ignore this thing. It's quite, yeah, disturbing. Yeah, anyway, this is the kind of output that we have got, right, for the HR diagram. Now, one last thing is, let's try to add the data for the sun and see that where exactly on this HR diagram that sun is going to be looking like. Okay, so for that, what I'll be doing is I'll be copying this data that I'm having for the sun and simply add it into our code. So I'm coming back to our code. I'm going to give this kind of a title, I mean the comment, adding data for sun. Now what is this? I'm creating one more axis specifically for sun because I also want to append this kind of thing and visualize in my output. This is the temperature value. I've gone to Google and got this kind of values. This is temperature. This is absolute magnitude. This is the size that I'm keeping. Color is yellow. Marker is O. And label is sun, right? And I'm simply also adding this axis that we have created for the sun. And I'm also appending this labels as sun. Okay. Now that's the whole point. You will be automatically seeing that somewhere over here in the main sequence, we know that sun is a main sequence star. So somewhere along this part, our sun should be added. Just like this, whatever kind of star you are interested to know about, right? You go and find its property on star and try to plot it and see where it's going to be in the graph. For us, sun is over here, right? That's where the sun is, and even in the legend, you are able to see that sun has been added separately. Apart from all of this, we are also adding a data point of sun. Isn't it just amazing how we have created this kind of whole thing by getting ideas of Python that we have learned in our first module, and then again some few things that I have taught in this particular video about how you can create an empty list and empty set, and then how you can add data to it. The whole idea over here was this thing. Okay, if you don't know how this kind of things work, then you will need some kind of experience of how set and this kind of list works. But the only thing that you need to know over here is that we have created this kind of empty list and empty set to store the axis that is with respect to the plot that we are making over here. We are trying to store it over here so that with respect to that plot, I am able to show the label that is present in the legend command, in this legend command, right? So yeah, that's the end of this particular video. I hope you enjoyed creating your own HR diagram, right? For the 240 stars, if you can see, I have also given this kind of a dynamic way of writing this so that in future, if star type is changing its length, let's say we are adding more data to this existing CSV file, then you will be able to create for, let's say, 500 stars if there are more addition to the data, right? So yeah, these are all the kind of plots that we have generated, but I have not saved it, right? My common so my common mistake is I always forget to save the figure size, I mean the figure, right, that we have generated. So save figure, how am I saving it? I'm giving my base directory and the name HR diagram. Yeah, finally running this, and I'll be also checking this before we end this video if this has been done fine or not. Coming over here, looking into the star plots, this is HR diagram. Close this. See the beautiful plot right in front of you, right? The reason I haven't shown you how to do the title, X label and Y label, because you have been doing this for a couple of above plots, right? In the Y label, I have added the absolute magnitude. On the X label, temperature, given respective font size and the color. As you know, my favorite one is step pink, so that's the color that I have given for them. And for the title, I am giving the HR diagram title and a dynamic way of writing the title by giving the F string. Font size is 15 and the color is royal blue, another my favorite color. Okay, so yeah, that's about this particular video, guys. I hope you have enjoyed this one. Hey guys, so welcome to the last video of this particular module, where you are going to understand that how you can download these visualizations that you have created in module 2 and saved it into a particular directory. So now how you can save that directory into your system from Google Colab Notebook. So all of these things you'll be learning in this particular video. So let's get into it. Alright guys, so now let's understand that how we can go ahead and download this star plots, all the kind of visualizations that we have created over here, from very basics to very advanced level of visualizations. You can do this with the help of, because we are using Google Colab, there are some specific ways in Google Colab through which you can do this. The one that we are going to do is, I'm going to follow this method that you can see it right now on the screen. Okay. The whole idea is that from this google.colab, I am going to import files. What are these files? These are the same files that you can see over here. Everything that is over here, we are going to get access to this with the help of these files, right? Now, what I'm doing over here, the logic that has been implemented is that I'm going to create a zip file out of this folder. Okay, if I just click on this option, there is no option to directly download this folder, right? There is no option like that. So what I'm going to do instead is to create a zip file of it, because zip files are downloadable in Google Colab. So what I'm doing, I'm creating this zip command, and then I'm giving two things. Which folder I want to zip, I'm just taking that particular folder, pasting that same thing over here, and just passing .zip on top of that. That hey, in this particular path, this is called content path in which the star plots exist. So in this particular path, I want to create a zip file. That's it. And once the zip file will be created, it will automatically be downloaded by giving this kind of input to this download command. Okay, so this download functionality exists in this file. Okay, so whatever is the file, if you give the path to download that file, it will be downloaded. If I show it to you, what's going to happen? So if I run this code, you will be able to see that a zip file will be generated. And now you are giving this path in the download. And automatically you are seeing that this kind of files have been zipped for us and also downloaded into my system. Now I simply need to click on this. And if I show this to you, this is the content folder, right? Inside which we are having the star plots folder. And see, here are everything that we need to know. Okay, ignore this particular thing. For example, this is the star colors visualization that we had generated, right? If you want, you can also obviously increase the size and everything, right? And then here is the HR diagram, my favorite diagram, right? It took the most amount of time in the whole video program, the overall program, not just one video, right? But yeah, that's the kind of output that we have generated. So yeah, now you can simply attach this kind of thing in any kind of research work that they are doing. So that was the whole point, that with the help of a tabular data, how you can create this kind of visualizations in Python with the help of Google Colab, and also extract it into your system. Alright guys, so it's time to bid a farewell to our module 2. So over here, we used a tabular data set on stars data and created some amazing visualizations with the help of Matplotlib and Seaborn library. We looked into some of the different types of visualizations like bar graph, box plot, line plot, pair plot, and then eventually created a HR diagram with respect to the scatter plot. And then how can we save these outputs that we are creating and download it into our particular system? So all of these things we have done so far, and I hope that you are enjoying each and every bit of this particular program. Now in the next module, we are going to jump into some image visualizations and do some amazing stuff over there. So stay tuned for that. I'll see you in that next module. Hey guys, I welcome you all to the third module of this program. Here, you are going to take one step forward, where in the second module, you had performed the visualizations on the tabular data. Now you are going to create visualizations on the image data. And therefore, to start with in this module, we are going to explain you what is the concept of an image, then what is fits file, because this is the file type through which you are going to access the astronomical images, which you are going to perform some kind of visualizations on top of that. Then what is sky view form, how you can fetch the data of Andromeda galaxy from astronomical surveys like SDSS GMAND and DSS2 Blue. Then how you can implement some of the pixel scaling methods on this Andromeda galaxy, visualize the pixel distribution, and lastly, what is the concept of Z-scale interval in a library called as AstroPy, and why are we specifically using it for this particular program? All of this is covered in this particular module, guys. So let's get into this module, and I'll see you in the next video where we are going to talk about image. Hey guys, welcome to the second video of module 3, where I'm going to explain you the concept of digital images in the format of pixels, what are grayscale images, colorful images, and a lot more. So let's get into it. Alright guys, so let us go ahead and try to understand this concept about an image. So what is an image? I'll be first talking about how this kind of images are formed, and then what are some kind of different things you need to understand about it. So talking about how this kind of images are formed. It's kind of a puzzle if you think about it. Okay, let's say that you are having different kind of pieces of puzzles which you are going to combine together to form this kind of an image. That's the same kind of logic that we are going to use in order to understand how this kind of images are formed. So this kind of puzzle pieces which are coming together and forming this kind of one final image. These puzzle pieces are nothing but the pixels. These pixels are combined together to form what we see as an image over here. So now what is this kind of pixels, right? We know about the puzzle pieces, that there are some kind of pieces which are joining together to form this image. But how do we know what is a pixel? So for that, what I have done is I have just zoomed into this particular image as much as possible, but not over here because Google Colab is not allowing me to zoom any further than this. Okay. So what I have done, I have captured this image, I have pasted it into the paint, and on the paint, I was able to zoom in much further as compared to what Google Colab is allowing me. So I got some kind of information like this. Okay. So this particular part is being representing the top left part of the image. Okay. So I'm zooming into it as much as possible, and this kind of small squares you are seeing, right? This is a small square, this is a small square, this is a small square. So all of these small squares are nothing but the pixels. And see how this kind of different pixels are there. And all of these pixels which are coming together, let's say if you're just talking about the first row of the small squares, all of these pixels are coming together to define the width of this image. Just like that, there are also pixels over here which are stacked up together in this kind of a vertical line, which is giving us the information about the height of this image. At the same time, they are having some kind of different shades of colors which are stored within it. Some kind of bluish colors over here, some kind of very darker shade of blue as compared to what are there in the nearby pixels. And similarly over here, it's talking about the brownish colors. Over here, it's talking about the dark green kind of color, right? So all of the small squares are hiding the information about what kind of shade of color is represented on that particular location of an image. So I hope a very basic idea about how this kind of images are formed is clear. This kind of images are the combination of this kind of pixels, and each of these pixels are having some kind of information about what is the shade of color represented over here to show it into the output of the image, right? So let's say this is a piece of puzzle which is storing this kind of detail. This is a piece of puzzle which is storing this kind of color of that particular detail. All of these pieces of puzzles are nothing but the square shape. But now, based on this kind of information of the shades of color, you are going to create an image that is something like this, right? Now they can combine together to get the width and the height of the image. At the same time, how do we know about this kind of intensities of colors? Now for that, we need to understand how this kind of images are formed. But I hope the part of the pixel is clear, that how this kind of pixels come up together to what we see right now in this particular image, right? Now if we talk about how this kind of intensities of colors are coming into the picture, how do we know that what kind of shade will be represented by what kind of part in the image? So to understand that particular part, we need to talk about the sensor. That sensor is nothing but the camera that I was talking about when I started this particular video. So let's say we are having this camera, and in this camera we are having three different filters. One to capture the red light coming from whatever is the source which sensor is trying to capture. Similarly, whatever is the greenish kind of part that is being captured will be done with the help of green band filter. And similarly for a blue color, whatever is the bluish part over here, you can see there is some kind of a blue part, there is a blue part over here, and also a blue part over here. So all of the light hitting to the sensors coming from this kind of bluish part will be filtered out with the help of the the blue band filter, right? So now what's going to happen? We know that typically all of these colors that we see, different kind of shades of colors that we see, are the formation of different kind of mixes of red, green and blue. We know these things from our very primary classes in school, right? Or in the art classes, right? So now this kind of different combinations of red, green and blue will be captured from this particular image with the help of the sensor, that is camera. And how? With the help of this kind of green band filter, red band filter and the blue band filter. Now the whole logic over here is the way that it is being captured is with the help of what kind of wavelength of light is contributing to the red part of the visible spectrum. Now I'm going into much more technical terms. Let's not go into that particular direction and talk about in a very simple terms. Whatever light that you are seeing over here is being coming to the sensor, if it's falling into the red kind of region, then that will be filtered out with the help of red band filter. Similarly for the green light and the blue light. And the output of this is represented always into this kind of a grayscale image. Okay. Now, if we talk about the image that we are going to deal with throughout this whole module is an 8-bit integer image. Now, different kind of bit of pixels stores different amount of information. Okay. So let's say I'm having a comparison of an 8-bit pixel to a 16-bit pixel. More this kind of 8-bit and 16-bit pixels, more the combination of shades of colors it can represent. That's a very simple idea about 8-bit image and a 16-bit image. In 16-bit images, you will be able to represent a particular color with a more amount of shades, okay, more amount of depth basically you will be able to get from an image, right? So if I talk about the image that is an 8-bit image that we are going to deal with in this whole module, let's talk about that. So in that 8-bit image, all these pixel values are going to range in between 0 to 255. To represent any kind of information, let's say about the red light coming from this particular image, from this particular part and hitting on the sensor. If it's coming from the red red light sources, it's going to be represented into different 256 shades and the values are going to be in between 0 to 255. That's the whole concept. So 255 being the lighter part of the whole image, and the part which is represented darker are closer towards the 0 side. So what does this kind of number 0 to 255 indicate? So 8-bit integer image is going to give you 256 different shades of a color, maybe red, green or blue, right? So now if you are going to combine them, red, green and blue, so 256 into 256 into 256, these are the possible shades you can get and form a whole colorful image that you can see over here. Okay, if you increase this bits, let's say 16 bits per pixel, then you are having 2 to the power of 16 multiplied by 3 times to basically get even more shades of colors as compared to an 8-bit image. Okay, so that's an idea with respect to this. But now let's try to observe that if I talk about this kind of bluish part, this is a blue part of an image, this is another blue part of an image, this is another blue part of an image. And now if I talk about blue band filter, it should be able to filter all of these things and give a very high value to it, that is 255. The lighter part of the blue band filter should be representing the blue part. So I'm having this kind of blue part that is surrounded by potatoes over here. Then on top of this kind of apples, we are having this, right? So if I try to show you the output of the blue band, you can see that this part is light, this part is light, right? This whole part is light as compared to the above images. In green band, this part is darker, this part is darker. In the red band, see, even this part is darker and this part is darker, right? So that's what I was trying to show you, that because with the help of blue band filter that is stored in the sensor, that is camera, it is able to get this kind of blue light and give a high value to it, that is 255, closer to 255. Similarly, if I talk about, let's say, greenish part in these images, which are this kind of grapes, right? This kind of melons, right? If I show you them over here, you can see that they are again expressed in the lighter pixels that are values closer to 255. As compared to this one, see how darker they are, closer to the 0, right? The darker pixels are closer to 0. So how this kind of things are represented by a darker color, right? Similarly, if you talk about this kind of red parts in the images, you can see that these are kind of apples which are red. These are tomatoes that are red, right? If I try to show them over here, see how dark it is in the green band filter. But if I talk about the red band filter, see how lighter this kind of things are. All of this information are represented by the pixels which are closer towards 200 255 kind of side, right? So that's the whole idea. Now you might be wondering that potatoes that are given over here are yellow in color, right? Then why in the green band and the red band we are having the lighter pixels? So if you think about a yellow color, it's a combination of the red color and the green color. Now that's the reason why even in the green part and the red part you are able to see this lighter part in the image. Now what is the exact shade of red? What is the exact shade of green? Out of the possible 256 combinations, they're going to come together and finally form this kind of a yellowish image in the final output. If I show you that potato in the blue part, you will see it's a darker color. As compared to the green and the red, you are seeing that this part is darker, right? Anyway, there are again some kind of blue pixels that are also there, some kind of shades of blue. Let it be a darker part, right? All these kind of things are coming up together and give you this exact color that you are seeing over here. So to just summarize the whole concept of an image, we first understood the idea about what are the pixels, because with the help of this kind of small squares that you are able to see, these small squares are coming up together and giving you this kind of this kind of what is the width of the image, what is the height of the image. And if we talk about the intensities of the colors that are represented by this kind of small squares, is dependent on how much amount of shade of red is present, what is the shade of green is present, what is the shade of blue is present at the time of capturing that particular image. And depending on that, based on this red band, green band and blue band filter, we are getting some kind of respective outputs, and all of these values are stored in the range of 0 to 255. 255 being the lighter part, 0 being the darker part of that specific output of the filter. Then you combine all of these three images with respective shades of green, red, blue, and finally whatever are the shades that you can create is the final output of this image. So wherever there was a bluish part, right, all of these pixels came together, are combined together, stacked on top of each other, and this part where the blue is present, this kind of color will be there. On this specific location, what is the output of the blue filter? What is the output of the green band filter? What is the output of the red band filter? Combination of all of these three. Because the bluish part is higher in color, that's why this kind of pixel is given some shade of blue. By combining this RGB possible combination that we are getting from the sensor, this is the color that we are able to fetch. So I hope I am able to convey the ideas with respect to what are these images, how are they formed, because these are the building blocks that we are talking about this module. As we go ahead, we are going to actually represent all of these images into the format of pixel. How are you going to do this? You will be seeing this in the upcoming videos. So stay tuned for that. Hey everyone, welcome to the third video of module 3. And now that we are going to deal with the astronomical images, they are typically saved in the format of FITS file. So it's essential for us that we understand what exactly is this FITS file and what kind of things it typically contains. So let's get into it and understand about all of this information. So now let's try to have a very quick idea about what are FITS files. So in the Astronomical Society, this is one of the very popular way in order to store the data that we are getting from these telescopes, in order to load it into our system, and let's say we are doing some kind of image processing on top of that, and doing some amazing research analysis of what kind of information is stored in this kind of images captured by the telescopes. Now that's exactly what we will be doing in the upcoming few videos, and that's the reason why I am explaining you over here about the FITS file, because you are going to fetch the data from one of the astronomical surveys, that is the Andromeda galaxy. It's not going to look like this at all. It's a very raw image that you will be getting from the telescope. And then how you are able to get that image? It's stored in the format of FITS file. So what are the components of the FITS file? Let's try to understand that. So FITS file is having multiple different header units. At the same time, all of these header units are also coming up with some kind of a data. Now this data could be in the form of images, it could be in the format of different tables, etc. Right? So right now, because we are going to focus on the image data, let's just understand what are these kind of two main components you need to know about the FITS file. The first thing is the header unit, and all of the FITS file will come with the primary header unit for sure, and then some kind of extension header units that are going to reveal about some more information about that specific image that we are trying to talk about. So typically this kind of header units are storing some kind of metadata which is revealing the information about, let's say for example, what was the telescope used to capture that specific astronomical object, what is the location of that astronomical object out there in space, for example, what is the right ascension, what is the declination. These are nothing but the space celestial coordinates that we are having to get an exact precise location of the astronomical body out there in space, right? So we are able to get all of this kind of information with respect to the header unit. I'm going to show this kind of live demonstration for this kind of Andromeda galaxy. By the way, this is the closest galaxy to the Earth, if you don't know, right? It's going to be really very amazing thing we are going to do in the few upcoming videos for this module, right? So we're going to study about this kind of header units, and all of these header units might have some kind of data. We're going to also extract this data and do some image processing on top of that to reveal some of the amazing beauties about this Andromeda galaxy. Right now, obviously, you are seeing a very highly detailed processed image. We are not going to get anything very close to this, but yet do some kind of research work in terms of doing some kind of image processing and get some kind of analysis, as in, like, you can see there is some kind of a small galaxy over here, right, on top of that huge galaxy, right? We'll be able to get all of this information by doing some kind of image processing, right? So all of these things you will be seeing in the upcoming few videos, so stay tuned for that. Hey everyone, welcome to the fourth video of module 3. So far we have just covered this kind of theoretical understanding of what is an image, and because we are going to deal with the astronomical data and typically it's going to be in the format of FITS file, so we have also covered that so far. But now it's time to start the coding process, and as usual, we are going to import the libraries, and if it's not pre-installed in Google Colab, we are going to first install it and then import it. So let's get into the video. Now, as we are going to perform some of the image processing tasks throughout this module on this astronomical data called as Andromeda galaxy, so how we can collect this data from a lot of astronomical surveys and call it into our Google Colab notebook. We can do this with the help of a library called as AstroQuery. So now, like Matplotlib, this is not pre-installed in the Google Colab environment. So you will have to manually install it by using this command called as pip install and the name of the library, that is AstroQuery. And you simply run this code and it's going to take some seconds and simply install it for us in this Google Colab environment. Now the moment this is done, you will require one more library through which you will be performing the visualizations. And as you might have guessed, it is Matplotlib. So I'm also going to import Matplotlib along with that pyplot as PLT. Now it's not that we are just going to use Matplotlib, okay? As I also installed this kind of AstroQuery, you are also going to use some of the functionalities of this particular library in order to call that image, as I mentioned about the Andromeda galaxy. And along with that, there is one more library called as AstroPy. Even that is the one that you're going to use in upcoming videos. But for now, there were only two basic steps that I really wanted to show you, that with the help of what library you will be calling this image of Andromeda galaxy into your Google Colab notebook. And then obviously, in order to visualize it, what is the library that we are going to use? That is Matplotlib. Now in the next video, you are going to see some of the amazing things through which you are just going to be completely shocked, like, this kind of things we can do in Python. So stay tuned for that. Hey guys, welcome to the fifth video of module 3. And here we are going to take a look onto the Internet's virtual telescope with the help of SkyView form. So what exactly is this form and how we can get the image of the Andromeda galaxy out of this? Let's look into that in this particular video. So let me introduce you all to this interesting form called as SkyView query form. Now with the help of this form, you are going to get this access of this Andromeda galaxy. So if I just click on this particular link, it's going to redirect me to that particular site where I can access this SkyView query form. So what is this form all about? As you can see, it is the Internet's virtual telescope. So with the help of this particular query form, you can query about any kind of image that you are looking forward to, that is M31 in our case, that is Andromeda galaxy. So for the Andromeda galaxy, from all the possible available surveys over here, we just need to give some of the selections that we want to visualize our M31 in. So the telescope that we are going to use is the SDSS and DSS, and both of them are in the optical range. And with the help of SDSS, I am going to perform some of the image processing tasks. And with the help of DSS, I am going to show you the whole output of how this kind of galaxy looks like in Python. Okay, we are going to do all these kind of things in the upcoming videos. But for now, let's see if I want to visualize this data in this form itself without using Python. How can I do it? So for example, if I'm clicking on this SDSSG and click on enter, because I have already pre-selected this particular object as or source as M31, that's the Andromeda galaxy, and I'm using this particular survey called SDSS of G band, it's going to give us this particular output. Now what is this? This is the extreme center of the Andromeda galaxy, or I should say the core of the Andromeda galaxy. So if I just have to show you over here, the extreme core over here, this kind of like, this kind of bright part you are seeing, this bright part. So that bright part, if you are trying to just dim that thing and look exactly into the center, that center is nothing but what is visualized over here. Just in case if I really want to show you what this means, this is very zoomed in version of what's going on in the center of this particular core of Andromeda galaxy, and we are going to perform our all the kind of image processing on top of this particular output. But now what if I want to just zoom out a bit and show you with respect to some other survey, that is the DSS, and let me select this DSS2 blue, and I'll do one thing. I'll clear every survey sections and then I'll again select this blue, and this time I'll just change the setting of image size pixels from 300 to 600. And now if I submit this request, so this is the kind of output that we are seeing. I have zoomed out only by a bit. I have doubled the pixel size, so I'm getting much more output as compared to what we were seeing before, a much larger output. But now it's still like, if I just compare it with the original image over here, it's this kind of part that you are able to visualize. If I just zoom in, say I'm not able to zoom in any further than this, but now this is the power of the telescope images that we are having. This is visualizing at the extreme center. Now over here in this specific image, you are not able to look into that extreme core because we have zoomed out a bit. However, you are able to see some of this kind of bands of this particular galaxy, and these bands are nothing but the bands that you are seeing over here. So this is a very zoomed in image. Now what I'm going to perform over here for you guys in the upcoming videos is that with the help of this DSS2 blue, we are going to try to visualize this whole not library, but the image, the whole image of this Andromeda galaxy. I'm going to try to visualize this kind of thing for you with the help of DSS2 blue, and then with the help of SDSSG, that 300 by 300 pixels that we had seen, we are going to perform image processing over there and try to decode what all kind of structures we are able to find out of that simple looking thing that we had seen earlier, this thing. Okay, I guess I have selected two surveys. This is the first survey and this is the second survey, right? This was the first DSS2 blue and this is the second one. That was the main reason why I primarily went away over here and clicked on clear survey selections, because I don't want to see both the things. I just wanted to see one. But anyway, these are both the surveys over here. One's with respect to DSS2, the zoomed out version 600 by 600, and over here this is 300 by 300, focusing extremely on the core of this particular galaxy. So now in the upcoming video, we are going to call this data of SkyView query form with the help of AstroQuery library into Python. So it will be really interesting to see how we can do this. So stay tuned for that. Hey guys, welcome to the sixth video of module 3. And here we are going to use the AstroQuery library in order to get the access of the SkyView that we had seen in our previous video. And from there, we are going to fetch this data of Andromeda galaxy from a particular survey, that is SDSS, specifically G-band. Okay, all these things you will be understanding in this video, but the output of this will be a FITS file. And now that you are also aware about the FITS file, it will have two types of information, header and data. So header will consist of metadata, and data will have some kind of image present over there. So we are going to take that image data and visualize the output of the Andromeda galaxy and just compare it with the actual view that we had for the Andromeda galaxy using the sky view form. So now that you are aware about what is this sky view query form, where you can give in the information about the source that you want to visualize with respect to any of these available survey options. Right now we have already visualized with respect to optical, SDSS and DSS. But now specifically if I, let's say, want to visualize this SDSSG in my Python. So basically what I'm trying to do is I hope this is SDSS G band. So I'm trying to visualize this particular information with respect to Python. So how we can do this with the help of Astro query library? Let's try to look into that. So for that, what I have to do is, first of all, I need to get this sky view functionality in Python. And I can do this with the help of Astro query library with this command from Astro query dot sky view. I need to import sky view class. So with the help of this sky view class, we are going to use one of the method of this sky view class through which we can fetch this data of M31 of this particular survey. And I can do this with this command sky view. The moment I press this dot, it's going to give me all the possible methods associated with this sky view class. And now because we are interested to get these images, I'm going to click on that. And now let's see what kind of inputs we can give to this particular method. So I'm just pressing the parenthesis and I'm just waiting for a while. And now this is the kind of pop-up that I'm able to see automatically on Google Colab. And the first input is going to expect is the position, which is nothing but the M31 in our case. The second input that is expecting is the survey, which is going to be SDSSG in our particular attempt that we are trying to visualize something. All the kind of other information, you can keep it as of whatever it is. I'm not going to change anything. And we're going to do a lot of different stuff on top of that. That's why I'm not changing any kind of things as of now. And so yeah, let me give the input of M31 as the position and the survey as SDSSG. And the moment I run this, I am getting a list within a list, right? I'm getting this kind of square brackets, which is called as a list. And inside that, I'm having one more list. And inside that inner list, I am having this kind of a file. Now, what is this file? This is a file which is called as a FITS file that we had talked about earlier in this particular module. We had talked about how this kind of FITS file is created. It is having some information about a primary header for sure and some of the metadata associated with that. Now, along with that, it might or it might not have this kind of extension headers and the data associated with that. So in our case, as we are seeing only one primary header, it's basically indicating that we are having information about the primary header and with respect to that, what is the metadata associated with it. And any kind of extension information is not given to us. And that's the reason why we are having only one information within this kind of main list. Now that's exactly what we are going to fetch out of this list and get this HDU file from it. How we can do this? First of all, I'm having this kind of the original list, the main list, inside which there is one list. So let's get access to that inner list. I can do this with the help of this index 0 because I know that this particular list is present on the 0th index. Now if I run this code and show you the output, let's see what do we get. So as expected, we are now into the inner list. Now inside this inner list, we also again see that this HDU file is present in the 0th element on the first position basically. So I again need to pass this 0 and now we are successfully going to get this HDU file that we are looking forward to. And now this is nothing but the primary HDU. So I'm just going to store it in a variable called as HDU. Now always remember, HDU is coming with two different type of information. One is the metadata, which is going to give us all the kind of details with respect to the FITS file, who has created it, when was it created, the information about the telescope and the survey that was used to fetch this particular data. Every kind of information will be stored as the metadata in the format called as header. Now, along with header, there is one more kind of thing we call as data. Now, that data, as I had explained earlier, could be in the format of an image, could be a tabular data, right? All this kind of information could be there. So now let's try to understand, first of all, the metadata that is associated with this primary HDU. Now I can do this with this function called as header of this HDU. So HDU.header. This is the only command that I'm typing to get all the metadata information associated with it. Now, as you can see that this is the file written by the Skyview, Thursday, December 14, with this particular time and everything, the information when this particular file was written. After that, we are also having this particular idea that it is containing a two-dimensional image as well. What is the width of the image? 300. What is the height of the image? 300. If you remember in the Skyview form itself, by default it was having 300 pixels. If I don't write this, if I just refresh this, by default it was giving us this 300, and that's the exact reason why we are having this 300 by 300. I can surely go ahead and manually change this to 600 if I want, but I'll be doing this for the other optical survey, that is the DSS survey, right? This particular survey, DSS2. I'll be showing that in the upcoming videos, but let's now focus on this particular part. See, by default the pixel size is set to 300, so that's the reason why we are again saying this kind of 300 by 300. So all of this information with respect to this, see, again there's a comment with respect to Skyview survey metadata, right? Then all the respective information, the copyright information, survey information, projection information, coordinates information, epoch information, all of this particular thing is given over here. In the SDSS, there are multiple data releases. This is part of data release 9, DR9. Again, this kind of information is there. So obviously, it will take a lot of time for me to explain each and every part of this metadata. You get used to it once you're having more and more practice with respect to, like, dealing with the FITS file, specifically the astronomical data. But right now, the key takeaway for you is that in this header information of the HDU file, you get this kind of basic information, right? You can just keep on scrolling and get any kind of respective useful information for you. So that was about with respect to metadata. Now what about, because we know that it's also containing some kind of image, how can I fetch that image out of this particular HDU file? So for that, I'll just scroll down and see here I've also written the comment that get the pixel data that is present from this HDU. Now I simply need to do HDU.data. How I did HDU.header for the metadata, just like that, I need to do HDU.data in order to get this pixel information. And as we had seen, it's in the format of float 32, where we had seen this. If I just scroll up, this is where we had seen this. Now it's like, it's also including some kind of negative numbers, and it could have positive numbers, and it's of a float 32 type. It's a floating point numbers of array, and it is a float 32 type. Again, in the beginning of this particular module, I had explained about this images, all of this kind of pixels. So these pixels are in the range of 0 to 255 for a uint 8 image. But right now we are dealing with the float 32 type image. And it's the sign is also playing an important role. It means it might have some kind of negative data, some kind of positive data. Okay, don't worry about all these kind of things. I'm not going to go into any kind of further technical details, but see, now we are having this kind of a data, and it's of a type float 32. Even this kind of information was present in the metadata. So over here, this is nothing but the M31 pixels data. I'm going to store this particular thing as the M31 pixels data, because this is a format of an array. So this array is nothing but in the format of an image. And now check the type of this particular M31 pixels that we have created. Now I have already told you that it's an array. Now how do you know it's a NumPy array? You can use this functionality of type and just pass in this M31 pixels. If I run this, it is a NumPy array. NumPy array, n dimensional array basically. Okay. Now what is the shape? It must be 300 by 300 by 300 as we had checked in the metadata. So let's even try to check that. M31 pixels dot shape. It must be 300 by 300. If not, then we are doing some kind of mistake. See, it's 300 by 300. The exact same thing that we had seen in the metadata, right? Now the next thing that we are going to do is to visualize this particular image. Now how we can do this? I can do this with the help of plt.imshow. In order to visualize any kind of NumPy array, any kind of array data associated with NumPy array, if you want to visualize it, you use this plt and then imshow. Now with respect to that, you give in the information of the array that you are trying to visualize. And you just hit run this particular code cell, and let's see what kind of output you get. This is the kind of output you are getting currently, right? By default, the color map that we are able to see this is Viridis. Okay, if I show you, CMap is equal to Viridis. So by default, Matplotlib is going to get this color map of Viridis. See, you can see there is no change because by default, color map that was used for this 2D image. 2D image means a grayscale image. Okay, so I can also convert this into a gray color if I want. Even that is fine, because this is the kind of some kind of similar output that we had seen over here. Now let me tell you that there is some kind of pixel scaling that has been done on top of this image. That's why you are seeing much more information as compared to this raw data we are seeing over here. And that's exactly what we are going to do in some of the upcoming videos. So stay tuned for that. But for now, what I'm really interested to show you over here is that our data is starting from 0 to 300, but on the y-axis, it's going in the opposite way. 0 is on the top. So we need to bring down this particular origin over here. So how we can do that? I can simply pass in the command of origin is equal to lower inside this imshow itself. So now if I run this, you will be seeing that now the origin is over here. And now this is the kind of the center that we are seeing over here. And how we can reveal a lot more other information, as you can see over here. Of course, I can give some of the input parameters, like, I can just change some of the input parameters while calling this image, get image. But I'm not going to do all that kind of stuff. I'm going to show you manually how you can try a lot of different ways of pixel scaling in some of the upcoming videos. Okay. Right now in this video, I just wanted to show you that out of these two surveys that we are going to use, how I can show you at least one of the surveys so that you are able to appreciate that yes, with the help of this Astro query library, we have imported this class called SkyView. From this SkyView, there was a method called as getImages. Now this is going to give us the fits file that is written with the help of AstroPy library, not AstroQuery, but AstroPy. Okay. Again, AstroPy is one of the library in Python, which is associated with this AstroQuery also. So with the help of that AstroPy, we are writing that fits file. So because it was in the format of a list, we are extracting this kind of list data and getting HDU from that. And once we got that HDU out of it, we are looking into the metadata and any kind of data associated along with that metadata. And for us, it was image in this particular case. It's not always image, just remember that. Over here, we were having the image data. We took a look onto the what type of that array was. It's a NumPy array basically. And we can check this kind of shape on top of that, that is 300 by 300. And also we have visualized this by shifting the origin to the lower, so that this kind of 0, 0 is matched. Now in some of the upcoming videos, you will be seeing that with the help of the pixel scaling techniques, how we can convert this kind of raw data into something like this. Okay. And along with that, I'm also going to show you in some of the upcoming videos in this module that how you can visualize this kind of overview. I'm not going to add any kind of color information. Okay. I'm not going to do any kind of that kind of color processing. I am just going to show you that with the help of this SkyView, how you can look into this kind of bigger output also, a zoomed out version also. Okay, so I'm going to give you all of this information in the upcoming few videos. So again, just stay tuned for that. Hey guys, welcome to this 7th video of module 3, and here I am going to show you one another survey with respect to which again we are going to fetch the data of Andromeda galaxy, but this time we are also going to tweak in some of the parameters so that we are able to not just see the core of the Andromeda galaxy, rather the overall galaxy that you must be seeing on the internet all over whenever you are searching for the Andromeda galaxy. So that's the kind of output that I'm looking for, not in terms of colors, but at least the image which is clearly showing you that yes, this is the Andromeda galaxy. So that's something that we are going to do in this video. So let's get started. So now that we were able to fetch this information of the Andromeda galaxy from the SDSSG optical survey that we were having, now we are going to go ahead and call this DSS2 blue and visualize the output in a much more zoomed out fashion as compared to what you are seeing over here. Okay, how can I do this in Python? Let's try to understand that. So again, what I'm going to do is, first of all, I'm going to copy this part of the code and come down over here and call this, but now at the same time I'm going to change this to DSS2 blue, right? Now along with that, now because I want to see the zoomed out version of this, I need to pass in further more arguments over here in the get images. So one thing that I can give apart from the position and the survey is the pixels. Now inside this pixels information, what all kind of things I can give? I can give, by default it is 300 by 300. I can, let's say, give 600, but now at the same time I'm also going to increase the radius of it so that we are able to see much more wider view of what we are seeing over here. Okay, over here also 600 by 600 is still giving us a little bit zoomed out version, but I want to expand the radius of this particular image so that we are able to see a lot more information in this 600 by 600. So for that I need to say, let's say for example 150. Now I need to convert this into arc minutes. Okay, I need to convert this into arc minutes. How can I do this? I can do this with this library called AstroPy that I talked about in the previous video. So from AstroPy dot, or I should say import AstroPy dot units as u, and this u, that is the units, will help us convert this 150 into the arc minutes. How? I'm going to multiply this into u dot arc min, that is arc minutes. And now if I try to just run this particular cell, okay, it's giving me some kind of an error. The spelling of pixels is incorrect, no problem. Now if I run this, I'm going to sort that out. It's going to take a little bit more time as compared to what we had seen in our previous video to fetch the HDU file, because it's taking a lot more pixels, and also the radius is very we have increased the radius, and therefore now if I go ahead and try to get only the pixels data from this HDU data, okay, and this is nothing but the M31 with respect to DSS2 blue pixels. And now if I try to just run this code and look into the shape of this M31 DSS2 blue pixels dot shape, it's going to be 600 by 600. But now just look into the magic. The moment I'm doing plt.im show of the same thing, giving the color map as gray, and at the same time I'm also doing origin is equal to lower. If I run this now, see, this is the kind of image that we are seeing. The same image that we are having over here, very similar to this. We are able to see that there is one more galaxy near the Andromeda galaxy. This is the satellite galaxy of the Andromeda. This Messier 32 is one more satellite galaxy to this Andromeda, and these galaxies are going to come and collide with the Earth, right, in some billion years ahead. and form a combination of Andromeda and Milky Way. We also call it as Milkomeda. There is this kind of name that we have given to this, when this kind of collision will happen between the Andromeda galaxy and the Milky Way galaxy, we will call it as Milkomeda and Milkdromeda, something like that. Okay, there are some weird names we have given. That is the combination of both of these galaxies. But anyway, see, now we have exactly got this data that we were looking into. I'm not going to add any kind of color information. Just look into the moment I have changed this kind of particular survey, we are able to get this kind of output. The whole Andromeda galaxy you are able to see over here. This is M Messier 110, this is Messier 32. All of this information we are able to see. Even over here, there is a star cluster. Even that information is visible. So we have done all of this with just one line of code over here. But now this is not what I really want to do. Obviously, we got all of these things. This is really very cool, right? But now let's do some of the image processing with respect to this core of this Andromeda galaxy. Now that's something that we'll be doing in some later part of the module. Before that, let me show you, because we are having a lot of information with respect to header information, even this kind of image information. If you want to create your own fits file, just like how these guys are creating this fits file, if you want to create your own fits file like this, how you can create it. After that, we'll be jumping onto all the kind of image processing and interesting stuff. Before that, this one part that I really want to show to the people who are really interested to know how this kind of fits file are made. So for that, just watch the upcoming video and you're going to get a good idea about how you can create your own particular fits file. Hey everyone, I welcome you to this 8th video of module 3, where I am going to teach you how you can create your own fits file. So obviously we don't have our own telescope that's going to capture all of this kind of things and get our metadata and also get the image. So what we are going to do is we are going to use the same header and the image that we have obtained in one of our previous videos of the Andromeda galaxy, use that as the dummy data and create our dummy fits file. Okay, so how exactly we can create it is what I'm going to show you in this video. And once it is created, we are also going to test it and see if it's working just fine as we expect it to work, right? So let's get into it. So let's try to understand that if you are having this kind of metadata information and this kind of image data information with you, then how you can create your own fits file just like how we had seen above. So for that, I am going to use this library called as AstroPy, just like what I had shown you in the upcoming, in the previous videos. That over here, the HDU file is in the format of astropy.io.fits. So to create your fits file, you need to import this particular thing in Python first of all. So that's exactly what I'm going to do in the first step over here. I'm going to say that from AstroPy, import, I should say from astropy.io, import fits. So now it's going to give me the liberty of creating the fits file, and you had seen that it was in the format of a list, right? Within a list, there was the HDU file that we were having, the primary HDU file. So we are going to take the same exact metadata that we had seen over here, right? And I'm going to store this metadata over here as, let's say, M31 header information, okay? And at the same time, we are also having the information about the pixels. So I'm going to add the same data into my separate HDU file that I'm creating, because obviously I'm not having any kind of existing metadata or the image data. So I'm going to use the same information to create a complete fits file from scratch. So for this, what I have to do, first of all, I'm going to initiate this kind of empty list that I'll be creating with the help of fits. And I can do this with this command fits.hdu list. It's going to help us store different HDUs within that list. And I'm going to call this as the HDU list, okay? Like this. Now the second thing is to create the primary HDU. The moment you are creating this empty list, you need to pass in some kind of HDU information. So the one that I'm going to create is the primary HDU. Okay, it's not DHU, it's HDU. And how we can do this? Again, I'm going to use this fits, but on top of that, I'm going to use primary HDU. Now what this is, okay, first of all let me show you what this is. This will be an empty list, and in this empty list I'm going to pass in this HDU file that I'm going to create. I'm going to copy this also. I'm going to paste that over here. So see, this is again an astropy.io.fits file. It's going to give us the primary HDU. But now what if I'm trying to, let's say, give this as some kind of a name called HDU1, for example. Okay. And now if I'm trying to look into HDU1.data, if I'm just doing this, it's not having any kind of information as of now in the primary HDU. It's completely empty. Even for the header, it will have some of the basic information that, like, it's conforming to fit standard, then it's a array data type, it's not currently having anything, number of dimensions is 0, right? So we are going to fill all of this kind of information over here with respect to M31 metadata, that is the M31 header, and in place of data we are going to pass in the pixel values that we were having. So let's try to do that. First of all, we are going to add the pixel data. How we can do this? We can say that HDU1 that we had created, because now it's a primary HDU, it's coming in with this functionality of data. And what is this data? This is the M31 pixels that we had created earlier. Similarly, like that I can also add HDU1.header. What is this M31 header that we just created a few seconds back? So now what I'm doing, I had created a primary HDU. In that primary HDU, I am adding some kind of data information. I'm assigning this M31 pixels to this HDU1 data, which was initially empty when I had showed you over here, right? And after that, I'm also filling in the information about the header, assigning this M31 header that we had gone above. Now, once this HDU file is ready, once this HDU1 file is ready, if I run this code now and I show this HDU1.data now it will have this kind of information. See, even the header information it will have, because I've assigned this kind of data to the HDU1. That's why now it is having the data. Now our duty is to pass this primary HDU into the list that we had created, that is going to finally create one fits file for us, right? It is having some list. Within this list we are having this HDU. So how you can do this? We know that we can add any kind of data to the list with the help of append function. So what I'm going to do is I'm going to call HDU list.append, and what kind of information do I want to add? It's the HDU1 information, which is nothing but the primary HDU that we had created over here. That's it. So our fits file is ready. Now in order to download this fits file or to write this fits file, what I am going to do, there is a functionality called as write to. Write to is going to help us finally save this fits file. So what I can say, let's say HDU list, that's the main fits file, right? A list. Within that list we are having the primary HDU. So HDU list, I want to write to this particular list as the fits file. We can call it as a dummy fits file, dummy fits file, and that is in the format of fits. So dot fits, right? So HDU list dot write to, and giving it a name this. If I run this code and if I look into this file storage, you can see that this fits file has been created for us. The same fits file that we were importing from the SkyView query, you are now able to save the same information into the fits file, and now you can also do a lot of different things with this. But right now that's something that I really wanted to show you, that if you want to create your own fits file, how you can do this with the help of AstroPy library. Now that we are creating this particular HDU file for the primary header, primary HDU, like this you can create extension headers also. If you are having the information, you just do a fits.extension header and you give some kind of data to it, give some header to it, and append that particular HDUs that you are creating in the HDU list. And then again do this write to for that list that you have created, and you will be having even the extension headers if you are having. Okay, So yeah, it's something that you really want to experiment by yourself. If you're having multiple header and its respective data information, so you can create multiple extension to the HDU file or the fits file. Okay. So now let's try to open this fits file that we have generated. How we can do this? I can do this with the help of fits.open. If you are having access to the fits file, you copy this path, you give this path as an input to this, where it went, it's over here. You give it in the format of a string. Let's say I'm calling this as some kind of again, let's say my fit, something like that. Okay, my fits is equal to this. If I'm running this, okay, let's look into this particular, let's say what is my fits. So it will be a list, and within a list there is this kind of HDU, primary HDU that we had created, right? So now what is present inside the first index of this my fits? Obviously this thing. So my fits of 0 is having what? It's having this kind of primary HDU file that you had created with the help of astropy.io.fits. Now if you want to check this header information, so you do my fits of 0.header. You could have also saved it into some kind of a variable called dummy HDU, and then you can check dummy HDU.header. Even that is fine. So you can see now there is a header. You can also do this for the data part, the pixels part, my fits 0.data, right? Again, now you can store it as a variable. Let's say this is dummy data variable, and I'm saving this data over here, and then I'm checking the shape of this dummy data variable dot shape. So because M31 was the SDSS from that particular survey, we had got that data. It's by default 300 by 300. So that's why we are getting that particular shape. And if you want to get the type of the variable, you do type of that dummy data variable. Check this. It will be a NumPy array, right? So as you can see, I've also cross-checked this particular thing the moment we were creating it, and even after creating it, once we are saving it, I am also importing it back with the help of fits.open command and checking all of this if it's working in a proper way or not. And yes, that's how you can create your own fits file if you are having access to the header information as well as the data information. So that was about how you can create your own fits file. Now in the upcoming video, we are going to talk about the pixel scaling that we were mentioning about before this particular video. And that's where the fun begins, guys. Hey everyone, I welcome you all to this 9th video of module 3, where I am going to show you the distribution of pixels with the help of an histogram. But before that, I'll also be showing you the summary statistics of these pixels that we are having of the Andromeda galaxy. And after that, I'll be showing you the visualization. So let's get into this video. So first of all, what I'm trying to do over here is to get the summary statistics of the NumPy array that we had created for the M31 pixels. What is this M31 pixels? If I just give you a very quick summary of this. So M31 pixels was the value of the image data that we had captured from the FITS file that we had seen for the Sloan Digital Sky Survey G-band. So from this we had fetched this particular information of the NumPy array, which is nothing but the array of pixels, which is eventually forming this kind of output. I'm going to set the color map is equal to gray, and also set origin is equal to lower for the same reasons that you had seen in the previous videos. And the output that you will be seeing over here is like this, a plain output which is just highlighting the center part of the Andromeda galaxy like this, but everything else is just black as compared to what you are seeing over here. This is a much more detailed output that we can see as compared to at least what we are having over here. So how we can get this kind of outputs? By doing what changes on the pixels, we can get this kind of output. That's something that we are going to look ahead to. But now for that, we need to understand what's wrong with this particular image. So for that, we need to do some kind of basic study on the pixel values, which is able to give us this kind of an output. So for that, we need to check the summary statistics of this particular pixels. So how we can do this? I'm going to simply use NumPy. That's the reason I have imported the NumPy over here which I haven't as of now. So import NumPy as NP. So yeah, now let's go ahead and try to print summary statistics of M31 pixels. And excuse me if my spellings are incorrect because I'm not good with them. But now the first thing that I'm trying to print over here with the help of f string is the minimum value that is present in this whole array of pixels. Out of all of this 300 by 300 image that we are having, where we are having, or I should not say where, but what is the minimum value of the pixel that we are having. So let's say minimum is np dot min of the pixel that I'm trying to find. I mean of the array that we are trying to find. If I just run this code, you can see that the minimum pixel value is 5.35 something, right? And just like this, because I want to find the maximum value also, what is the average value of the pixel, what is the spread of the pixel, I'll also be needing the maximum, mean, and the standard deviation values of this particular array. So after minimum, I'm going to look for maximum, I'm going to look for average value, that is the mean, and the spread basically over here is referring to the standard deviation. Okay? So don't worry if you are looking into this kind of terms for the first time, it's completely fine. STD. Now let's look into the overall summary statistics over here. The minimum value is 5.359 of the pixel. The maximum value of the pixel in this array of M31 pixels is 178. Now if you talk about on an average in this M31 pixels array, what is that value of pixel? It is 13.329 something. So on an average, the pixel values that you will be seeing will be more towards the minimum side. It's not exactly in the center. It's very much skewed towards the left hand side of the pixels, that is towards the minimum side. So if you want to get more sense of this particular data, we can also visualize this and look into the reason of why we are having this kind of 178, because minimum is 5.35 and the average is about 13 point something. Then how come maximum is 178 over here? So it could be there is some kind of noise that is present over here in this image. I can also prove you this with the help of what is the pixel value that is at the brightest spot that we can see over here, that is exactly at the center. Because remember that this kind of images that we are having is directly from the telescope who is focusing, or I should say which is focusing at the extreme center of that Andromeda galaxy. And with the help of the metadata, I can literally show you what is that reference pixel. Okay, so if I just scroll up, so over here now we can see over here, see X reference pixel is 150.5 and the Y reference pixel is again 150.5. So it basically means that this is the center which was focused by the telescope in order to generate this particular image. So that's where we expect the maximum value of the pixel to be there. So again, if you want to just cross check that part, you can do this with the help of M31 pixels located at 150, 150, because we cannot give any kind of float values over here to get the location of the pixel. So it is 148.5. What about 150? 1 and 151. Oops. Yeah, let's check this value. It's 126.5. So both of these values are again far away from 178. So it basically means there is some kind of noise that we are having in this particular data. And again, we can go ahead and visualize this. I can also first of all give this particular thing as a comment, as visual or printing the value of pixel at the center of Andromeda galaxy, right? So yeah, that's something that we are having over here. And now let's try to visualize the distribution of these pixels with the help of histogram. Now you can again create a histogram with the help of Matplotlib. So what I'm going to do is I'm going to say plt.hist for histogram. I'm going to give the M31 pixels to get the distribution of the pixels of this thing. So for example, let's say we are having 300 by 300 pixel values. Over there, whatever is the pixel that is present, how many times you were able to see this in the array. So that kind of distribution you will be seeing with the help of this histogram. Okay, now I guess there is some kind of an indent problem, so I'm just going to delete that part. Yes, and now after this I'm going to also give in one information called as bins. What is this bins? You will understand it in a while. Okay, for now I'm just giving a value as 50. But now if you remember, this is a 2D array. It's a 2D image. Now in order to quickly visualize this particular thing, I am just going to convert it into a 1D kind of format using this flat operation. So this flat on top of this NumPy array is going to convert this into a it's going to treat it as an iterator as a one dimension. So it's quickly going to help us visualize this histogram basically. Okay. If I don't use this flat command, it's going to take a lot of time to get us an output. So that's why I'm using this flat, and quickly we are having this kind of an output. Now if you look into this kind of steps that we are having, right, you can play around with these steps by increasing or decreasing this bins value. Let's say what happens if I'm just using 1. So this is the kind of output that we are having. In between 5 to 178, we are having just this kind of 1 bar. So if you want to have a lot of proper visualization, just increase the value of bin to, let's say, for example, 100. It's going to give you much more better distribution as compared to what you were seeing. And if you still want to get a refined version of this, you can still increase the bin values. Let's say, for example, 300. And now look into the output. See, again, output is pretty much similar. So I guess we are fine with this one. And now clearly we can see that this is like the pixel distribution is completely skewed to the left hand side. So clearly we can see that there were some kind of pixel values in the array, which is not appearing for a lot of time. So it must be some kind of noise. That's something that we are expecting, right? So this is the kind of observation that we were able to get over here. Now in the upcoming videos, you will be seeing what are some kind of different pixel scaling techniques through which we can transform this kind of pixels to some new type of pixels, such that in a hope we get a lot more better information from this particular output as compared to what you are seeing currently. So yes, that's exactly what we'll be doing in the upcoming few videos. Hi everyone, welcome to this video of module 3, where we are going to start our journey of pixel scaling with the first method that we have over here is min-max scaling. So to start with this video, I'm going to show you some of the helper functions that we'll be creating that will be eventually helping us to generate some visualizations for the comparison or just a normal image with some of the functionalities added to that particular function. After that, we're going to again create one more function that's actually going to implement the min-max scaling on the given input pixel array. And once this kind of output we are able to generate from this function, we are going to compare the visualization of the original image and the scaled image. So that's the whole idea that we're going to cover in this video. So let's get started. So the first pixel scaling that we are going to look into is the intensity normalization, or also called as min-max scaling or linear scaling. The idea over here is that we take the whole array of pixels, we do a subtraction with the minimum value that is present in that array, the minimum pixel value in that array, and then divide it with the range, or you can also call it as the difference between the maximum pixel value and the minimum pixel value in that array. And the output you get, the output of the array will be same shape, but now the values will be scaled down. So that's the whole concept of this intensity normalization, or whatever kind of thing you want to call it. And let's see how we can achieve this. So I'm going to create a function for that over here. I'm going to define it as let's say min-max scaling. And what input it takes only one thing, the main array of pixel. Let me just call it as pixel array, something like this. Now it is divided into two parts, numerator and the denominator. So let me call it as over here, numerator is equal to the pixel array minus the minimum value of this pixel array, and then denominator, let me just call it dn. What is this? It is the maximum value of this pixel array minus the minimum value, np.minimum of that pixel array. That's it. Now the output of this should be what? Again an array. But how? It's the division of this numerator and denominator. Simple as that. So our function is ready. If we are going to pass in the data of M31 pixels, it's going to give us the output in the format of min-max scaling. And we are going to hope to see some better information as compared to what we are seeing over here. We are not sure it will be better. We are just hoping that we get a better output. So coming back to this, what I'm going to do is, first of all, I'm going to create min-max scaled array, or I can just say min-max array, right? And I can do this with the help of min-max scaling that I have created on top of M31 pixels. And now before I go ahead and visualize this, what I'm going to do is I'm going to create a common function that will help us visualize this kind of output, because it's going to have some kind of common things, the title of it. Then once we are showing this kind of array, this kind of CMAP equal to gray, origin equal to lower, all of this kind of code will be repetitive. So for that, what I am doing is I'm just converting this into a function so that in just one line of code, we can do all of this task. So let's say I'm defining again one more function and calling it as, let's say, plot underscore pixels, something like this, right? So the first thing that I'm going to give is the pixel data or pixel array. After that, what kind of title I want to give, what kind of color I want to set for the title, some kind of this information. The first thing would be to display the array, that is pixel array, and keep the same color map, that is gray, always for now. And after that, I'm also going to set the origin to lower. And then I'm also going to do plt dot title, going to set title to the title that is given as an input, and also set a color to it. Color is equal to the color given by the user of this function. And also I'm going to use plt dot axis and turn it off so that the output is not giving us this kind of axis. Okay, we are just getting the output in the format of the image without the axis. Okay, it's going to look much more better, I guess. So yeah, that's something that I'm trying to do. And also after this, I'm trying to get plt.show to avoid any kind of external text information that it may display on top of the image like this. Okay, over here we did not use plt.show. So it is showing me this kind of output. I'm not really looking forward to this kind of things. So that's why I have given this kind of plt.show, and that's it. Our function is ready. So not every time after converting, after scaling down our pixels to some values, we don't have to plot this multiple lines of code. I'm just going to use this plot pixels, give the array of the pixel, change the title, change the color, and get the output. That's it. Again, I can do some more interesting thing. I can give the weight of this pixel as bold. And yeah, that's it. I guess this is fine. I'm just going to rerun this code. And because we have already created this kind of a min-max scaler, right? What I'm going to do, I'm going to plot pixels for min-max array. Now the title I'm going to set is min-max scaling. Color that I want to give to this is royal blue. And yeah, that's it. So let's see what kind of output do we get by just, okay, I guess we are having some kind of an error. The error says that the text.set got an unexpected keyword called weight. The spelling of weight is incorrect. Again, don't mind my spelling, guys. I'm really poor at spellings. Let's run this. I'm going to run this again. Yeah, it's giving us this kind of an output. Now, again, what I'm trying to do is I'm trying to compare this with the original image over here, right? So what I'll do is I'll also create a comparison over here. Okay, I'll be creating one more function to compare the scaling. So compare pixels. It's going to take two data: original M31 data, original array. At the same time, I'm going to give scaled array. Okay. And I'm going to create a subplot over here, plt.subplot. So the first subplot that I'm going to give is 1 to 1, 1 row, 2 columns. On the first position, I'm going to plot the original array. And I can do this with the help of the above function that we have created, plot pixels. I'm just going to remove this plt.show as of now. I'm going to have plot pixels, and I'm going to first of all pass in the original array, right? And after doing this, I'm going to have multiple titles over here. So for the first one, I'm going to give the title as title as original image, and I'm going to give color is equal to black. Okay. And after this, I'm also going to use subplot at 1, 2, 2. Plot pixels, I'm just going to copy this whole thing and paste it over here. And it will be the scaled array. The title will be, let's just keep it a title over here as title only. Okay, I'll be passing the title, whatever is the title that I'm trying to give. And again, the color will be just a color. I'm just going to give this as an input, and let me create this kind of thing. And now let me try to compare these things. So what I'm going to do is I'm going to scrap this part, and instead I'm going to I'm also going to do plt.show at the end. Plt.show. Okay. And now if I come over here and do compare, what was the name of the function? Compare pixels. The original data is nothing but the M31 pixels. The output is min-max array. Then the title of this plot that I want to set on the second one is the min-max scaled. And the color that I want to give to that is royal blue, let's say. Or I can also fix this color over here as royal blue because that's the only one that I want as an output. So I'll also remove this part over here. And now I can just give this as this only. And hopefully it gives us the output the way we want. Yes, so this is the kind of output that we want in terms of comparison. Now, because we are having some kind of gappings in between, I can improve this kind of gaps. I hope you know the command. The command is nothing but plt.tightLayout. And I can also adjust the figure size if you want to have a larger size of this image and any kind of that kind of thing. But I guess I am satisfied with the output that I'm getting. On the left, we are having the original image. On the right, we are having the min-max scaled image, right? So over here, I don't see that major difference over here. It's pretty much similar. So we didn't get any kind of useful information with the help of min-max scaled output. Now in the next video, I'm going to show you one more type of scaling called as standardization or Z scaling. And it has been done with the help of this formula. So I'll explain you this whole concept in the upcoming video. Hey guys, I welcome you all to this video of module 3, where I am going to show you some other pixel scaling methods apart from the min-max scaling, namely standard scaling, log and square root normalization. So once we are done getting the outputs of this scaled version of the M31 data, we are going to visualize them by utilizing the functions that we had created in our previous video, and then just compare out of all of the scaling methods, which one is performing best in terms of visual appearance, which is revealing most information about the core of the Andromeda galaxy. And then we are simply going to take that output, which is revealing the most information, and get its pixel distribution with the help of the histogram, just like how we did in one of our previous videos, right? So yes, let's get started and look into all of this kind of things, guys. So let us understand this particular formula. What is this about? So this is the actual array. We are subtracting it from the mean of the array and dividing it with the standard deviation. So now you already know how we can take this mean and standard deviation. That's what we had seen in some part of codes earlier, somewhere over here, see. So we're going to use this kind of NumPy functionality in order to get a standardized output. Okay, the kind of technique we call to this particular formula that you are seeing is either standardization or Z scaling, whatever you want to call. So if you have studied normal distribution, you will be understanding the actual meaning of what this is. But let me not go into the very technical concept and talk about Z scale array or Z scale, only just Z scale. Let's just say that this is Z scale. again I'm going to give pixel array as an input, and the way that I'm going to code, again I'm going to have a numerator, that is the pixel array, the whole array. I'm going to subtract the mean of this pixel array, and the denominator part is just the standard deviation. So again I'm just going to have this kind of denominator as np.std, standard deviation of that pixel array, simple as that, and written numerator by denominator as an output. So our function is ready for the scaling, and the output that we are going to visualize now will be straightforward. So scaled array, or I should also call this as z scaled array. Z scaled array is equal to z scale on top of m31 pixels. And now if I just go ahead and call compare pixels on m31 pixels, okay, again now see, because this m31 is common, I don't want to give this input again and again. So I'm just going to give in the scaled array only as an input. I'm going to keep this as m31 pixels by default. Okay, I'm not going to change this one, it is always the same. So I'm going to run this code, and even in this image I'm just going to take this part out, run this part. Yes, and now I'm going to do the exactly same thing over here. I don't need to pass m31 pixels over here now anymore. I just need to pass in the z scaled array, and the title will be let's say z scaled image. Let's see the kind of output that we get. I guess we have created an error. The error is num.den. Okay, yeah, it's because of this particular thing. No problem. Let's fix that up. Hopefully no errors this time. Yes. Again, not a lot difference that we are expecting over here. Even with the help of z scale output, it's pretty much similar to what we see in the original image. Don't worry. It's not that we aren't doing anything perfectly, or there is some kind of a problem with the scaling techniques. This is pretty much obvious. Okay, at times you won't be able to see a lot of difference. But now the next thing that we are looking into is the log normalization. What is this whole concept of the log normalization? You take the log of all the pixel values that you are having in your data. Simple as that. So now what I'm going to do is I'm going to create a function for that, def log normalization, or normal log scaling, whatever you want to give. Input is the pixel array, and it's going to simply return the log, np.log of this input pixel array. Simple as that. So this is the array that we have created, and if you want to visualize this, so log norm array is equal to log normalization of m31 pixels, and compare pixels of log norm array, title is equal to log normalized image. Now you will be able to see some of the visual difference as compared to what we were having in the initial image. Now see how we are getting this particular output. We are seeing a lot more details, some kind of part that we see in the around the core of the Andromeda galaxy. All of these things are now visible. This is the center part. This is what we see, which is not visible over here. See, that's the power of, like, scaling your particular pixel values to some different scale, right? Right now we have implemented log on all the pixel values with the help of np.log. Now if I just compare this with this output, see how well it is able to give us this kind of outputs of all this kind of, if I show the stars over here, right, all this kind of information. See, even over here I can see that the output is revealing much more information, but yes, we are having this kind of output so far that we have achieved. Now on top of this, there are again some more normalization and scaling techniques that you can do for sure. But now before that, what I'm going to do is, because we got a slightly better output over here, I'm going to create a histogram distribution of the pixels of this particular output. Okay, how can I do this? I'm going to do plt.hist of this log norm array dot flat, going to, let's say, set bins to 300 and look at the output with the help of plt.show. Okay. So see, now this is the kind of output. The spread in the data is much more as compared to what we were having initially, and this is the kind of output that we have achieved so far. Okay, and I can also show you the shape over here. That is log norm array dot shape. It must be the same. Okay, that's something that I wanted to show you, that the shape is just the same, right? So over here we got the I guess the log normalization was already done, so I just got the image of the log distribution of the log normalization over here, and that's what we had to do over here. So I'll just scrap this part, but at the same time I'm trying to show you one more type of normalization. Let me just call this as the fifth part of this scaling technique, square root. Okay, so what I'm going to do over here is I'm going to create a code, two code cells, one to define the square root function. Again, I can do it with the help of NumPy. So def, let's say square root scaling, giving the pixel arrays, and it's going to return this thing, np.sqrt of pixel array. That's it. Going to run this. I'm going to create a square root scaled array or square root array, just like that, and I'm going to call sqrt scaling on top of this m31 pixels, and compare pixels, and I'm going to compare this with square root array. Title will be square root scaling. Let's see what kind of output do we get. So this is the kind of output. This is one more way. You can see that there are some more information that has been revealed over here, right, as compared to what we see on the left. So just like this, there are a lot of different scaling techniques that you can use. So far we had seen that a lot more information we were able to get with respect to the log normalization. So we stick with that and said that, like, let's create a histogram out of it, a histogram distribution of it, and that's how we can see how the pixel values are distributed now, right? So yeah, that's something that I really wanted to show you, that with the help of this pixel scaling, how you can reveal a lot more information like this. Now in the upcoming video, what you will be seeing is one more technique which is called as a Z-scale interval. Okay. Now with the help of this, again I'll be showing you some more information, and then we are going to use any of the scaled output and perform some of the image processing techniques as we go ahead in this particular module. So stay tuned for all of this kind of interesting things coming up for you guys. So welcome to this last video of module 3, where I'm going to talk about the Z-scale interval class that is present in the AstroPy library. Okay, so what is it all about and why are we using it? All of these things you'll be seeing in this particular video. So let's get right into it. So now let us discuss about the Z-scale interval. I'm not going to go into the logic behind, like, how this is coming up with. I'm just going to tell you what it is going to do and how it can be useful for us. Okay. So for the demonstration purpose, let us try to create a demo array. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. Now the whole idea of the Z-scale interval is to give you an interval. That means give one minimum value and one maximum value. So let's say mean and max. Now this mean and max are not 1 and 10. There are some different values that you will be getting. For example, let's say minimum we got as 3 and the maximum we got as, let's say, 8. Right? Now the whole idea over here is to take this original array and clip it according to this particular interval. Any values in this array that is less than 3 should be converted to 3, and any values that is greater than 8, beyond 8, should be converted to 8. That's what we call it as a clipping of an array between a particular values. So now because we know that the minimum value this array can take is 3, so wherever you see any value less than 3, convert that to 3, convert this to 3. Similarly, if you are seeing a value greater than 8, convert that to 8, convert that to 8, and that's it. Once we are done with this kind of conversion, we are having a whole new way of visualizing the respective image that we'll be creating. So we are going to follow the same exact process, and the way through which we can do this in Python is with the help of AstroPy library. So what I'm going to do is, from AstroPy, there is a module called as visualization. So I'm going to call visualization, yeah, import Z scale interval. I'm going to run this code, and now I'm okay. I guess there's a spelling. Oh no, not a spelling mistake. There is a problem with the space over here. Yes, it's working fine. So now we are going to create the object of this particular class, Z scale interval. And what is the whole idea of creating this object? Because this is the object through which you will be able to fetch out the limits on the any of the image that you want. Okay, in our case, you can choose, let's say for example, square root scaling, original image for that matter. I can also choose this kind of log normalized image. Because this was performing the best, I'll be simply copying this part and go down, and I'll be simply calling this kind of limits with the help of Z scale interval on top of this particular array, right? Now how we can do this particular thing? You call this Z, you press that dot, it's going to give you this particular method called as get limits. So it is because of this object that you have created of Z scale interval, you are getting access to this method. Now this method takes the array whose minimum and maximum value you want, that you have got with the help of Z scale interval technique. So if I'm having this over here, and if I know that it's going to return two things, minimum and maximum, so let's call Z1 as minimum, Z2 as maximum. So we're going to get some kind of outputs, and let's just check it with the help of print command. F string, let me just say that minimum is Z1, and like that print F maximum is equal to Z2. If I run this code, so the output that we are having over here, the minimum value after clipping we should have is 1.6889. okay, we haven't clipped as of now, but the minimum value after applying the clipping should have 1.6889, nothing less than this. So if I show you in the original array of log norm array, what is the minimum value? np.minimum of that array. If I'm just running this, okay, it's saying that, oh yeah, because we haven't defined y, not array, it's array. Anyways, so yeah, the minimum value that we are having in the log norm array is 1.6788, and after implementing this get limits on the Z scale interval, we got that the minimum value should be 1.688. so obviously we can see that there are some values which are less than this. So all the values in this array that we are having for the log norm array, all of these values including this will be converted to 1.6889. Any values less than this will be converted to that. And just like that, if I try to see the maximum value, and if I run this code, it is 5.1817837. And over here, after implementing the get limits of Z interval on the log norm array, the maximum value that we are getting is 4.4479. So any values beyond this, as we can see clearly that yes, there is at least one value that is beyond this. So any such values present in this log norm array, we want to convert it into all 1.5, 5.1817, all these kind of values that has been written, right? So yeah, I was trying to print this to show you that this minimum and maximum is not equal to the minimum and maximum pixel of this particular array. It's different, right? So now that we are having this kind of an idea, let's try to visualize this data by clipping this array of log norm array. How we can do this? I can use plt.imshow, and now over here I'm trying to call this log norm array, but now I'm going to use two different parameters which is going to help me clip the values between these values. So vmin is the minimum value, that is Z1, and vmax is the maximum value, which is Z2, and cmap, as you know, is our gray, and the origin is equal to lower. We know this kind of settings, we have been using this since the start of this notebook. And now I can simply do plt.show. Hopefully the code works without any kind of error. And now the output that you will be seeing will be significantly different than what you have seen over here. Okay, you can see this, it's kind of a blurry kind of thing, bit faint kind of thing. The stars are not that highlighted. Even this kind of the center part of the Andromeda galaxy is like this. Now just look into the output that we get over here after applying the Z scale interval. See, it's a bit more highlighted, right? You are having a much more brightness in that part as compared to the smaller part. So now this is the kind of output that we are having. Okay. It's not that you need to specifically apply this method. It's just that I'm trying to implement one more method so that you guys know that this kind of techniques also exist. Okay. What have I done? I just got two values, the limits. Now from the help of this limits, I have clipped my array. I haven't done any kind of transformation as such. Just clipped the array such that any values less than that particular value and any value beyond this value are converted to its respective values. That's something that I have done, and this is the kind of output that I have achieved. Now, according to your research, according to your whatever is the objective, the problem statement that you are working with, you come up with a specific technique and you carry forward your any kind of image processing or any kind of information that you want to with respect to whatever you are comfortable with. It could be this square root scaling image, it could be original image, it could be this log normalized image and not this one specifically, right? It's completely your choice according to the problem statement. Now, because I want to demonstrate something in the upcoming videos, so what I'm going to do is I'm going to take any one of this image, let's say this particular image that we got over here. But now, is this an image? Yes, it's an image, but what is the pixel representation of this? If I am trying to clip this particular values, I haven't clipped log norm array over here, right? I am using this IamShow in order to clip these values with the help of these arguments. So now how can I convert this into NumPy array or any kind of array? So for that, I'll have to store this whole image as a variable first of all. And now let's try to visualize what kind of output it is giving us. Okay. It is the Matplotlib's image. It's not a pixel representation. It's an Matplotlib's image. So it's not giving us any kind of array over here. So how we can convert this image into its pixel representation? I can do this with the help of a command called as make image. Okay. Now one input that it takes is called as renderer, renderer. Now I am going to choose by default whatever they are having in the backend of Matplotlib by simply giving the command of none. Okay, now I'm going to run this. It's going to give us the 8-bit integer form of image. So from this kind of float 32, we are converting this into unsigned integer 8-bit image basically. Right? So this is the kind of output that we have got. But now along with this output, it's throwing some other things also out. But we are just carrying for the first part of the output, that is the image array. So I'm going to extract this first part that is present on 0th index. And now this is the array that I'm looking forward to. And you can see that it's a D type equal to uint8, unsigned integer 8. Right? So that's something that we were looking forward to. And now let me just store this into an array, image array, let's say. And now let me go ahead and try to check the shape of this. So image array dot shape. It is 370, 370 and 4. Original shape was 300, 300, that's it. So we need to think about this. We need to convert this into 300 by 300, not this shape. So first of all, how did we get this 370? So over here, I just need to pass in one more argument called as unsampled is equal to true. Now by using this particular command or argument unsampled is equal to true, it's going to keep the dimensions as it is. If I run this again and again run this particular code, you will be seeing that 300 by 300 has been achieved, right? So we have decreased our shape back to 300 by 300. That's something that we wanted. Now what about this 4 channels? What it means? So 4 channels basically mean, let me just write a note over here. So the 4 channel basically is indicating to us that it is having red, green, blue and alpha channels, makes up a 4 channel image. Typically, if it's in the format of RGB, so the first 3 channels will be RGB and the last one will be alpha channel. Now what is alpha channel? It is with respect to the opacity of the image. Okay, the values again are in between 0 to 255. 0 means completely opaque and 255 means the opposite of that. So yeah, that's the idea with respect to the 4 channel output. Now how we can convert this 4 channel output into only one channel, that is grayscale. Now that's something that we are going to look into with the help of CV2 library, which is nothing but the OpenCV library. I can import it with the help of import CV2 command, and by default it is already present in the Google Colab, so you don't need to again install it over here. So I am simply using this command of import CV2 and importing my OpenCV library over here. Now how we can remove the 4th channel of the opacity, and basically just convert this into and convert it into grayscale. Okay, I should have written remove 4 channels, or just um, convert 4 channel image to grayscale image. Now how we can achieve this with the help of CV2? So in OpenCV library there is some method called as CVT color, right? Now the input that is it's going to take is the image array whose channels are 4. So I'm going to pass it over here, and along with that it's going to take a flag. What is this flag? The flag that is going to convert this 4 channel image into a grayscale. Now by default in CV2, that is OpenCV, it's not going to read as the first channel as red, second as green, third as blue. It's going to be the opposite of that. On the first channel we will be having blue, on the second it will be green, and on the third it will be red, and then on the fourth it will be alpha. So it's BGRA, this 4 channel. If you are using CV2, right, so if you're using CV2, the 4 channel will be in the format of BGRA, and now that BGRA needs to be converted to gray. I can do this with the help of cv2.color underscore BGRA to gray. That's it. And let me just store it as gray image, gray array. And now let me just go ahead and cross check if the shape is correct. Hopefully it is. Yes, it's correct. And now just to visualize if we have lost some information, or it's just like what we are seeing over here, let me just again plot this thing. So I'm going to plot it with the help of the plot pixels function that we had created above, right? It's going to take in the input of the array, that is the gray array. Then I guess it was taking the title also. Title would be, let's say, Z scale interval grayscale, let's say something like this, and color, let's say, is royal blue. Hopefully this is not giving any errors. I hope that these are the parameters. Okay, we got an error. So error is TIT. Oh, never mind. TITLE is the spelling. Yeah. So this is the output that we have got, and it's just the same image that we were having over here. Exactly the same. Right? You can also try to plot it side by side with the help of that comparison function that we had created. But anyways, I am happy that yes, the output is just the same, and we are going to carry forward with this particular thing, right? The gray array, right? That's the kind of conclusion that we have made so far. Now let's also look into the histogram visualization of this. So plt.hist, going to pass in the gray array, and use flat to convert it into an 1D iterator, and then pass in the bins is equal to usual as usual 300, and look into the output. As you can see that we are getting some kind of a display of array. I'm just going to use plt.show, and it's going to just show me the output of the image, nothing else. So now this is the kind of output that we are able to achieve, and the pixels are ranging from somewhere from 0 all the way up to 255. Why? What is the reason behind that? The logic is that because we have converted our float image into 8-bit image, and in 8-bit image, as I had explained earlier, the values are in between 0 to 255. So that's the reason why we are having this particular range, right? So yeah, this is the histogram visualization that we are having. And now, in order to apply any kind of image processing on this particular image, what I'm going to do is I'm also going to convert this grayscale array into some good name so that we can use it further. Let's say I'm giving some unique name to it as grayscale or grayscale z interval, z int array is equal to gray array. So I'm just giving a meaningful name to this because we were just doing some kind of experimentation over here, and because everything is working fine, so I'm just saving it in a very good name so that we can use it in the upcoming videos, right? So the whole idea that we have seen over here is that with the help of z-scale interval, we got two values for the interval, and we use this IM_show in order to clip the value between these two values that we had got, z1 and z2. So from this, we stored it into this image variable, which was nothing but the Matplotlib image type. So from that, we converted it into its pixel representation using this particular function. We give these two inputs, we fetch the array part of it, and the output will be 8-bit integer image. But the output now was having 4 channels. So whenever you are trying to perform the image processing, and because see, the output is just the same over here and over here. So why take 4 different channels and perform image processing on that? It's going to take much more time as compared to what it will take in only one channel. Output is just the same. So that was the whole concept why we took these 4 channels and converted it into single channel or gray channel image, right? And we did it with the help of computer vision, or I should say OpenCV library, CV2 library. In the CV2, we are having this option of CV2 color, CVT color, which is helpful to take the image array. And with the help of this flag BGRA to gray, we can convert it into grayscale image. If you want to, let's say, convert it into 3-channel image, you use BGRA to BGR. Even that is fine. But now that will be 3-scale image. 3-channel image. Because eventually we wanted a grayscale image, I directly converted that 4-scale into 4-channel into 1 channel. And here is the proof of that. That has been converted successfully. And yeah, here is the final output that we have got, and here is the pixel distribution of this in between 0 to 255, right? So yes, with all this being said, we are done with this whole idea of pixel scaling and looking into some different ways through which you can come up with an array, and finalize something that we are going to use for the upcoming sessions on, or I should say upcoming videos on image processing after doing some kind of pixel scaling on this, right? So stay tuned for that, guys. Hey guys, I welcome you all to this last module of this program, where our focus will be to understand how we can implement some different type of filters on the existing image and get some kind of features extracted out from that particular image. So starting with, we'll be understanding the concept of the convolution operation. Then we are going to take one image from our previous module and apply the Gaussian denoising technique with the help of Gaussian kernel to remove some of the noise in the data. After that, we are going to implement measuring and Sato filter in order to enhance the features in the image. And lastly, we are going to use some of the features of the SK image library, where we are going to take corner, Forstner and multi-basic features to extract this kind of features with respect to this algorithms, how this kind of techniques are working. Everything will be covered in this particular module, guys. So yes, without any further ado, let's get into this module. Hey everyone, welcome to the second video of module 4, and here we are going to learn about the convolution operations. So what exactly are these convolutions? Why do we need it over here? And then what is some kind of practical demonstration in terms of visualizations so that you are able to understand, okay, yeah, that's exactly what is convolution. So that's something that we are going to cover in this video. So let's get right into it. So now that we are aware about that, we are going to use this particular image in order to get some kind of features out of this image and do some cool stuff in the upcoming videos. One thing that we need to do is to remove any kind of noises present in this image before we actually go ahead and get those kind of features out of this image. So we can do this with a technique called as Gaussian smoothing, which is nothing but denoising the image with the help of Gaussian smoothing technique. How it works? It is simply working on the principle of convolution. So how this convolution works? So it will require one kernel. You can also call it as a filter. In our case, it will be a Gaussian filter. Right now, this is just a demo filter just to explain how the convolution works. And it will also require one image. Now this image in our case will be this one image. So on this image, we are going to place our Gaussian kernel and do some convolution operation, then slide that filter one unit to the right, do convolution operation, again slide it to the right, do that convolution operation until you are sliding across every pixels step by step. Now that's the whole idea of the convolution that you are going to perform with the help of a Gaussian kernel on the full image. So let us try to understand with this GIF that I'm having over here. This light blue part that you are seeing is the image. It's a 5 by 5 image, as you can see. Now on top of which we are going to pass this kernel size 3 by 3. Okay. So now what is the convolution? So wherever you are seeing 0, I am going to pass this 0 of this kernel on top of that. Now wherever this is a second 0, I am going to multiply that with -1. Then this 0 will be multiplied with this 0. Then this 0 will be multiplied with -1, 60 will be multiplied with 5, 113 will be multiplied with -1, 0 will be multiplied with this 0, 73 will be done multiplied with -1, and 121 finally will be multiplied with this 0. After multiplying all these numbers, I am going to sum them up together. And that summation output is nothing but the thing that you are seeing over here as an output. Right? So if you want to visualize what I'm trying to say, I have already written this particular thing for you. That you do 0 into 0, then 0 into 0, like 0 into -1. Just map these values of the kernel on top of this first 3 by 3 part of the image. Multiply its respective elements which are coming on top of each other. And after multiplying, simply add them up together. You will be ending up with the value called as 144 for the first place. Just like that, you slide your kernel by 1 unit to the right. And now it will be on the 0, 0, 0, 60, 113, 56, 73, 120, 154. Again to the same process. The output will be 328. So one time if you are doing this, that is one convolution. Like that you are going to do multiple convolutions with this kernel on top of this image. And you are going to finally get the convoluted or convolved image with the help of Gaussian kernel. Right now, as I mentioned, this is a dummy kernel to give you this explanation of how these things work. But yeah, that's the whole idea of convolution operation. In our case, this light blue kind of thing that you are seeing is nothing but the original image that we had stored over here. This will be the image on top of which we are going to create a Gaussian kernel. How we can create it, what are its properties, we are going to discuss about that in the upcoming video. But yeah, that's the whole logic. But now you might be wondering that what is this kind of 0, 0 on top of this, right? So whenever you will be implementing the convolution operation, you will always decrease the size of the output. Now to keep the same size, that is like 5 by 5 over here as an input, we also want the output as 5 by 5. So for that specific reason, I am adding a layer of padding. And this padding is nothing but a 0 layer padding. It means all the values over here are 0, 0, 0, 0, 0. Now there are other ways through which you can fill up these values. You can also use this kind of a reflect kind of padding, which means that this 85 will be reflected over here, 128 will be reflected over here. Let's say this 131 will be reflected over here. So even that kind of thing is possible. So in short, there is one padding layer. So if we are having a padding layer, this image size will be what now? It will be 1, 2, 3, 4, 5, 6, 7. So it's a 7 by 7 thing. So from that 7 by 7 thing, after the convolution is over, you are getting this 5 by 5. However, the original image was 5 by 5. So eventually what we are getting is that input was a 5 by 5 image, output is a 5 by 5 image. So for that particular reason, we are having a padding layer. So I hope the concept of padding is clear. At the same time, what you are seeing over here, that the sliding of this kind of kernel on top of the image, different part, this sliding is called as a stride. This is called as a stride, stride. So over here we are having the stride value of 1. That's why it is moving one unit to the right and then 1 unit to the down. If the stride value was 2, it will skip 2 columns and then start from this particular. Then again skip 2 columns and start from the next particular available part. So that's how it's going to work. Alright, so yeah, that's the concept of padding and strides that is associated with the concept of convolution. Now, in the next video, you will be seeing that how we can create a kernel for a Gaussian smoothing and apply it with respect to the image that we are having over here. And then denoise this image, and after that later on how we can implement some of the filters or some of the feature extraction techniques to get something out of this particular image. So stay tuned for that, guys. Hey everyone, welcome to this third video of fourth module. And now we are going to discuss this concept of Gaussian denoising as in terms of implementation. I'm going to take one of the image from the output of module 3, implement the Gaussian kernel on top of that, and see how the output looks like after doing this kind of convolution operation. So for this, you will also need to understand what are the properties of this Gaussian kernel. Only then you will be able to appreciate this whole idea. So this is exactly what we'll be discussing in this video. So let's get into it. So basically this convolution operation with a Gaussian kernel applies a weighted average to the neighboring pixels with the higher values at the center, which are gradually decreasing towards the edges of the filter. So the filter that you are seeing over here won't be like this. It's a very special type of filter where the values in the center are high and at the edges the values are going to be low. Okay. So this process is effective in reducing the high frequency noise and preserving important image details. So how we can create this kind of a filter and then how we can do this kind of convolution operation on that image that we are having over here. So let's try to understand that part. So we will require the convolution 2D filter from the SciPy's signal module. How we can do this? I'm going to say that from SciPy. SciPy is again a library that is pre-installed over here in the Google Colab, so you don't need to install it. So from scipy.signal, I am going to import convol 2D. And after this, I am going to generate my own filter that is not at all associated to the Gaussian filter. And the way that I'm going to create this is with the help of np.ones. Now, what is the whole purpose of the np.ones? So let me first of all explain that to you. So np.ones, if I'm let's say doing it 5 by 5, okay, I'm passing it inside a tuple. So what is this going to be? So it's a 5 by 5 of ones. Now I am just going to divide all of these values by 4. Okay. Or I should say 25, not 4. Why by 25? So that the summation of all of these values is equal to 1. Now by doing this particular thing, it's going to preserve the range of the pixels in a way that it's going to be a better output basically whenever you are having this kind of summation equal to 1, right? So that's the reason why am I dividing this with 25. So because I'm having 5 cross 5 of ones, so total in short the summation is 25, right? There are 25 times 1 in the array. So that's why I'm dividing this with 25, so that now if I take the summation of all of this, the output will simply be 1, right? So that's for that specific purpose I have done this thing. And now let me just store it into kernel. Kernel is equal to this. Okay. Now let's go ahead and actually we have already looked into that, but still I'll just paste it over here so that yeah, you are having the output. Now we are going to create a Gaussian kernel. So let me just give a name to it, Gaussian kernel. I'm going to create it with this np.array method. Now what I am going to pass over here, I am going to pass this kind of values, 1 by 16, 1 by 8, 1 by 16, then come to the second row, and now in the second row I'm having 1 by 8, then 1 by 4, again 1 by 8. You try to look into the pattern that I'm trying to create over here, okay? And the last line again will be very similar to the first line, or I should say exactly the same. 1 by 16, 1 by 8, and 1 by 16. Now as you can see that in the center part we are having the maximum value present over there, and as we are going to the edges you are seeing that the values are even smaller. So now this is going to follow the property of the Gaussian kernel, and even the summation will be equal to 0 if you are going to go ahead and check it. Okay, and even you can check it with respect to the graph that we are having over here, that in the center we are having 1 by 4, and at the edges we are having the values of 1 by 8 and 1 by 16, right, as you can see. So this is a 3 by 3 kernel that we have created. Over here I have created 5 by 5. Again over here, if you want to create a 3 by 3 kernel, you can create it by simply doing this 3 by 3 over here also. And now because 3 by 3 in total there are 9 values, so I need to divide this by 9 in that case. So even this is fine. Okay, there is one kernel that we have created like this, where it is 3 by 3, so the output of this will be a total of 9 ones. So the summation of that will be 9. So I just divide that with 9, so that overall summation of all of these values will simply be adding up to 1. So I have created two different kernels, one that is a simple kernel and one that is the Gaussian kernel. Now I am going to show you how we can convolve this with the help of a con2d thing that we have imported from scipy.signal, and show how the output looks like with respect to this kernel and the Gaussian kernel. And again we are going to see it in two images, one that is the M31 pixels by default, and the second one is this particular image. So let's try to go ahead and visualize it. So get the convolution done with our normal kernel. Now how we can do this? We can simply call convolve 2D. Now what kind of input it takes? It takes the original image, on top of that it takes the filter, and after filter it takes some kind of padding, right? So I'm going to say that M31 pixels is the first thing that I want to choose, and then the normal kernel I want to give as an input, and the padding I can give with the help of the command mode. Now this mode I'm going to keep same padding, means the shape of the output should be same as the input. That's what this means. Okay, and this will be the output of the convolution. So let's say we call it as convolved image, and we are storing in this, right, and we are running this now. And the same thing we are also going to implement with respect to the Gaussian kernel. So Gaussian kernel, exactly the same steps have been repeated. There are no changes at all. And now I'm simply going to visualize both of this output, one with the convolved image and one with the let's say, because I have given the same name over here, let me just call this as Gaussian convolved image, but I guess there is a problem. Okay, let me check what is the kernel that I have selected over here. Let me just run this code. I'll copy this, come over here, paste it again just in case to check if the spelling is correct, and now I'll run this. So yeah, we are having two images, and now we are going to first of all visualize the first convolution output. So I'm going to do plt.imshow of the same thing, right? So I'll be using the plot pixels, and what kind of input I want to give? This is the input. Title is normal kernel convolution, and color should be, let's say, maroon. So this is the kind of output that we are able to see right now in the normal kernel convolution, right? Now what I can do is I can also go ahead and visualize the Gaussian kernel. I'm going to copy this code. See how useful that kind of function is that we had created. In only one line of code, we are able to get all these things done. And now this is Gaussian kernel convolution. So now again, as such, we are not able to see that level of output. You can see there's some kind of some kind of circles you are able to see over here. And similarly over here also you are able to see a similar kind of output, right? Over here, because we are having some information, maybe it's done in this particular way. What about this image? Yeah, over here also it's done in that same fashion. So as such, we are not able to see any kind of such difference. Now what I'm going to do is I'm going to do the same thing on the grayscale output that we had created over here. This one. I'm just going to copy this. Come down. Using grayscale to convolve and this grayscale z int. Going to convolve 2D. Going to pass Gaussian kernel. Keep the mode is equal to same. And I'm going to store this into some kind of output. What kind of output we can give? Just try to think about that. Let's just say convolved grayscale, right? Let's this. I hope the spelling is correct over here. convolved. It seems correct. Let me just run this. Convol 2D. Never mind. You know my spellings. Convol 2D. I'm going to copy this. Going to paste it over here. Okay. Now let's see how it looks like. Again, I'm going to copy this, paste it, and now I'm going to copy this name, paste it over here, and give it as Gaussian kernel convolution, Gaussian kernel on Z scale interval. Let's see how the output looks like now. So this is the kind of output that we are having as compared to the original image. Okay, as compared to this image, this is the kind of output that we are having. So if it is having some kind of noises, it has simply removed it by adding some kind of a blurring effect, right? So yeah, this is what we have done so far. Now we are also going to fetch out the histogram before we go ahead and implement any kind of image processing techniques in terms of applying filters and feature extraction techniques. So plt.hist on this particular output, that is the convolved grayscale. I am going to pass dot scale and bins is equal to not scale dot flat and bins is equal to 300. Plt dot show. Let's see now the distribution of the pixels that we are able to fetch after doing this kind of convolution with the Gaussian kernel. So now this is the kind of output. See, this is the kind of output that we have got from this. From this, you can see there was some kind of gaps in between. Now we are having this kind of continuous kind of output that we are seeing over here, right? All the way up to 255. So yes, I guess this is a better output. And now we are going to get all the kind of features, apply different kind of filters in the upcoming videos with respect to this convolved grayscale output. Hi guys, I welcome you all to this fourth video of module 4, and here we are going to take the image output that we had got from our previous video, that is the convolved denoised image basically, and enhance the features present in it by implementing two different type of filters, majoring and Sato. Now both of this we are going to import it with the help of SK image. So let's get into the video. So now that we have decided that we are going to use this convolved grayscale output that we have got by doing the Gaussian blurring, we are going to come over here and enhance the linear features on this M31 data. And I'm going to visualize this in multiple different color maps, and therefore I'm defining this particular list over here called a spectral list, and all of these are nothing but the color map that in which we are going to see the output after implementing two different type of filters, which is going to enhance this kind of linear features, that is majoring and Sato filter, and I'm going to import them from SK image itself. So from SK image dot filters import, I don't know the spellings properly to be honest, I'm just going to copy this and paste it over here. Remove the end part and just give a comma. That's it. So these filters have been imported, and now we simply have to go ahead and do the convolution, implement the majoring filter and the Sato filter on this grayscale output. So what is this grayscale output? I'm just going to copy that. Yeah, this one. copy this array, come back, and let's say this is a measuring filter is equal to this. Oh, not this. Actually, it should be measuring of this. And for set of filter, set of output, I should say, right? Measuring output and the set of output. So let me change this to output as well, and set this to set of, and paste this part. So after running this particular code, what I should be getting is the array with the filter that we have implemented on this particular image. Now what we are going to do, for every color map that we are seeing over here, we are going to create the output for the measuring filter first, and then for the set of filter, and try to see that which of this color map is combined with this measuring filter, giving us the best result. So that's the kind of thing that we are trying to do over here. And now we can achieve this with the help of plt.imshow of what? I'm trying to show measuring output. I'm just going to copy this and paste it over here. I want to show this with what color map? I want to show the color map. I'm going to create a for loop over here. So for color map in spectral list, I'm again going to copy this. You know the reason. Yeah. So this, I'm going to give an indentation over here so that we are not having any kind of errors. And now instead of CMap, I'll be giving color map that I am fetching from the spectral list. And after doing this, I'm also going to do this kind of origin is equal to lower, and give a title to this plt title, title. And with the f string, what I'm going to do is I'm going to give the name of the color map, and I'll also tell that this is a measuring plus this particular thing, right? So this is something that I'm trying to give, and let's say measuring M31 plus this color map. I guess this is good, and I'm also going to hide the axis. Okay. And now after this, I'm also going to do plt.show, and I'm going to run this. Hopefully it is working the way I expect. If not, we'll be modifying this code. Okay, again we got a name error. Spectral list is not defined. Oh, because we haven't run this code. No problem. No problem. No problem. Run this again. Hopefully no errors. Fingers crossed. Yes, we are getting the outputs now. See how we are getting these outputs. Over here, we can clearly see this kind of objects are present over here. 1, 2, 3. Here, over here also some kind of dull objects we are able to see. Over here also some kind of object is being formed, and here is the core of the Andromeda, right? Now I can just scroll down and try to see some kind of different features that we are able to extract over here. Right? If you're able to find something different over here. And whatever kind of color map that you are liking, that is giving you the lot of information, you simply use it for any kind of further analysis. Okay, the reason I have printed a lot of color maps over here is just for your understanding that we can do this kind of things. Now according to your problem statement, whatever it is, you choose the best image that you think according to which is giving the best result. According to me, it's the NumPy spectral color map which is giving most of the information about the image, right? Now according to whatever is the hypothesis that you must create, and to prove that hypothesis, you can do this kind of image processing by implementing different kind of filters and get this kind of outputs and test your hypothesis, right? For example, you might have said that there are some kind of stars at the edge of this kind of image. Near the galaxies, there are this kind of formation of this kind of shapes that we can see near the core of the galaxy. By default, we were not able to see this kind of information. If I just show you over here, we were not able to spot that well, this information as well as this information. But now after implementing this kind of filters, we are clearly able to see this kind of things. And trust me guys, this kind of thing, if you are able to create a subplot out of it, you can literally extract this subplot, download it and use it in your research paper. The outputs like this, how you are able to describe it, it all depends on your skills of explaining a visual appearance in front of you, right? So I hope you have now understood that how we are able to get this particular thing done for the measuring filter. Now I can simply go ahead and look into the Seto filter and look into the output over here with respect to that. So this is my Seto output. This is my Seto M31 plus color maps. Again, same color maps I'm using, and see the output over here now. See, this one is, I guess, much better as compared to what we got with respect to measuring. Again, we are able to highlight all this kind of information near the core of the galaxy, even the side part. But this is much visually, it's more appealing as compared to the previous output that we had got. Right? So yes, according to this kind of outputs, according to your problem statement, according to your understanding, whatever kind of image you can describe the best, you choose that and use it in your research work, right? So I hope this kind of ideas with respect to how you can implement different filters. I have just shown two examples. Like this, there are a bunch of filters you can get with respect to skimage.filters. I can show you the documentation over here. skimage.filters documentation. Okay. And I'm also going to add this part in your notebook also, so that you can just take a look into different kind of filters that are available. Take a look onto different available filters in skimage. Okay, I'm giving this link over here, guys. All right, so yeah, you can explore any kind of filter that you want to see how it is working with respect to the astronomical data that you're dealing with. You just need to know how this kind of, for example, this is the filter, how it works, what kind of input it's taking, and based on this input you try to get some kind of outputs like this, right? So yes guys, that's it for this particular video. And now in the next video I'll be telling you that how you can extract some kind of features with skimage itself. So stay tuned for that. Hi guys, welcome to this fifth video of module 4, and here I am going to show you that how you can take skimage and go to its any kind of feature available in their documentation and implement to get some of the outputs on top of the input image. So the one that I'm going to show you first is the corner fastener. So what exactly this is and how we can use it in Python with the help of the skimage documentation of the features, that's exactly what I'm going to explain in this video. So let's get into it. So now let's take a look into the feature detection and extraction with the help of skimage feature. So just like how we are having skimage.filters, like this we can also have feature. If I just look into that, so here is the documentation. Again, I'll copy this link and paste it into our particular file. Okay, I'll also just create this skimage different features. You can use any one of them by understanding how to implement that. Now that's exactly what I am going to show you, that how you can use one of the feature, that is corner underscore fastener, how we can use it. So what you do is you go to their official documentation and search for that. The one that I am looking forward to is over here. So if I click on this, it's telling me that it's going to take one input of image and sigma, and the output will be two things. Okay, this is output will be two things. Image is an input shape of m comma n, row comma column, and sigma is nothing but the standard deviation used for the Gaussian kernel. By default we'll keep it as 1 only for our case as of now, but surely you can play around with this particular value. But the output that we are going to get over here is W and Q. The first output basically that we are going to get is the error ellipse sizes, and the second output that you're going to get is the roundness of error ellipse. So if you're not understanding this kind of technical terms, no problem. Let's try to go ahead and try to implement how this kind of skimage.feature of corner fastener is working. Okay, I'm just going to copy this name, come over here, and first of all import this. So import, okay, I should say from skimage.feature, import this. I'm going to run this. Now you can pass this on any kind of image that we had created above. I am again going to use the same image that we had used over here, right? You can also use it on top of this Seto output also if you want, okay? But for now, I'm just going to implement it on that this one, convolved grayscale. Okay, so let's go over here and implement this corner fastener on what? Grayscale. or I should say convolved grayscale, right? Yeah. Now if I just run this, and if I check the length of this, I should get two different outputs, right? I should have two outputs. Let me check. Yes, I am indeed having two different outputs. So now what I am going to do is, let me just store it as only one output as of now. Let's say I'm calling this as a feature output. And this feature output is actually having two different things. So check the output of the feature image. So feature output 0, the first output that we are having over here is with respect to actually the error ellipse sizes, and the second output is roundness of error ellipse. Okay, so this is the first, this is the second, right? Now what exactly it's going to depict, we are only going to understand once we are going to visualize them, right? And if you want to check the type of this output that we are getting, the type of this, actually it will be in the format of a tuple because it's throwing two different values, right? So type of this, let's check. And again, length we have already checked that it will be 2. Now we are going to define we are going to split this kind of thing into two parts. One is for the error ellipse and one is for the roundness of error ellipse. So you can just give any kind of variable name that you are okay with, right? Whatever kind of name you are okay with. But what I am going to do is, I'm not really going to define this as of now. I'm just going to delete this part. And color list we have also already defined as the spectral list. Just let me see spectral. Yeah, let me see if it's still working. Yeah, we are having all of this. We are just going to use the same color maps, and now we are going to create the visualization. So how I'm going to do, I'm going to simply say that for color map in spectral list. Now what I'm going to do, on the left hand side, I want to visualize the first output of the feature output, and on the right hand side I am trying to visualize the output of the roundness of error. Okay, one is error and one is roundness of error. So how I can do this, I can achieve this with the help of plt.subplot. Now I want to give 1, 2, 1. Now on the first, what I want to show, plt.imShow of feature output of 0, right? Now any kind of color map I can give, but because I'm using a for loop, I'm going to give this color map, and origin is equal to lower. Yes, I guess this much is fine. I can give a plt.title as what kind of title we can give. We can say that this is error image plus the respective color map, and I just need to pass this in the f string, and also turn off the axis, plt axis off. Now I'm just going to copy this code over here and repeat the steps for 1 to 2. But now this will be feature output 1. This is roundness of error, roundness, right? And I guess we are good to go, and I'll just have plt.title layout because we are plotting the subplot, and then plt.show. Hopefully this is going to work in the way that we expect. Let's see how it's going to work. Yes, first of all, we are having the gray. See, on the left we are having nothing. On the right we are able to see this kind of circular or ellipse kind of shapes that it's being detecting. So yeah, this is the kind of features that you are extracting over here in the format of an array, and this arrays is what you are visualizing over here, right? So you extracted this kind of features, and now you are visualizing them in different color maps, right? So error image plus prism, roundness of error plus prism, then error image with respect to NumPy spectral, and this is with respect to the roundness of error image with NumPy spectral. So yeah, that's it with respect to what we are doing with the corner Forstner. I hope this is making sense, that this is one of the examples that we have fetched from this skimage.feature. Like this, you can go and check any kind of different feature. Like this, in the next video, you will see that we are going to try one more feature, extractor actually, and that is multi-scale basic features, the local features. So I'll talk about that in the next video. And over here, you can surely go ahead and try to check out some different feature by yourself. Try to implement it, and just note that you need to know how it is working by looking into its documentation. If you are able to look into that, if you are able to do your research properly, you can use any kind of feature for a specific task that you are looking forward to. Alright guys, I'll see you in the next video. Hi everyone, welcome to this last video of this particular module. And here we are going to go ahead and understand how we can implement this SKMH feature called as multi-scale basic feature by following its documentation. And just like what we did in our previous video, the same stuff we'll be implementing over here and see what type of outputs we are able to achieve. So let's get started. So now let's try to look into one more feature that is present in the SKMH, that is known as multi-scale basic feature. So I'm going to press Ctrl F to search this multi-scale. I had already searched for that, but yeah, that's where it is. So over here, it's going to take all of this kind of different parameters. You can read its respective information. For now, I'm just going to pass the image and keep everything as default. I'm not going to change anything. Obviously, it's up to you how you want to change it and get the outputs the way you want. And the output will be an array of the shape of whatever is the row and column plus some n features. So as you can clearly see that it's trying to detect multi-scale basic features. It's going to give us the local features for a single or multi-channel n-dimensional image, right? And it's going to be actually the intensity, gradient intensity and local structure are computed at different scales thanks to Gaussian blurring. So all of this kind of information is what we are having, and what we are able to understand from this is that from a given image, it can give us multi-channel output, and in each of the channel that we are going to get, each channel will have one kind of feature that has been extracted. So if I'm trying to implement this, first of all, I need to import this particular thing. So I'm going to say that import this feature. So from skimage dot multi-scale basic features, I should say dot feature, import this name. I'm just going to copy this very quickly and paste it over here, and I'm going to run this. And now I'm going to create a featured, let's say a feature image. I'm going to call this with the help of this, and I'm going to pass in the convolved grayscale. Okay, so this is the kind of input that I'm passing in, and now I'm going to run this. Now let's say what is the type of this thing that we have got. Previously we had got tuple, right? Now let's see what do we get. Now it's a NumPy array because that's what we expect over here as an output. It's going to return an array. So that's why we are saying an array type in the return of this. Now let's look into the shape. That's something important. So this dot shape is what? So we got 300 by 300, and there are 24 local features that has been extracted. And each of the channel is having some different types of extraction of these features and has been stored over with the respective channels over here. Now what we are going to do is we are going to extract each and every channel out of this and create a list out of it. Basically, how we can do this? I'm going to use CV2 functionality of split, and I'm going to pass this featured image split featured image. I'll be creating a list of all the outputs that we get. If I'm running this, it's going to give us a total of if I check the length of this output, it must be 24. The split means what? It's going to split all the channels and it's going to give us as an output each and every channel. And all the channels will be of the shape 300 by 300. So that's the kind of output that we are going to get. So first of all, I'm just going to store it in P1, P2, P3, P4 and everything. That's exactly what I'm going to do. So I'm not going to write everything and make you guys bored. What I'm going to do is I'm copy that part, paste it over here, say that this is equal to that. If you notice, because I was having 24 different outputs, I'm having P1 all the way up to P24. And if I want to check this P1 and also look into the shape of that, it must be 300 by 300, right? Just like that, I can also check P24 dot shape And yes, because everything looks fine, I'm going to go ahead and create a list out of this. Okay, I'm simply going to go ahead and create a list out of this and call it as pixels. Different pixels that I have created, right? And my goal is to visualize all of this features that we have extracted in a particular color map, any kind of color map that you like. I'll be choosing a color map called, I guess if I'm not wrong, I'm going to choose Pixel Prism. Okay, I hope it is present over here somewhere. Yeah, this prism, right? So I'm just going to copy that. Where it is, it's over here. So I'm going to copy this, come back where we were. Yeah, and now finally visualize this kind of pixels in only one color map, and there will be 24 different outputs. So what I'm going to do is, for feature in pixels, what I want to do, plt.imshow of feature, right? I want to use color map, only one color map, that is this one, prism color map, and origin is equal to lower, and plt.title, I can say that this is feature 1, feature 2, like that. I can give this kind of thing. So I can also use enumerate over here, enumerate. So what is this enumerate going to do? It's going to give me two things, index values as well as the feature, that is like what is present inside this pixels. So with this I am going to show what is feature, that is it feature 1, feature 2, right? So it is feature and I plus 1, because index will start from 0. So feature 1 all the way up to feature 24. So that's the kind of title that I'm giving. And then plt.axis, I'm going to turn it off as usual, and plt.show. So if I run this, hopefully it's going to be running the way that I am expecting. Yes, it is indeed. Feature 4, like this, you will just see that the output we are getting over here. We got feature 11, 12, 13, 14, 15, 16, 17. See how in all this image we are getting different kind of features that has been extracted, right? See all this kind of things, all these kind of different features that are associated to this 24 outputs that we have got. All of this we are able to visualize that, and now we are able to visualize that in one color map that is called as prism, right? You can also do this with the help of DP spectral, also grayscale, whatever you are comfortable with, right? So yes, these are the kind of outputs that we have got. We can see this kind of all these kind of different features, right? And currently, because we haven't defined any specific hypothesis that what exactly we are trying to look forward to, so that we cannot prove anything over here. It's just that I am trying to show you that how with the help of this kind of feature extraction techniques that is present in ASCII image, you are able to fetch this kind of information. Now, any image that you are seeing over here, any output, whichever you think is describing the thing that you are looking for, you look for that specific image and then write about that particular part in your thesis, research work, internship report, whatever it is, whatever you are working on, right? So yes guys, that's the whole process. Let me just try to visualize this in NumPy spectral. I'm assuming that is going to look much better. Yeah, this is my personal favorite, guys. Okay, NumPy spectral. Yes, indeed, it's giving us a good result, right? Wherever there are this kind of spots, the stars, we can clearly see that here is the nucleus of our particular Andromeda galaxy. Over here also we are able to see something, right? So all this kind of information over here, we are also able to spot this kind of stars in the background, right? Even this kind of feature over here, this feature over here, all of them are highlighted. So yeah, that's the beauty about this kind of feature extractors. And obviously I'm not going into the details of what all kind of things you can extract. Let's say if your image is having some kind of jets coming out from the center of the galaxy, it might be indicating that it's coming from some kind of X-ray sources, and that X-ray sources are nothing but indicating a presence of black hole or something that is ejecting this kind of high energy X-ray beams, right? So with respect to that, whatever kind of particles you can associate with, you can create your hypothesis and work on that. So yes, guys, that was about how you can use different image processing techniques. Once you are importing the image, I have shown you how you can apply different type of image processing techniques by implementing two different filters and also two different feature extractors. So yes, guys, that was about this particular video. Alright guys, so with this being said over here, we are finally done completing each and every module of this program. Now I'll be creating one more video after this to conclude everything in just one video from the start till the end, and what are some kind of further steps that you can take in order to continue your journey in terms of astronomical image processing or maybe some of the other stuff that can help you from the programs that we have uploaded on Udemy itself. So stay tuned for that. Hi everyone, I welcome you all for one final time in this program on astronomy research data analysis. First of all, I congratulate each and every one of you to successfully complete all the 4 modules of the program. Now let's go ahead and conclude this whole program that we had conducted. So to start with, in the module 1, we looked into the very basics of Python that you need in order to create some amazing visualizations that you have created by the end of module 4. In each of these modules, you were creating some kind of different types of visualization. So yeah, for those things, we understood some basic of the Python. After that, we moved on to module 2, where we took the tabular boring kind of data of stars and converted some amazing visualizations on top of that. We created the bar plot, we created the line chart, we created a lot of different visualizations, including the HR diagram. Then we moved on to module 3. Over there, we took the data from the astronomical surveys like SDSS, DSS, and then did some pixel scaling on the image that we have got in order to find some interesting things that you can see in that particular image. Then in module 4, we use the output from module 3 in order to enhance the features that were present in that image, which we couldn't see till module 3. But in module 4, we saw a lot of things depending on some kind of feature extraction techniques that we had seen from the SK image. So by now, you must be having this kind of an idea that whatever type of visualization you want to create in Python, you are now eligible to do that. You can save these visualizations and use this in any kind of your research work that you are doing, or maybe internship report, or even the thesis work. All of these kind of things, you can surely go ahead and use this. So with all these things being said, I'll bid farewell to all of you guys, and I hope to see you anytime soon in future. Thank you guys.